Okay, welcome everyone. Let me share my slides. Okay, how's this? All right, well, welcome to the 5th Neuro-Symbolic AI Summer School. This is your, oops, 1 second. 1 second. I'm in a slideshow mode. Joe, I think I has the repeat stuff going. How do I turn that off? Okay, maybe we're good now. All right, let's try this again. Okay, summer school. Here's your main link. You can see the very latest schedule. Oh no. 1 second. Technical difficulty.
Okay, Alex, there you go. Check the on mouse click in the top right. Do you see that?
Yeah.
And then get rid of after.
Uh-huh.
But it has to be applied to all. So select all slides on the left-hand side. Yeah, okay. Make sure there are no stars. If you see stars, that's not gonna, get rid of anything with a, on mouse click, not after. Get rid of after. Apply to all. You should be good to go now.
Okay, thank you.
Cool.
Let's try this again. Okay, everyone seeing this full screen? All right, good. Well, I'm Alex. I'm our President and Scientific Director, and you're here at the 5th instance of this summer school. And so we're very happy. Our audience keeps growing and interest keeps growing. Now, what is Neuro-Symbolic AI? I'm actually not going to answer that. You'll find out in our very next full talk from Vaishak Belle. We will introduce it, but roughly speaking, it's a cloud of ideas for kind of what it sounds like, combining statistical and symbolic AI. Okay, and it's 6 a.m. here, and probably a terrible time for most people, so thanks. We are a global event, so we have people all over the world, 95 countries. Now, let me tell you a little bit about the Institute, just for some background. You can find out more on our website, but basically, our reason for existence is to change the field toward smarter and safer AI, as I'll describe in more detail in a sec. We're a nonprofit, 501c3. Our mission is research, long-term research in particular, the kind that is difficult to do over multiple academic grants, and particularly difficult to do for companies that are in a race for survival, typically, and growth. And so we figured you actually need an independent org to do this kind of work. And at least we can help the ecosystem and education around helping people to do this. Now, we do our own research. We also fund academics to do research, and that will keep growing. We're already starting to do that. Okay, and so why do we hold these events in the first place? There's a lot of work to put on, but we've really seen some of the fruits of it over the years. So it becomes a kind of meeting point for an emerging neurosymbolic AI community. It's really fairly large now. We estimate it's about 10,000 people if you put all of our channels together, consisting of researchers, developers, data scientists, and other people who work in AI on the business side, CIOs, CTOs, and a lot of other people just interested in the latest and greatest in AI. Now, many people, including me, feel it is the next wave of AI, and sort of inevitable that at least major elements of whatever the next AI is come exactly from here. This is part of the growing interest. But it's very complicated because it's a cloud of ideas. There are many approaches. They all attack different aspects. And so there's a lot to learn about. In particular, the statistical and the symbolic parts are both complicated and rich and have lots of history and lots of different approaches within them. And putting them together multiplies the complexity. And so I felt education is really necessary, technical education. There's also a kind of education which is, we think it's important, just creating awareness of the capabilities within this space for those who are going to translate it into society, and in particular, policymakers. Now, we are not a policy org, which I'll come to later, but we feel this emerging area is woefully under the radar in terms of policy and just general public awareness. One of the things, which I'll say more about maybe tomorrow, is our certificate that you can get for attending the summer school. And it keeps looking nicer and nicer. Last year was a jump up, and this year will be, I think, extra nice. And I want to also say that our role in the ecosystem is, as I described, but we are not a conference per se, meaning we don't, in fact, many people asked us if we should be or want to be, since we get a lot of viewership and we have such a large community, but we think that role is better played by existing outlets. NSAI in particular, the oldest of the neurosymbolic events that are conference events, started out as a workshop, now full conference, and excellent. You should check it out. Here's the link. It's coming up soon, actually, so it's registration time for NSAI. Check it out. There's also Noose, relatively newer and also very strong. Check it out. And there are also workshops that appear increasingly in conferences, major conferences like FutureOfAI and so on. iClear. Okay, and we are also kind of can function as a central hub for information about all things neurosymbolic. You'll start to see that more and more on our website as it really is starting to expand as an area. Okay, let me just, just so you have some background on the kinds of things we and many people think you sort of need Neuro-Symbolic AI for, something like it, something within this cloud. It's to address these core problems, which you may recognize as things in the headlines everywhere now. Hallucinations and non-factuality. And it gets even worse as you generate potentially wrong text and it goes back into the internet, poop into your own food, so to speak. Many people are concerned with this, and logical reasoning errors. In short, you don't really need to make such errors if you do it with a rigorous reasoning process as opposed to pattern recognition. And of course, the massive costs, both in data and compute, which we're now seeing lead to all sorts of issues beyond the obvious economics. But like if your data that you need is so large as possible, you can't really vet it. You may be violating people's ownership rights and so on. The compute, of course, is very much in headlines now, leading to massive data centers, affecting climate, water, concentration of power, and so on. Uncontrollability. By this, I mean the following a policy or laws or rules inherently in the AI. And we have prompts that you can use in sort of current AI, but there's actually no strict guarantee the prompts are followed. And things can be forgotten anyway in current types of models that are black boxes are difficult to trust for mission critical applications. And one that, these are all things we talk about all the time so far in Neuro-Symbolic AI and actually everywhere in AI. But this last one, I think I just want to highlight because it's not necessarily obvious, but maybe a greater concern, greater than all of them, all of the previous ones, even though they are all significant, is our existential fear of being essentially left out of the loop entirely in a deep way as humans. Now, and this is very real, and we're talking about jobs and so on, but even more deeply, our importance, a reason to exist at all. So, and we may touch upon this in our panel at the very end of the event, but I'll just throw out that Neuro-Symbolic AI, to the extent that, or one way to think of it is, it has two inputs, raw data, as opposed to one input, which is machine learning really has one input, the data, you could say. And now you could say this set of AI ideas, Neuro-Symbolic AI, adds a second input, which is formalized knowledge. That, at least if done in certain ways, would require humans in the loop, okay, to author, vet, modify knowledge, and also reasoning paths, giving humans an actual important place in AI. Okay, now I just want to emphasize, we see our role. Most nonprofits around AI are actually about policy, if not all of them, and that's incredibly important. We need to, as a society, figure out what we want to do with AI. in terms of controlling it and so on. But we are not a policy org. We are starting to think about working formally with policy orgs, and we're not political. Our role is to try to technically enable these things and allow AI to implement some kind of policy strictly. So that's it. And I think a lot of the things you'll see in this meeting are attacking one or more of these issues. So, and we have a new website, just went up yesterday. So if there are any little glitches, let us know. And I'll show some highlights of it tomorrow. And we have a new learning site, and this is where we're starting to make it easier to check out all of our many videos from all of our events. About 230 videos so far, which is only about, it's not all of our videos, in fact. I want to give a special shout out. You may have noticed the nice leap in aesthetics. And that's thanks to Will Wire and Tony Murphy. And if you need a designer, you cannot do better than these guys. So highly recommend them. Reach out to us if you want. Contact info. Now, these are some of the many ways to stay connected with us. On Discord, this is the biggest community, Neuro-Symbolic AI. We have a BYOP program, Bring Your Own Project. And this is where we'll host your project and give you the added visibility of doing so. And places to follow us, literally, you can actually listen to this event from YouTube, usually from LinkedIn, although for this event, I think we're not doing it from LinkedIn. So by the way, you can ask questions in this event from either Discord or YouTube, okay, and we'll funnel those to the speakers. Now, let me just lastly mention a bit what's coming up over the next 2 days, today and tomorrow. So you'll have a little overview of Neuro-Symbolic AI from one of the leaders of the area. Vaishak, Luis, another leader and pioneer of the field, will go over some of these many approaches, as I mentioned, to combining the two sides and give you a sort of way of thinking about a framework for thinking about that. And today is a lot of pragmatic stuff for those of you who just kind of want stuff that works and want to answer the question, what can I do with Neuro-Symbolic AI today? So we'll have a nice tutorial on improving the abilities of LLMs with symbolic techniques. And then very special to me is potentially a coming out of Neuro-Symbolic AI as far as really starting to make the leap into industry. I think research in Neuro-Symbolic AI has gone all the way back to the early 90s, but it's now starting to appear in industry and products. Okay, so we're gonna show you a nice sample of notable companies, two giants, Samsung and Amazon, and some startups and small companies. And this is not all of them, but we thought these were notable in different ways. Okay, and it's growing. then that's, I think, the larger kind of takeaway, and getting better and better. And finally, you'll see efforts at DARPA, and this is as all institutions more or less that have their eye in the future are starting to see more activity in Neuro-Symbolic AI, including DARPA, NSF, venture capital funded entities, and so on. Okay, and then tomorrow we're gonna get into more hardcore research, including theoretical topics. But we're gonna start with a very special, for those, in particular for those of you who are new to logic and symbolic AI. We're going to have a very special session with Bob Kowalski, the creator of Prologue. And this Prologue just celebrated its 50th anniversary, and hugely, it's hard to say how important it was for all of symbolic AI, and still is. And we'll have a number of other important tutorials and two very special panels. One with the leaders, some of the leaders of key efforts in the symbolic AI era, and that is a very special collection and conversation that I'm really looking forward to. And about lessons learned, and ideas for how we can build upon many of the great works that were done. And finally, we're very fortunate to have two very prominent journalists, and Gary Marcus, many of you know, longtime supporter of Neuro-Symbolic AI, and we're going to discuss a lot of societal issues. All right, so that should be really fun. And okay, oops. With that, maybe now I'll pass it to Josh. Let me just say, we haven't had sponsors until this year, so that's new and exciting for us. We're even considering sponsors, we're kind of careful to choose ones that really resonate with us. And fortuitously, Josh Bloom, professor of astronomy at Berkeley, is providing a service for researchers, and we love that. And let me pass it to him to tell you about it.
Thank you very much, Alex. I've got a couple of slides to show. Hello, everyone. Good morning, good afternoon, good evening, wherever you are. My name is Josh Bloom, and I am professor at UC Berkeley and also CEO of Valency. And we're super happy to be supporting this summer school. Give you just a couple of slides here to introduce us, but the big picture here is that we view AI accelerated research as coming, and we want to support open science and open research in this agentic era with a grounding. And what I'll be talking about today is our first product called Valency Bond, that we believe helps ground AI accelerated research in a fresh corpus and helps against hallucinations, but less on the negative side, more on the positive side, can help you and your agents and the ways in which you're working in this new era do things with confidence and trust. I should say that these slides are live, and you can see the link down below, and there's a version of this talk that's up there if you want to follow along. But the biggest takeaway here is that we're hoping you can get a free account and start engaging with this large corpus of literature as you do your deep literature search using your favorite LLMs. So if you have a phone, you can take out the phone now and scan it with a QR code, or even better, if you go to the link that I show up there, app.valency.io/go NS 2026, you'll be able to connect your favorite LLM and get access to this fresh corpus of data. Now, what can you do with that? Well, you can ask a lot of interesting questions and do this with semantic meaning. So you're not just searching the fresh literature with keyword searches, but search in natural language. If you want to know more about somebody that you're about to speak with or is coming up next, Vaishak's coming up after this, ask questions about that person, find out what they've been up to. And instead of having your LLM go off to the internet to do a web search, once you've connected up Valency Bond, you'll end up getting these answers very quickly and drawn not from what is on the web, but from the actual record of what is in the corpus. So far, we've indexed 45 million papers. There's a few thousand that come in every day from a variety of different sources. And behind that is an even larger graph of 450 million citations. So as you wind up asking questions about the citation network, so if we click on the show network, you can see Vaishak's different collaborators across a couple of different areas that he's worked in. And that, we think, is incredibly powerful as you're trying to engage not just with the literature, but the people who are doing this work. And as you ask questions, obviously, and as you write your papers, you're interested in getting the artifacts that are important, like BibTeX exports of those papers of interest. So there's lots of different ways you can engage across any topic of interest, but obviously in the neurosymbolic world, these are just a couple of examples. Asking questions about trends, asking questions about impact across multiple fields. And again, asking about people and their research and how it's had an impact on potentially other fields. If you go into the live presentation itself on the web, you can click on the 38 MCP tools, and you can see all the different tools that are happening under the hood, where we've done all the joins and the normalization of the data for you. We also have a set of skills, and just with a single copy of what you see on the left-hand side into your terminal, if you run that, you can install all these different skills, which are really just a collection of the MCP tool calls that allow you to go even deeper into the grounded corpus. So as I wrap up, just to say, we are in public beta right now. You still need an invite code, and for the whole summer school, we've made one available. If you go to app.valency.io/go/NS2026, or you scan the QR code, which I'll show again, then you can just connect up your Claude, your Codex, whatever it is that you use in your daily life. And after you do that, you'll be able to confirm that you're live and start asking questions grounded in the corpus. So with that, I'll say thank you. We're super excited to be supporting this summer school. Please do connect. One of the fun things is once you're in and you're working with your LLM, if you just say send feedback to Valency, if you see an error with the corpus, or you want something else that's not there, we'll see that and we can act on it really quickly. The last I'll just say is that we really see ourselves as the data layer for this new era of agentic science. There's incredible intelligence that's happening above us. And when you ground intelligence in a real corpus, we think that is a huge power up. And we're super excited to see what you do with it. Please do get in touch and have a great rest of the summer school. Bye all.
Thanks so much, Josh. All right, happy to support Valency and AI to help research itself. Again, free. Now, and we'll make that code available at the break that Josh mentioned. And let me just say, if we had known about this tool, it might have helped us a lot. We do a lot of curation, as you can probably tell, to sort of show you the best of Neuro-Symbolic AI and things we think are very important developments in this meeting and our other meetings. So we're part symposium, part school, you could say. Okay, so, and you'll be seeing more links so you can find Valency. So with that, let's bring in Vaishak Belle. Hey, Vaishak.
Hey, how you doing?
Good, good.
I'm going to try and replace, I think you probably see the whole window. I'm going to try and... How's this? Can you see the screen?
Yes, there you go.
Okay. Good.
All right.
All right. Then yeah, thanks, Alex. Thanks to Alex and Centaur to have me over to present. I'll try and stay on my screen because I think if I switch, it's going to give you an infinite regress into all the ways the screen can be shared. Again, and Alex, please feel free to interrupt me if something goes off on my end. So I'm very excited to be speaking at the summer school, and thanks to Olga and Alex and Valency as well for supporting this initiative. So what I thought I would do, as Alex said, and sort of led his way to Neuro-Symbolic AI, is I thought I'd have this catchy title from a paper that Gary Marcus and I wrote earlier this year. The future is neurosymbolic, and hopefully for those of you who are new to the area, you will sort of be convinced. Interestingly, just recently, just on Twitter, I've seen a lot of folks who are not from the neurosymbolic sort of area make a similar claim about how a lot of the successes you see with Claude Code and Codex has kind of a neurosymbolic flavor to it. And maybe this is what Neuro-Symbolic AI looks like in the future. Who knows? So one of the motivations for Neuro-Symbolic AI, as Alex kind of hinted at, is that, you know, AI systems in just about 10 years are making very, very significant decisions. So 10 years ago, you could be an AI researcher and you could write your paper and submit it to NeurIPS or AAAI, what have you. And, you know, you'd be lucky if there are a few people in the audience who'd go back home and read your paper and do something about it. But now, you know, at least with the big tools, everybody's picking up on it. They're being connected through MCPs and so what. And this makes it a challenging sort of enterprise to be an AI researcher in, because the systems you develop have very significant consequences. So, you know, to some extent, you know, we've had this issue of explainability, and I'd argue that LLMs are making it, you know, far worse. So, you know, we use AI in criminal sentencing, medical diagnosis, loan approvals, and we could, I think, agree to some extent that, you know, there is a sense in which we want these systems to be accountable, but we don't have a very good definition of what accountability means. And so we fall back on some kind of traceability, or some kind of trace or structure or audit trail, so to speak. And all of these things require structure, knowledge, provenance, which are difficult things to really imagine the way systems are being built right now in a very ad hoc fashion, whether it's agentic or LLM based or Gen AI based. So, you know, understanding how we can harness you know, all the learning and the inference to some kind of structured information is a challenge. And this is why Neuro-Symbolic AI probably is the only way forward to get this correct. So I'll pitch my roadmap roughly like this. I'll just briefly talk about the AI landscape. And again, listening to Alex, you might have gotten a sense, but let's just recover the basics. I'll then describe to a very, you know, in a broad way what Neuro-Symbolic AI is, what the design space looks like. some of the key directions we're seeing in the field. I'll then talk about some work we've been doing where we've been trying to better understand where LLMs fit in. And in a way, this connects back to what Josh mentioned about valency, where you connect to some sort of knowledge source, use an LLM for that, but then you have some sort of neuro-symbolic architecture that leverages that and uses that in some way or another. I'll conclude with some challenges and open problems. Some of these are more academic, some of them might be more on the side of the industry, but I think they are challenges nonetheless. So it's worth thinking about and working out what exactly the implications are. The history, of course, of symbolic AI goes back to the history of AI, and John McCarthy, one of the founders of AI and perhaps the originator to use this term, had this idea that symbolic logic could serve as some sort of common sense program, as he called it. He said, you write programs which have some sort of commonsensical information, and the programs act on this information and do things with it. In a way, you can see that vision going all the way through program learning, program induction, and also what we're seeing right now with code generation using natural language prompts. Now, symbolic logic, if you're not familiar with it, is a mathematical language for describing symbols and expressions. And then what you use is a kind of engine that concludes proofs or truths based on this information. So, as in terms of strengths, again, because it comes from a history of mathematical reasoning and mathematical knowledge, there's explicit structure, there's very strong semantics. We talk about principled reasoning solutions. So we have a clear definition of what it means to reason. And you might have seen the word reasoning quite a lot now in the LLM landscape, but what it means in the logical space is a very clear mathematical object. There is a function that takes a certain output and gives it the same output no matter how you rearrange the input. Okay, so there's some sort of symmetry, there's some sort of structural correctness in the way it works. So these are the strengths of logic. But then there are limitations because you have to write everything down. There was a challenge back in the 50s and 60s. And of course, this is partly due to hardware, partly due to the fact that we just didn't know how to deal with complex sensor data. We didn't have a very good way to connect that sensor data, which is very high dimensional. You take an image of say 30 by 30, there's lots of pixels. And how do you capture that thing in a symbolic expression or a symbolic language? Wasn't very clear, and it led to a combinatorial explosion, not surprisingly. But then people started looking into this and they realized, well, you know what, using logic to formalize open-ended domains is hard. What do I mean by open-ended? So, if you're building a robot for a coffee machine or in a coffee scenario, you also want the robot to act in case a person falls down, or if there's a dog that jumps on a human being, you want the robot to act in these scenarios. So sometimes you can't quite write down everything the robot needs to know. So there's an open-endedness to this. And how do you put that into logic wasn't entirely obvious. The other kind of challenge is that, when you look at the real world, a lot of things are kind of true, but not always true everywhere. A simple example is we know that smoking and vaping is bad, but maybe there are some people with certain kinds of genes who have some sort of resistance to it. So you want to say that smoking likely causes cancer, but you can't say smoking always causes cancer. Right? So this is some of the challenges with using logic. And I'd argue that the machine learning certainly gives another interpretation to the last point. But I don't think machine learning has found a very robust and general purpose way of dealing with open-ended knowledge. And in fact, we know this already from demonstrations. So when people deployed self-driving cars, for instance, there were a lot of crashes because sometimes the cars encountered something they hadn't seen before, right? So this is a problem we'll come back to. And again, I'm not saying that the symbolic area has a solution to that. I think it's worth thinking about different ways to address that problem. And symbolic knowledge might offer some sort of insight into how we could constrain and understand open-endedness. Okay, so it's a kind of a research challenge, but certainly training from data alone is not likely going to solve this. Okay. We then have the deep learning era, I'd say maybe from 2012 onwards. And again, there's no surprise here that there are lots of interesting breakthroughs. And this is owing to a combination of things, right? Training techniques have gotten sophisticated. They've also gotten more opaque, but they have gotten very sophisticated. Hardware is incredibly powerful. Even your phone is more powerful than some of the computers we had in 2010. We have access to a large amount of data, the internet corpora. So all of this has led to, a decade or more of scaling. So it's not surprising that we're seeing a massive improvement in performance. But the question really now is it sufficient to learn from data alone? Are we missing something? Okay. And from a conceptual point of view, I'd argue there are very clear limitations of the deep learning approach. Okay, so going back to what I said about the car example, there's distribution shift fragility. So you train the model in one distribution, you go and deploy it somewhere else, and you don't know what happens. It may not work. Okay, we don't have guarantees, so often we have seen this, that sometimes deep learning models can give you predictions that don't actually make sense. They violate hard constraints that apply to the domain. So this certainly happens in things like when you apply it for physical modeling or environmental modeling, you have lots of constraints coming from these domains, and you don't quite know how to make the deep learning system respect those constraints. Okay. There is this interesting point about compositional reasoning. And again, here, I would say there is a bit of misunderstanding on how well compositional reasoning happens with LLMs, because to some extent, what's really happening is that they are trying to compose patterns and see conjunctions of patterns, but compositional reasoning can be a lot more complex. So for instance, I could understand by looking at a problem that I could break it apart, solve the independent components and put them together. I can understand the problem at different levels of abstraction. And if you think hard about it, it's not entirely obvious how we can model these things with deep learning. Okay, so we have some ideas that as you train deeper and deeper networks, there's some amount of hierarchy or abstraction in the intermediate layers, but whether it all comes together in a systematic way is not entirely obvious. We know, for instance, deep learning models are very sensitive to the size of the data. If you have very small data sets, then you can have funny behavior from deep learning models, and this is a problem in some cases. Okay, I'd argue these are not engineering limitations, right? So they are structural properties, and I'd say this because if you think about data dependence, just by the nature of the hypothesis space with deep learning, it's not entirely obvious that you can get rid of the small data problem immediately. I mean, there are ways you can transfer some information. In some cases, you can do things like zero-shot learning by, transferring weights and so on. But all of them are not, bootstrapped from scratch. They are bootstrapped from some other model, and you're not building them from scratch. Okay, so these are issues that are not easy to fix by just building better systems. Okay. Of course, the argument that took off Twitter by storm, I'd say 2 or 3 years ago, and maybe continuing today, is scaling the answer, right? And again, we don't know where this is all going to lead to. We know that some of these models are getting more and more powerful, but we don't quite know exactly, where is that boundary between how much scale is needed, compare that to the performance. Okay, so just to give you a contrast, something like GPT-4 was likely trained on 1 trillion parameters. Okay, so that's 100 times fewer than the human number of network connections in the human brain. So think about it. The human brain uses about as much energy as a laptop, whereas to train a GPT-4 requires enormous amount of physical and economic resources. Okay, so it's that massive. It's used almost all of the data in at least the English data, okay? And yet you'd argue that it doesn't quite do the job. It makes very silly mistakes. And the question is, okay, do we accept these silly mistakes and move on? Maybe we can. And this is, again, this is for all of us to decide as scientists, as users, and so on. So I'm not trying to be dogmatic here, but I certainly think that there is an issue of proportionality. Given the amount of data we've trained it on, the amount of cost that's gone into it, it doesn't seem like the most appropriate use of resources, especially if there's a case of diminishing returns. So now with the GPT 5.6s and the Claude Fables and so on, we're seeing, better performance with certain things, especially code generation and mathematical proofs. But it's debatable whether it's useful as a plug and play solution for all problems that we have both in the industry and science. And many would argue that's not the case, right? So I think it's worth thinking about, whether we should keep paying this cost of scaling, and whether there are other ways around it. And this brings me to Neuro-Symbolic AI, right? And Neuro-Symbolic AI is a very broad field. Lewis, who's going to be talking next, has been part of this field for a very long time. And, to some extent, you can see instincts of, the combination of neural reasoning combined with symbolic reasoning, even back to the 70s, okay? So largely, we think of these as a family of approaches where you have some sort of structure from the neural side. This might be pattern recognition, this might be reasoning or learning. And then you have symbolic representations that tie into these neural outputs, okay? So there's a lot of different ways you could do this. You could think about both of them sort of influencing each other. You could think about a sort of a divorced or a modular approach. And this leads to a very broad design space. So there are different logics. Again, I won't go through all of them in any detail. I'll upload the slides in case you want to look at it, but there's very different many logics. There's a propositional, first order, there's different kinds of semantics, there's probabilistic or fuzzy. Again, depending on where you're coming from, the industry or the academic circles, some of this may matter, some of this may not. And this is something we're navigating and figuring out. We're trying to work out, which kind of semantics leads to better guarantees, which sort of language is appropriate for which domain. So we don't have a complete, map of everything, but this is part of the research space. And that's why it's so exciting, because we're trying to tackle these different questions on representation and learning in a joint way. And this is what makes Neuro-Symbolic AI very exciting. Okay, so even the question of symbol emergence, which I would argue is something that even cognitive scientists and philosophers and psychologists think about, how we get the sensory motor data, through our eyes and ears, and we use that information to build concepts and constructs. How do we do that? And this connects in a way to the neurosymbolic as well as symbol emergence paradigm. Answering that question might help us provide a framework, a computational framework, to understand things like symbol grounding. So, one of the discussions we've seen, at least in the last couple of years, is Neuro-Symbolic AI a kind of technical implementation of Daniel Kahneman's dual process theory of thinking fast and slow? Think of neural networks as system one, which is fast, exponential, and do you think of symbolic reasoning as system two, the deliberative, the cognitively inspired, and so on and so forth. And again, I don't want to suggest that it is an actual realization or a computational realization. I think there was a debate where with Daniel Kahneman at AAAI a few years ago. And it's, so you can debate back and forth on this, but I think certainly as a framework, and if you consider the broad design space, there are opportunities to think about an implementation of thinking fast and slow using Neuro-Symbolic AI. And, and that makes it exciting. I'll mention a few sort of interesting directions. Again, this is your mileage for these directions may vary depending on which sector you're coming from. But I'll go over them very briefly. And if you're interested, I'm sure you'll look it up following the slides. Okay. So one of the big questions, and this especially comes up in the large language model and the agentic era, is how do we embed expert knowledge into these LLM pipelines or any sort of learning pipeline? Okay, so there's a lot of work on knowledge graphs, ontologies, and any kind of expert knowledge that could be injected as a kind of a structural constraint or structural information for these neural modules, including large language models. Okay, so this is a big area. To some extent, retrieval augmented graphs in LLMs can be seen as a kind of embedding of expert knowledge, although the reliability of RAGs it has been challenged a bit, but nonetheless, this is a space in which it belongs. Okay. Going back to, I guess, the foundations of Neuro-Symbolic AI, a question is, how do you write programs that can embed and use concepts from neural networks into a logic program? So as Alex said, Bob will be speaking tomorrow on logic programming, and he might ask the question, well, if I have neural networks, how do I use that information inside a logic program? And then you have this kind of interesting space of neuro-symbolic programs. I'd say if those of you who are familiar with the concept of probabilistic programming, that was very popular about 6 years ago, this could be seen as the next iteration of that, where you have symbolic, neural, and probabilistic all embedded in the same programming paradigm. Okay, so it's an interesting space in terms of semantics and language if you want to look into it. A classic problem going back to explanations of neural networks is, can we learn, given a neural network, can we learn something that looks like a logic program from these networks? Okay, so I call these differential program induction. Program induction is a classic problem in computer science where you try to learn a program from data or examples. And in differential program induction, you try to do this using an end-to-end network in some way. Okay, so can you use a neural network to extract programs? And maybe this extracted program could also serve as an explanation for the neural network. A challenge, as I mentioned, with neural networks is that they don't often obey constraints, structural constraints and domain constraints. So a big problem in one of the sub areas of Neuro-Symbolic AI is, how do we inject constraints into the training function? Okay, can we build a training regime that respects these constraints? What would it look like? Is it always satisfied? Do these constraints sometimes fail? What would it mean for a domain, especially in safety critical domains? So there's an area of research in Neuro-Symbolic AI that focuses on the so-called loss functions, where you go into the loss function of a neural network and you augment it using some sort of logical construct and see what happens. Okay. Then there is the whole area of applications of all of these problems in a temporal or dynamic setting, because especially if you think about reinforcement learning agents that are being deployed to act in robotics, you need to think about what neuro-symbolic paradigms look like in a robotic setting. And I think we'll see a talk about this tomorrow on neuro-symbolic AI in robotics. Okay, so there's a lot of interesting challenges here too, like how do you provide constraints to reinforcement learning agents that are logically informed? What would it look like, and so on. So worth checking out if you're into reinforcement learning or verification. At a more fundamental level, we have this big question of, what are the semantic choices? How do the semantics of the logic and the probabilistic and the way to come together, how do they affect each other? How do they affect the overall learning paradigm? How do they affect the application, right? These are interesting questions that we don't have answers to, okay? But semantic choices, I think, is an interesting angle of research that you often see in the neurosymbolic space. I'll very briefly talk about two pieces of work where the symbolic approach gives you a clear insight into what you can do with Neuro-Symbolic AI. Okay, so 2 years ago, we started looking into the problem of fairness, of building machine learning models that behave in a fair way. The idea here is that, often there's a version of fairness called as counterfactual fairness, and what it says is that if I change a protected attribute, it wouldn't change the outcome. So let's say I'm applying for a job and I'm offered the job, and if I came back to that model and said, what would happen if rather than male, if I was identified as female? Would the outcome still hold? And again, in this case, we are trying to model what the model might do if the protected attribute took on a different value. And if the answer came back as a no, then you would say, yes, the model is unfair, because if the person is male, he gets the job, but when he applies as a female person, the job is no longer offered to him. Okay, so what we showed is that using a neuro-symbolic approach, you could sort of look at this fairness criteria as a structural constraint when you train the model and see what happens, and you can trade off the fairness constraint with the accuracy criteria that you might be looking for. Okay, so it's a way to carefully and cogently study the relationship between fairness as a requirement and what you expect the model to do in terms of its accuracy measures, and see how we can compare these two. Okay, so the symbolic approach here is really trying to give you that handle into that constraint and see what it can do with it. Another sort of area we've looked into is the case of explanations. So as I said, explanations is a major topic in machine learning, and a very popular definition of explanation that came up, especially in the context of the GDPR, was so-called counterfactual explanations, where you're basically saying, I apply for a loan, my loan was rejected. What would I have to change to get the loan approved? Okay, and there are definitions and approaches to doing counterfactual explanations, but what we've kind of showed is that when you have a symbolic approach, you can also throw in diversity constraints. Okay, so for instance, if the solution came back and said, well, if you change your job and got a double the salary that you're getting now, then you would certainly get the loan approved. But of course, it's not realistic, right? If I could change the job and double my salary, of course I would do that. I might have constraints that prevent me from moving from the place I'm living in. I might have other commitments in terms of loans and mortgages. So diversity constraints allows us to pose these as constraints. And so the counterfactual explanation would take these constraints into account and give me back an explanation that respects these constraints. Likewise, you could also ask, what is the reason for explanations? Okay, so there's some research in psychology that says that the reason we ask for explanations is that because we are missing some information, we don't know something, and we're expecting the explanation to fill the gap. So there is an area of research that focuses on mental state modeling in a mathematical way. And you could tie counterfactual explanations to this kind of mental state modeling. Okay, so you can say things like, who is the explanation for? Because depending on who the explanation is for, my explanation might be different. What does this person not know? And based on that, I might try to provide an explanation that fills the gap. Okay. So, it's, the good thing, as Alex mentioned as well, is that to some extent, the industry is also taking note of the changing landscape. In fact, this is just from Google DeepMind, and I thought I'd mention this just because they are perhaps at least open about what goes into the insides of these systems in some regards. But alpha proof and alpha geometry, if you've looked at them, basically they have some way of tying either an LLM that looks at a natural language context, translates this to some sort of algebraic or symbolic solution, computes the exact solution, and then gives back the answers. Okay, that was alpha geometry. Alpha proof is being used as a proof assistant, and again, it uses this theorem prover called Lean, which is now becoming really popular in the mathematical circles as well. Okay. One thing I thought I'd mention is AlphaFold, which, as you might know, was cited in the Nobel Prize in Chemistry in 2024. And one of the interesting things to note there is that, in just a few years, of being introduced. It was mentioned in the Nobel Prize and is quite rare. Usually, a person has to retire before they get acknowledged in the Nobel Prize. What's interesting about AlphaFold is that if you read through their white paper, there's a lot of structural domain knowledge about how molecules come together and how certain structures, chemical structures, can react with other structures. And all of this information from the looks of it is injected into the loss function, okay? So they don't actually make use of a logical solver, so to speak, or a symbolic solver, but I would argue the inspiration for this is very neuro-symbolic, okay? So the question is neuro-symbolic AI in the future look a bit like that, where the relying on the symbolic structure is completely removed and it's somehow embedded in the training architecture? I don't know the answer to that, but it's an interesting question for us to ponder. I found these interesting quotes as well from the World Economic Forum and the HBR that for the first time, I thought they mentioned neuro-symbolic AI, but they mention it for the reasons that I think Alex went over in his slide deck as well. I mean, you want to get rid of the hallucination problem, and maybe the hallucination, the confabulation problem is a structural thing, and it's not something that you can engineer away. So if that's the case, then using ontologies, using expert knowledge, and using symbolic solvers might be a way for us to make sure it doesn't happen, okay? So lots to be said. Certainly, if you're coming from the industry space, I'd really recommend for you to give it a think on how neuro-symbolic AI could impact and improve what you're building with agentic workflows, among other things. Okay. The last bit of my talk, I thought I'd mention some interesting observations we had when we tried to leverage large language models in the neuro-symbolic pipeline. And as I mentioned, the classic way to use this would be to use the large language model as a natural language interface, right? So you have some sort of prompt that is facing the customer or facing the user. They write things down in natural language. We find a way to translate this into some sort of symbolic structure, execute it exactly, return the answer, okay? Now, I'd say the inspiration and perhaps the first instance of this goes back to Wolfram Alpha, if I'm not mistaken, where when ChatGPT came out, they had this blog post where they were suggesting, this could be an interesting way where you write something in ChatGPT, and especially if it involves calculations, it would go off to Wolfram Alpha, which would do the calculations and come back with the answer. So even though Wolfram Alpha had that connection, I think for a while, ChatGPT and OpenAI didn't pick it up. I'd say in 2023, 2024, you saw lots of tweets of people asking simple computations to ChatGPT, and they got completely fabricated responses, okay? Whereas if you make the connection to Wolfram Alpha, of course, it would do the calculation correctly. I'd argue now with Claude Code and Codex, this is more direct. If you ask Claude Code or Codex something to do with your mortgage calculations, it's going to spit out a bit of Python code or a bash script where you can actually see what's happening. You execute the script and it gives the answer. Okay, so in this sense, I'd say it is neuro-symbolic once the translation is done to the programming interface. Okay. So we were sort of pushing along these lines, and the question again we're asking is, if we need explicit symbolic machinery, why not just use symbolic solvers? And this could help us build systems quickly rather than retrain them for specific use cases, okay? So we try to pair the LLM as an interface to a symbolic system as a reasoner. So what's a good test bed for this? We got interested in the theory of mind back in 2023. So the theory of mind is a classic problem in computer science and comes up in cryptography, comes up in game theory and a whole bunch of other areas. And the idea is, if you have a bunch of agents in the picture, in an environment, and they're communicating to each other, what do they know? Can they collaborate or coordinate and come up with an answer? So a classic example of theory of mind applied to computer science is distributed systems. We are trying to work out, can two remote agents exchange information reliably. Okay, there are many other applications of a theory of mind, and in mathematical logic and symbolic logic, it takes the form of epistemic logic. Okay. When we looked into this, somewhat surprisingly, there were tons of claims of emergent theory of mind abilities of LLMs. They weren't very reliable, but the argument was, again, a bit like how there's arguments about LLMs being able to do mathematical reasoning. We found that there were lots of claims, and we sort of decided to challenge it using our work. And what we discovered is that, you take a theory of mind problem, okay, you can either ask the LLM to answer this problem exactly, or you could obtain a symbolic solution, run what is called as the model checking on the solution, return the answer, and compare the two results. Okay, I'll be slightly faster on this because I need to wrap up in the next 5 minutes or so. And largely what we found is that theory of mind, if you do direct prompting, so you just ask the LLM for the answer, it's a little better than random guess. So it's about 58% accuracy, but you get it to do the translation and you answer it, and it goes up to 91% accuracy. So you might wonder, why not 100%? Why does it stop at 91? And there are two reasons for this. Okay, the first reason is that sometimes the translation gives you an ill-defined formula. So it's not well-defined expression in the mathematical logic. And so the solver just rejects this as incorrect input, okay? In other cases, the translation itself is wrong. So even though the translation is well-formed, because it is wrong, the model checker gives you the wrong answer because it's working on the wrong input, if that makes sense, okay? So I suspect that as you improve on that engineering effort, you could get to 100% accuracy. Now, when we figured out this translation was going wrong, we decided to dig a bit deeper into this, and we looked at looking at temporal reasoning. Okay, so as you know, one of the classic problems with knowledge graphs is you're interested in reasoning about time. So, for instance, currently you might say, Brad Pitt is married to person X and Y, but at a previous time he was married to somebody else. So how do you work out whether the LLM or the neural system is keeping track of these temporal constructs correctly? Okay, so what we wanted to do is we wanted to do temporal reasoning with LLMs. And we wanted to do the reasoning itself using a symbolic solver. So there's something called Allen's interval algebra, which is a symbolic solution for dealing with before, after, during, between, and so on. So we wanted to substitute that bit of the pipeline with interval algebra and see what happens. And so the expected result, of course, is like with the previous slide. We expected a little bit of an improvement or a large improvement over the neural baseline. But the actual result is that there was no improvement. And in fact, in some cases, it got worse. Okay, I'll let you think about why that could be for a second. But what turned out to be the case, okay, was that the production of the temporal graph from the LLM was wrong. Okay, in some cases, it took a natural language, it produced a wrong temporal graph, and because we acted on the wrong temporal graph, we got the wrong answer. Now, the interesting thing is the wrong temporal graph was also given to the LLM, okay? But the LLM chose to ignore this and decided to use its own internal weights to answer the question. So it got the answer correct, even though it was working on the wrong knowledge graph, okay? So this is why we call it a double cautionary tale. So the first caution here is that the bottleneck is extraction. If the LLM makes a wrong translation, you're working on the wrong input, okay? The second caution is that the LLM might give you the correct answer, but for the wrong reasons, okay? So the correct performance is not a reliable measure of reasoning. You need another way to make sure that the LLM is coming to the answer correctly, and not just producing an answer and coming up with an ad hoc explanation for it, which kind of looks right, okay? So there's an area of literature that tries to understand how can we extract reliable explanations from LLMs? And again, because it's a research area, they should tell you that it's not a solved solution, okay? Last 3 minutes, let me wrap up. So A lot of interesting questions here. Okay, so one of the challenges is, do we need the diversity? Is Neuro-Symbolic AI a broad church a good thing or a bad thing? I'd argue it's a good thing, mainly because as attractive as it is to come up with a unifying theory, sometimes you need different logics and languages and representations for different applications. And although we should make an effort to relate them to, it's not necessary that everything falls under one umbrella, okay? And maybe it won't ever fall under one umbrella, we'll see. The other issue is, from the point of view, from a practical point of view, if you're a person building an application, how much of this information do you need to provide by hand, and how much do you want it to be learned from data? I'd say this is a classic question that nobody has an answer to, going back to when people were figuring out where the learning and reasoning boundaries lie. Okay, we don't know. It's a bit like asking, for humans, are they learning everything from scratch? We know that not to be the case. Evolution has provided us with some structures to learn. So where is that? What's the boundary for how much bootstrapping is needed versus how much needs to be learned from scratch? Okay, an interesting mathematical and conceptual challenge, I would say. Trustworthiness. So, we make a case that Neuro-Symbolic AI would provide the foundations for technical correctness, but it's worth keeping in mind that trustworthiness is also about norms. So we need to think about how we can incorporate norms in the agenda. And it's also about socio-technical constraints, okay? So if you're deploying a technology in some sort of scenario involving people, we need to think about what the impact is. And when we think about that impact, not all of those impact values are measurable or quantifiable. So we need to work out, where is the boundary of what can be captured using mathematical language and what needs to be left to policy, regulation, and informal guardrails, okay? There's lots of interesting open problems from the semantic foundations to finding the boundary of scaling versus symbolic reasoning and what's the best way to combine the symbolic and the neural. But I'll leave this for now, and these are good questions if you're interested in doing a PhD in Neuro-Symbolic AI, okay? So to wrap up, neural and symbolic approaches on their own are likely insufficient, and scaling, which seems to be the main punchline from many of the big tech companies, is probably running into economic, political, and scientific limits, okay? This is still to be seen, but there are reasons to be cautious here, okay? And Neuro-Symbolic AI may be an approach for reliable, accountable, and alignable AI. A point that Gary Marcus made in our paper is that Neuro-Symbolic is necessary but not sufficient. And the reason for this is that, of course, we see Neuro-Symbolic AI as the essential language to combine the neural and the symbolic. But if you think about trustworthy AI, as I mentioned, given the interesting socio-technical considerations, it's not the only thing we need to care about. So from a technical point of view, Neuro-Symbolic AI is certainly necessary. But if you're thinking about AI deployed as a whole, we need to think about other criteria. So it's not sufficient in the long run. So with that, I thank everyone for listening and for paying attention. And thanks, Alex, again, for inviting me.
Thanks so much, Vaishak. Excellent overview. I think you captured things extremely well. Let me just propagate. Oh, one question, which is for Vaishak, which is before we bring on Luis. Where do you publish basically in Neuro-Symbolic AI?
Now running for a startup as a workshop, and Luis might say more about it anyway, but it's been running for a few years now, and it's a very good venue for getting your work out there to the Neuro-Symbolic community. But I'd say if you look across the spectrum Neuro-Symbolic folks are active in, I would say, in all conferences, mainstream conferences like AAAI, HCI, NeurIPS, ICML, right? So there is certainly appetite for a Neuro-Symbolic AI in all mainstream machine learning solutions. I think the challenge that we would face as a community is this battle from the other side, where somebody might argue scale is all you need. Here's an LLM with a trillion parameters, and look how well it does, and all of these things. So finding that sweet spot in terms of discussing and showing reliability, showing performance, and showing that you can get away with small models but with better constraints might be the way forward.
Okay, excellent. Thanks so much, Vaishak. Check out Vaishak's excellent work coming out of his research group at Edinburgh. And I'm sure we will see Vaishak in another setting soon. All right. Thanks so much. All right. Now, Luis. So Luis, as those of you who followed our events before know, is one of the pioneers of the whole area, and had the foresight to start working on this before most people. So now he's going to tell us about this thing Vaishak mentioned, this kind of zoo of different neurosymbolic approaches, which is both a good and a bad thing. But Luis will, although intellectual diversity is generally good, Luis is going to tell us how we can organize this in our minds. Take it away, Luis.
Oh, hello. Good morning. Let me share my presentation here. Just a second. Yep. Just okay. I hope you can see it well. Okay, the array of principles for Neuro-Symbolic AI. So this is the result of Dagstow's seminar that we ran last year with several researchers in the field. And this paper is coming, it's probably going to appear in September 26, most likely in the communications of the ACM. And the idea here is to have design principles for AI systems. And we can also see that several existing systems in AI can be, in a way or another, framed under this spectrum, under these principles. And I hope we can have some interesting discussions and some food for thought. Of course, this is the work of many authors. They are listed here in the first page. And all failures in the presentation are on me, of course. So the summary. When you talk about Neuro-Symbolic AI, we have a spectrum of systems, principles, ideas. And I always say that you can have tightly coupled Neuro-Symbolic AI systems, and you can have loosely coupled Neuro-Symbolic AI systems, right? Things that come more from the neuro side, machine learning side, and this spectrum goes from, say, integrating an existing system, an AI system, or a Gen AI model, or a Gen AI technology that's in production, like large corporations are doing. And on top of that, you can use a theorem improver or a verifier to check properties of this neural system or this Gen AI system. And in the other end, let's say in the other side of the spectrum, I'm not going to talk about everything in between, you have what I call Neuro-Symbolic AI without a hyphens, right? That are tightly integrated, tightly coupled systems. Is the kind of work that Arthur and I did in the early days, where we would see the neural network both as the learning engine and the inference mechanism, so much so that we would translate rules inference rules into the architecture of the network. So just to see that there are, just so that you have an idea that these things come into a spectrum. So, and we also, when we design system, we have to think about what we are designing, and this happens in a spectrum or on how we integrate principles of design that made these systems more tightly integrated with respect to Neuro-Symbolic AI and more loosely integrated. And I also present some perspectives on Neuro-Symbolic AI research and industry. Okay, what's this paper is about, right? I bring some bullet points here saying, of course, for those who are not in the field, and we always have audiences that are very diverse, Neuro-Symbolic AI, if you are seeing and watching Vaishak talking, brings together the statistical nature of machine learning and the logical nature of reasoning. In the early days, as Alex has just mentioned, when we said, oh, we are working on Neuro-Symbolic AI, and we are combining logical reasoning with neural networks. And people would ask, why? Is that, does it make any sense? Why are you doing that, And the idea was exactly that we could envision that systems where more than one artificial cognitive ability would be integrated together to have richer AI systems. So that was the whole principle of having Neuro-Symbolic AI. And we say that in a paper that we published 2023, we kind of summarized the perspectives of the field. And you can read this paper, it's called Neuro-Symbolic AI, the third way. So another point that's very important that this paper makes a sense is that industrial AI systems that use sensor, text, fusion data, video streams, they are typically assembled in ad hoc perspectives, ad hoc design principles. They are very focused on task-specific modules, task-specific architectures that are designed and optimized independently. Those who work in industry that know exactly what that means. When you design a pipeline for software production, you are very specific on what you're doing. And then, of course, you have to think about compositionality, but you are going to mention how these things can be good or bad, right? So this divide and conquer approach that we called in the paper, it accelerates the development of production code, but results in non-compositional pipelines several times with no formal guarantees on the behavior of the system, right? In the composed behavior of the system. This is a very important thing to consider. So error propagation, discontinuities at module interfaces, and in the let's say the modularity of the system, the difficulties in understanding what exactly is going on is something that we see to these days, and that we're going to discuss over this couple of days. And I saw that Vaishak also mentioned that. And the persistent problem of LLM hallucinations, to this day, I was again making some tests yesterday, and then again the problem persists. 4 years after the release of ChatGPT, we still persist with the problem of hallucinations. And of course, it suggests that we need a more principled solution to avoid this problem or to solve this problem, because this problem is escalating. Even in science and technology today, when we look at publications, we see the vast number of hallucinated citations and other content in papers that are published every day. And we are going to frame, the idea here is to frame the design of Neuro-Symbolic AI systems around 4 core principles: reasoning, assurances that we ideally want to offer and want to offer to the users and consumers of production level AI, the interfacing between people and systems and in between the components of the systems, and the learning dimension, of course, that comes in Neuro-Symbolic AI. The learning and reasoning dimensions are the fundamental components of Neuro-Symbolic AI system. And these principles, they provide a blueprint or a framework for building reliable, explainable, and compositional industrial AI pipelines and AI technologies. And I always like to make some historical connections in my talks, forgive me the aside, and the current trends in Neuro-Symbolic AI, I would say we have, the beginning of research, as Alex was mentioning, late 90s, early 2000s, and then more interest in Neuro-Symbolic AI started around 2019 when we had this AI debate with Yosha Benjo and Gary Marcus, where they're trying to understand how AI could move forward with better understanding of the reasoning component integrated with the neural learning component. And at the time, we also had, the late Daniel Kahneman taking part in several debates on the future of AI, perspectives on AI, and several parallels have been drawn between his theory of cognitive reasoning that's summarized in this book that's very well cited and very well read by a lot of researchers, Thinking Fast and Slow, and the parallels that this book can be drawn with our foundational work in integrating logic and neural networks. So if you are more interested in high-level discussions about cognitive reasoning and cognitive learning, you can read Daniel Kahneman's work. And if you are someone who comes, I come from logic, I come from a more rigorous background, I want to understand exactly how logical proofs and inferences and learning is carried out from a principled way, you can check our book on Neuro-Symbolic Cognitive Reasoning. It's the kind of book that has lots of theorems and formalizations of the way that we can build neurosymbolic systems. Okay, and another point that I want to make here is that why this paper is important. In a larger technological economic sense as well, we can say that understanding the science of AI, understanding what's actually going on in AI is crucial. If you think in terms of the research that received the Nobel Economic Sciences Prize last year, this science, the Nobel Prize was assigned or was given to researchers who understood how certain scientific discoveries and developments are effectively translated into technologies that actually create economic value. So people wanted to understand in history why certain domains of science and certain research discoveries are very successful economically and others are not. And one of the key things that their 30, 40 years research identified is that you have to understand exactly how the science underlying the technology works so that it can create economic value. And we are at a moment where a lot of people say, even experts, they say, we cannot explain why AI is creating such and such results. So if you want to have an AI, not only as a scientific discipline that we all that work in the field fully understand it, but we want it to have the desired economic and technological social impact in the long run. We have to understand how AI works, right? So understanding how science works also avoids us to, not to waste valuable resources in fruitless inventions or fruitless paths that are not going to lead to future advancements that can, of course, have a positive impact in humanity. So we have to think about these consequences and these connections and these results that researchers have shown in the past, that understanding science is also key so that we have the corresponding technological and economic impact later on. So the sciences and their scientific results that were fully understood by humanity were those that later on created the biggest economic impact. And we are in a point or in a moment in AI research where everyone talks about explainability, hallucinations, interpretability, what is inside the black boxes and so on, right? So this is another point that's important. So understanding the science and technology of AI is also something that in the background, at least in my research mind or my research principles, is always underlies everything that I do. And when we developed this rail framework, we worked on it over a DAX2 seminar in Germany last year in November. One thing that we saw and that we're trying to see is that applying these principles, applying the rail framework, will offer hopefully a unified view of seemingly disparate AI systems ranging from physics-aware machine learning to systems like, for instance, Google DeepMind's Alpha Suite, the Alpha Star Suite that's allegedly in certain of these applications is a neurosymbolic systems. Also in causal learning, that's very important to understand. We still have not, reached the point where we can understand causality in its fullest sense in science. And also two augmented large language models, where I mentioned we augment the language models or the Gen AI systems and tools with a theorem prover or other symbolic mechanism. And more importantly, and as we say in the paper, using the neurosymbolic rail principles can be seen as evaluation standard or design standard for AI that will allow the software engineers or the AI engineers to make better informed and more principled decisions about the design. And more importantly, even more important or equally important than to the design is the deployment of production level AI systems. So these principles, I believe, can be a great contribution to AI engineering or AI software engineering. Right, so here is the paper, here's the draft paper, the Rail Principles of Neuro-Symbolic AI is going to come out very soon. I believe there is some version already preprint on the web. And also, if you want to understand a little bit more about Neuro-Symbolic AI, we have this perspectives paper that has been published in 2023, and that where explain where the field has come from and where is it going, under our perspectives. So, another thing that we mentioned in the paper, why we need neuro-symbolic AI approaches, even after 4 years now, after ChatGPT, time flies, we have the persistent problem of hallucinations and the lack of explainability, right? So industrial AI pipelines, they are still typically ad hoc and task specific. They are built fast, and they are fast to build, allegedly today, with all these tools that we have to generate and create code. But they come with no formal guarantees overall, right? We don't understand their behavior, why error is propagating, and they have, they offer some opaque, some very fuzzy ways of showing how the reasoning, and I quote, reasoning between quotes, works in these systems. So Neuro-Symbolic AI aims to close this gap by embedding then sound symbolic rules, sound symbolic inference rules or deduction rules, as we've been working, into the learning systems. And they are organized around 4 design principles. The systems ideally you want to build are organized around these 4 principles. The principles are reasoning, assurances, interfacing, and learning. Reasoning is about how inference moves between or from implicit pattern completion to explicit formal symbolic reason. This is a spectrum. If you think in terms of, okay, is a pattern recognition system a reasoning system? In the end, if you only implement some image or image processing or some pattern recognition classification, statistical classification mechanism, or whatever algorithm you have in your toolbox, that's more, that's an implicit or explicit pattern completion or pattern recognition sometimes. And the other, let's say, end of the spectrum, you have fully symbolic, fully formal logical reasoning, obeying restrictedly to the rules of proof systems, logical proof systems that must be, sound, complete, compact, and have to have other properties of logical systems. So reasoning is also happening in a spectrum in today's AI system. The question of assurances is also very important. Even from the, I would say, the early 60s, the quest in software engineering for guarantees that the system would behave correctly always has been important in software development, and now in AI development, as AI is guiding or is probably leading or contributing to most of the developments that we have in the software industry. The other point, the other principle that's very important is the principle of interfacing, how knowledge and how the explanations flow between humans and the system in both directions, right? From the system to humans and vice versa, in the interface that, of course, we are always going to have with the AI systems. And finally, the principle of learning. If we're building a neuro-symbolic system, the learning, the machine learning component is key here. How much of the system behavior comes from data, right? Data-intensive learning, machine learning that we have, versus systems that we have some injected structure background knowledge that can be, over a knowledge graph or over a logical theory and other things in between. So when we read this paper, when you find this paper then, hopefully published very soon, what we define here is a spectrum of the Rail principles for neuro-symbolic AI. Each principle exists on a qualitative spectrum, as we say. We can define later metrics, of course. I'm pretty sure there will be people developing metrics to quantify where the systems can be positioned in this spectrum. And the principles exist in a spectrum. Just to give an example, the intermediate positions here say, when you think in terms of reasoning, as I mentioned, the first dimension here, the first dimension of this principle spectrum, we can start, let's say, from one end of the spectrum into implicit pattern reasoning recognition to some structural neural reasoning. In the middle, we have some neuro-symbolic blend in the way, for instance, that when we develop specific architectures that implement symbolic reasoning. And in the other end of the spectrum, we have formal logical reasoning in a purely symbolic way with very rigorous logical formalizations of the inference rules, soundness and completeness results, and decidability, and so on, right? The same way, we can think of the other journeys are in the spectrum for assurances, for interfacing, for the learning. For instance, we can have continual neurosymbolic learning in the learning spectrum that goes up to a spectrum where we consider data-only learning up to an extreme where we don't even have learning at all. We are just using some statistical tools to develop our systems. And of course, this spectrum allows us to think about how the systems can be designed. Am I designing a system that depends a lot on symbolic data, symbolic structures, structured knowledge? Or am I designing a system that's purely pattern recognition? And where neurosymbolic AI systems are going to be situated here so that I can understand how to best design, how I can best develop, and how can I best deploy and maintain this kind of system that I am by principle designing and building, thinking in this characteristics that hopefully, safer systems are going to be built upon. So in terms of the reasoning dimension, we can expand how this spectrum from implicit patterns go to formal logic. We can think in terms of reasoning, where reasoning chains, right? We have inference steps that in reasoning, we have inference steps if we are building a proof, if you have ever built a proof, we start from certain premises and hypotheses, and then you have rules of inference that you draw your conclusions. Of course, you have other forms of reasoning that can be abductive reasoning. Abductive reasoning is a very sophisticated way of defining the search and the quest for explanations of what we observe in the world. Brilliant scientists use abductive reasoning to explain certain phenomena. And this is the kind of reasoning that machine learning systems and AI systems in general are still not good at. Abductive reasoning is a more sophisticated way of thinking about reasoning and defining and explaining certain discoveries that we have in science. So, and this reasoning axis, or this reasoning spectrum, spans from very implicit pattern completion, like what we do in LLMs, where we actually don't know exactly how it's working. Of course, we know the transformers architecture and so on, but from a reasoning perspective, we have no guarantees that this kind of inference is always going to work. We will not hallucinate, for instance. And on the other end of the spectrum, we have formal logical reasoning, like a logician develops, like a formal logician, a mathematical logician, or a computer science logician develop, where you have the sound inference in classical or non-classical logics with verifiable step. Every single step of inference is verifiable in formal logic, whereas in the other end of the domain, we have, the emergent latent reasoning by similarity, for instance, LLMs chain of thought. So the thing here that we have to think is that under this spectrum, I have to try and position my system, the design of the system, with respect to the reasoning principle, in a way that I'm going to offer guarantees, right? So that the user of the system or the deployment of the system will show that the system is behaving in the way that I have designed the system. And in between here, I have the neuro-symbolic blend. Where does neuro-symbolic comes here? Where do I have the neuro-symbolic system blend, the neuro-symbolic with no hyphen, fully integrated? And we have some tools that are being developed these days, like DeepRoblog, that's based on inductive logic programming, and then probabilistic inductive logic programming with a learning component, right? And we have also the logic tensor networks, logic neural networks that mix implicit and explicit inference within this system. Why do I say implicit? When they are implicit, when they implement exactly or try to implement the inference rules that we see in logical systems. I say that they're more, implicit when they're using other ways of designing the inference mechanisms, such as those based on the loss function, that I'm pretty sure there will be talks explaining how they work. The other point, the other principle that is important here is the assurance principles, because assurances in software engineering, it's not a new thing, but they are the guarantees, or they provide the guarantee that a system, is going to be safe, will perform according to the expectations of the designers and, of course, the users, and it's going to be reliable, right? We can have systems or models that are unconstrained to guarantees that are baked into or built into the architecture. And in one end of the spectrum, I have systems that are verified by design. For instance, in this kind of system, the requirements or the rules are baked or constructed directly into the network architecture of the system. I go into the spectrum, for instance, as if we take here in the middle, I have some mixed constraints where some shield layers assign zero probability to outputs that would violate a constraint. For instance, I can have an output grammar that's checking it. And in the other end of the spectrum, I have this external validation where the neural components trained with no requirements, they're not trained with AI requirements, and the correctness must be checked outside the system, right? You can think of systems where I coupled to a Gen AI system an external verifier, an external formal methods to verify and validate certain properties. And balancing these assurances against the scalability of the system also is a very important research problem, how I connect these components in a way that the neuro-symbolic system is effective and it delivers efficiently the results that we expect from this system. The other point here, the other principle that we also define in the paper or in the research is the principle of interfacing. And we define interfacing as the shared representation that lets users or humans, but we could extend this definition beyond humans, like systems interacting with themselves, but that's another discussion, that lets humans and systems exchange domain knowledge and explanations in both directions, right? In the direction from and to the human, right? So we can have, in one end of the spectrum, pure embedding system, so the high dimensional latent representations that we have today, they capture some statistical structure, but they are very hard to inspect and understand what's going on. In the middle, we have some mixed representations where we have, for instance, graphs and causal models that support intervention while they remain compatible with sub-symbolic systems, right? We can explain, and there is some interesting work that connects causal models to neural models and build these bridges between causality models and a neural learning system. And the other end, the interfacing is purely symbolic, where you have a formal knowledge representation with a very well-established formal semantics. It's very expressive, but it's usually hand-specified. Those who have specified formal semantics know how hard it can be under certain constraints. So interfacing is typically also, as we have observed, often asymmetric. Guiding a system is relatively easy, but getting an explanation back out of the system, right, is a very hard problem. So much so that today you have explainability conferences, being organized. And finally, the learning principle, of course, the machine learning component. It can also range in a spectrum that goes from continuous learning to non-learning. What does that mean? Non-learning means that predefined symbolic is used as is, relying on knowledge engineering, knowledge representation, rather than any statistical model or any learning mechanism. In the middle, we have systems that are what we call knowledge guided, that typically, let's say, neuro-symbolic systems where we have structured knowledge, where the shapes are learned, that shapes the representations, for instance, via knowledge graphs or other mechanisms, and they improve generalization and improve data efficiency, data characterization, ontological understanding, and so on, right? And the other end, we have continuous neurosymbolic learning, where learning continues over time as the knowledge evolves through feedback loops, such as reinforcement learning. So the learning mechanism is a key component, is a continuous component of the learning mechanism that runs autonomously in the system. And most industrial systems They combine data-only components with certain pockets of knowledge-guided learning. And today we see a lot of growth, for instance, in the use of knowledge graphs and graph representation mechanisms for certain structure information and representation of knowledge in neurosymbolic systems. Okay, just to give some examples where these domains or these principles, the rail principles, show up today in certain systems. So the idea here and the understanding that we had is that rail is not just a design ideal. Some major areas of AI and some major AI systems, they already, in a way or another, they use or they are put or classified somewhere in all of the 4 rail dimensions. For instance, when we think in terms of the domain of knowledge discovery, embedding-based link prediction in graph-based models versus rule learning over knowledge graphs, right? These systems, they are already systems that can be seen or can be classified or organized or taxonomized under the rail classifications, as you can see. The other thing that, the other application that I think Vaishak already mentioned is what we call tool-augmented LLMs, language models that write code, call APIs, and reason step by step with external tool. For instance, the React framework or the React proposal, it goes along this direction. Other kind of system or other major areas of AI, because they have received a lot of investments, is the area that is called a neuro-guided search. For instance, DeepMind's AlphaFamily, AlphaGo, AlphaFold, AlphaProof, and so on. They pair neuro-learning and sometimes reinforcement learning with symbolic game and proof trees. This is clearly a neurosymbolic system, and clearly the principles of reasoning assurances and reasoning and learning and interfacing as well, they appear in certain positions of that spectrum. Causal learning is another example that is also classifiable or taxonomized under the rail principles, because causal graphs, they are in between statistical estimation and formal do calculus reasoning. For instance, if you look at Jude Pearl, Joe Halpern, and that school of thought in terms of causality, right? They are in between statistical probabilistic estimation and formal reasoning. They also can be positioned into that dimensions or into that spectrum of the rail principles. And also other new domains that we have had a look in terms of the physical aware of physical informed neural network or physical aware machine learning, physical laws, symmetries, conservation principles. They can act as symbolic knowledge for scientific machine learning. So physics-informed machine learning or physics-informed neural networks, they're also positioned in a way where symbolic knowledge and symbolic information, mathematical information, is being integrated in a neurosymbolic way. And we can see where the reasoning components and the assurances that are provided by building an architecture that obey physical laws and physical principles can offer to users. And of course, in industrial architectures of AI systems, the modular production pipelines, they already combine learned components with symbolic glue code, right? So those who have developed using the typical methodologies of software engineering, MLOps, DevOps, and so on, they can see these principles being adopted. Okay, in terms of a case study here, not only an example, in the knowledge discovery domain, embedded-based methods, they are, let's see, seen as having a very interesting reasoning principle being adopted. If they are embedded-based, the reason is implicit, right? We reason over vector similarities and distances in the embedding space or in the latent space, right? So this is kind of more opaque reasoning, but this can be observed. In a rule-based systems, the reasoning is more explicit, right? We apply the symbolic rules discovered from the graph, right? We are not working in the latent space or not working at the embedding level. We're working explicitly at the symbolic rule level in terms of understanding what the graph is representing. In terms of assurances, the same way, we can think that this embedded-based knowledge discovery, we can work on think in terms of the relaxed constraints, and the loss minimization, they raises likelihood, but gives no guarantees. So that's another thing, when we think in terms of the loss function-based approach to Neuro-Symbolic AI, we have to think about this perspective, of course. And in terms of assurances, rule-based systems, we can move forward, or we can move toward verified constraints via ex-post ontology checks. For instance, can do type checks. We can check in terms of cardinality of the sets that you are doing the inference, and so on. The things are more clear from a mathematical and logical perspective. In terms of the interfacing principle in knowledge discovery, this is weakly structured, right? The embeddings are hard for humans to inspect directly. Our interaction with the system is harder to be explained to us and understood by us if we're working at the embeddings level or the latent space, right? In terms of fully symbolic systems, of course, graphs, rules, and new relations, they remain human readable because they have been, they have a history of formalization in computational logic, mathematical logic, where things are very clear by design, by construction. They are explainable, and the semantic is very well defined by design. And finally, in knowledge discovery, under this rail perspective, as an example, the learning can be from an embedded-based perspective, data only or knowledge guided when we are using informed sampling strategies, right? Or when it's rule-based, the learning can be bidirectional, right? In the sense that rules are learned from the graph, and then they applied back to it so that we can draw inferences within the graph. So the two categories, they are almost, when we think in terms of embedded-based approaches, and we think in terms of rule-based approaches in knowledge discovery, right, in this kind of applications, the two categories are almost opposite in the spectrum of the rail principles. Embeddings, they favor machine learning, especially, of course, if we're thinking in terms of embedding, they favor the current trends in using transformer neural networks, whereas rule learning, it favors the principles of assurances, of course, verifiability of the system, and the interfacing, right? Understanding the intricacies of the system. If we have a fully rule-based understanding of the properties of the system, is much easier for us humans than to inspect, latent space and all the complexities that come with it. And since I'm running, a little bit out of time, I believe. I'm going to accelerate a little bit, but there are other case studies in the paper that are very well explained. For instance, the two used by language models under the rail perspective. One can couple LLMs with external programs that reintroduce neurosymbolic principles in three explicit forms. For instance, in program synthesis, the LLM generates executable code from natural language specifications, natural language descriptions. The reasoning remains implicit, right? We are not expressing that via logical rules, but expressing via certain language interface that's not typically exactly formal, right? From a formal semantics perspective. But the output is explicit and testable. We can test the interaction and the code that's produced in program systems. The other dimension, the other aspects that we can consider here is tool invocation. The LLM calls an existing API or do some database queries. It gains assurances then from executing and from certain unit tests that it did not to alter. We can do that automatically as well. So we use tools for doing that. And finally, we can think about this agent-based perspective to AI that is pretty much perhaps the most discussed topic in AI that we have these days, right? Where reasoning and actions of the system, they interleave, are interleaved and intertwined. The model deliberates, acts, observes the results, and self-refines the next step, right? So LLMs can be seen as a kind of, or LLM-based AI or Gen AI tools that we have seen today. We see this interleaving or intertwining between reasoning and actions. And this can be used also to avoid hallucinations in a way or another. But we are not totally error-free or hallucination-free in this kind of approach, because the systems, they are loosely coupled, right? When we use LLMs coupled with certain tools, by definition, they were defined and they were designed, they were produced under different design principles. So we still, we still have errors that can remain and can still, of course, cascade and compose in history as the system is being deployed in time, right? So a few more systems or more examples that we have seen in terms of our research about systems that use the rail principles, right? For instance, if we think in terms of neuro-guided search as the alpha star family from Alphabet, we have stronger formal assurances, right? When we adopt that approach, when we observe that approach that Google or DeepMind has used, right? AlphaGo's implicit rules, right? Implicit game rules that were based on search trees that were Monte Carlo tree search, as we saw about 10 years ago, maybe, right? And versus the alpha proof, lean verified proofs, which of course is more rigorous. Even this kind of approach is under a spectrum of, let's say, assurances and reasoning in the rail spectrum. In terms of physics-aware machine learning, for instance, we can think that symmetries, conservation laws, and other physical laws, if we are building systems under the principles of physics-informed neural networks or physics-aware machine learning, or any other denomination that you have today for AI that's inspired and uses physics, the symmetries and conservation laws, they act here as symbolic knowledge, like logic does in neuro-symbolic systems, of course, giving assurance by design through equivariant and Hamiltonian architectures, for instance. And finally, in industrial architectures, building modular pipelines, ideally, we're going to have components where they are glued and composed together when they already have been, by design, built in a way that assurances are properties of the system, and then the compositionality the neuro-symbolic AI approaches offers and the rail principles by design are offering will guarantee the properties and the success of the deployment of these systems. Okay. Other families of systems, and just because we are a little bit running out of time here, we can check the recent results that Amazon and AWS is publishing about neuro-symbolic AI systems. For instance, Amazon Rufus that integrates reasoning and learning. This was even in the Wall Street Journal last year. I believe that was August last year. They even interviewed Byron Cook, who is, of course, a very well-known name in the automated reasoning community in AI. He's a VP at Amazon, and he explained how Amazon is deploying neuro-symbolic AI systems, in particular how the lean team, the team that uses the automated reasoning system to check proofs, the lean team is developing very significant contributions to have Gen AI systems, or to have lean-based reasoning checks that validates the LLM outputs against certain constraints, certain logical rules. And Amazon has reported that it has catch hallucinations with up to 99% accuracy. That's a very interesting result, industrial level result of neuro-symbolic AI that can also be framed under the rail framework here. And also the alpha geometry, where the interfacing dimension is very important, proves to be important. Why? Because the language model proposes constructions in natural language, and a symbolic deduction engine turns them into formally verified Olympiad-level proofs. You can check that again on the paper that Alphabet has published in 2024. Okay, so these are some examples of large-scale systems that can be seen under the rail framework, and also that hopefully similar systems and more sophisticated systems can be developed under these principles of the rail framework. Okay, and in conclusion, the rail framework or the rail principles, they are a design space. They are not a checklist, right? These 4 axes, they constrain how we frame a neurosymbolic architecture. For instance, as we have seen here in this talk and in the paper, reasoning spans and goes from implicit pattern matching to formal logic. And in the middle, we have something that we believe is, fully coupled or tightly coupled neurosymbolic systems, where the neural architecture implements both the learning engine and the inference rules or deduction rules or abductive principles, whatever you have it. The assurances span from external validation to built-in guarantees in the system. The interfacing between humans and users, humans and systems or AI, is two-way. It happens, the guidances go in, the explanations ideally come out, and the systems then that use the rail principles hopefully will have better explainability in the future. The same in the same path, I would say that the learning dimension, the learning principles spans from no learning to continual learning. Of course, we can have as much learning as as you wish and as is desirable when you are designing your systems. And these four axes, they are trade-offs against each other, right? The further you go from symbolic representations, you're probably moving towards a very probabilistic statistical system, data-heavy system, where you are looking more into certain information that you can extract by pattern matching or pattern recognition than information that you can, or knowledge that you can extract via a symbolic logic or symbolic reasoning or under some formal logic mechanism or any other let's say symbolic formalization. The same thing applies to assurances, right? Assurances are, varying in a spectrum again, and to provide assurances about an external observation of a large language model with, billions, trillions of parameters is much harder than to guarantee assurance by design using formal specification and rigorous requirement analysis using certain formal methods, right? So in the end, this rail principles or the rail spectrum is a qualitative map, and ideally turning rail into a practical tool for AI will also consider and take into account operational criteria and very concrete metrics that we can develop as for the research, right? So the path forward here in terms of future research, we can see, as we have seen in this talk and as we can check in the paper, several high impact systems turn out to already be neurosymbolic, maybe unwittingly, maybe unknowingly, and they can be classified and can perhaps, they can, of course, consider following the rail principles if they are not already following them. The rail defines a four-dimensional design space whose interdependent axes constrain viable neurosymbolic architectures, and mapping existing systems onto it reveals real trade-offs and synergies, as you can see in the examples that were given in the previous slides. And by visualizing these relationships, the rail principles open new design opportunities for both research and for industrial deployment. So thank you very much for this opportunity. This talk was perhaps the least technical talk I have ever given over the last couple of years, but I really enjoyed working in this paper and with the co-authors that co-wrote this over the last, I would say, 6 months that we have been working over it. So thank you very much.
Okay, great. Thanks so much, Luis. I'll just comment, I think this is a really valuable tool for us for thinking about structuring the space. So I'm really glad you guys worked on this. I think it'll be great for the field. We probably don't have time for questions, but Luis, there are a few questions if you want to jump on Discord.
Yeah.
Or we can maybe come to them during the break. But
yeah, no, good. All right,
we'll see you on Discord, perhaps.
Yeah, I like the question, especially when we think about the spectrum. What's more tightly connected, tightly coupled, loosely coupled neurosymbolic system. We can think about it. Yeah, I saw some of the questions here, and interoperability, interfacing. No, those are great questions. We can talk about it. Yeah, of course, and you can also email me. It's going to be a pleasure. Yeah, or reach out under some social network connection.
All right, very good. Thanks, Luis.
Thank you.
Okay, next we have Xiao is going to tell us.
Hello.
Hey.
Can you hear me?
Yes.
Okay.
And we're going to hear about how to improve your LLM with reasoning, improve your LLM's reasoning with symbolic AI. All right. And I think this will be of interest to a lot of people. So take it away, Xiao.
Okay, thank you. Can you see the slides? Okay. Good morning, everyone. My name is Xiao, and I'm a PhD student at Nanjing University. It's a great pleasure to join this summer school. Today, I will talk about neuro-symbolic learning of large models. This is a very broad topic, so my goal is not to give an exhaustive list of papers. Instead, I would like to give a simple map of what has changed because of large language models, what has not changed, and will symbolic methods still provide capabilities that LLM alone does not give us. I think LLMs create new opportunities in both directions. Let's begin with the basic motivation. Neural networks are very good at perception and intuitive pattern recognition. They can process images, languages, and a large amount of unstructured data. In the language of dual process theories, we often compare this to fast, intuitive system one behavior. Symbolic systems has a different strengths. They represent rules, constraints, and compositional structure explicitly. This allow exact computation and verification. We often compare this to slower and more deliberate system to reasoning. Neuro-symbolic AI tries to combine these both advantages. The interesting question is not which side wins. The interesting question is how they communicate. Okay. This question has a long history. Henry presented a well-known taxonomy in his III lecture describing several ways in which neural and symbolic components can be arranged. Other surveys organize the field according to the direction of support between the two components. For example, symbolic knowledge can regularize neural learning or transform knowledge into a neural model. Neural model can also support symbolic system by extracting symbols from raw data or by accelerating symbolic reasoning. A third family integrates both components more tightly through differentiable logic reasoning or gradient-free optimization. Today, I will mainly use this view symbolic for neural for symbolic, and neural plus symbolic. However, our neural component is now a large language model. This replacement is small, but importantly changes the design space. Okay, this brings us to the question. Large language models can produce fluent chain of thought, solve difficult mathematical problems, write programs, or interact with tools. So in 2026, do we still need symbolic methods? My answer is yes. We need it because fluent reasoning is not the same as reliable reasoning. At the same time, LLMs make symbolic systems much easier to build and use. So what new changes can LLMs bring? I'll answer the second question later. First, here is a roadmap for this tutorial. First, I will briefly discuss why LLM reasoning remains unreliable, and then summarize four changes introduced by large language models. Secondly, I will discuss symbolic methods for LLMs. We will see how symbolic system can provide training data and can augment reasoning. Third, I will discuss LLMs for symbolic methods, especially LLM-guided search. Finally, I will connect both directions in the context of neuro-symbolic agent systems that learn reusable symbolic knowledge from experience and then use this knowledge to improve further reasoning and planning. This tutorial is based in part of our EJCA survey. The paper and repo are here, provided here. Anyone who would like to read? Okay. Before answering the second question we provided earlier, let's start with the limitation of LLMs. LLMs struggle with tasks demanding exact computation and strict logic consistency. Even the most powerful models today can easily make mistakes in simple computations and comparisons without using any tools. As in this example, models cannot perfectly perform multi-digit multiplication. Here is another simple example. We ask multimodal models how many red and yellow balls appear in the image. The correct answer is 9 balls and 12 yellow balls, but different models return different counts. The model is confident the response is detailed, but the detail does not make it true. For this task, a more reliable system might use object detection or small programs that keep track of the count. In other words, the task benefits from intermediate structures. Now considered a much more realistic example from China Travel, which is our open-end benchmark for language agents in travel planning. One user may request a multi-day trip with a fixed budget, preferred cities, such as she wants to go to Beijing her budget is 50,000 yuan. A plan can sound perfectly reasonable, generated by large language models, but this plan can exceed the budget or scale during a closed attraction. We tested LLMs, and we find that the strongest language models still struggle with a combination of hard global constraint, and their final pass rate still be 0. This is exactly the place where a hybrid method become nature. Use LLM to understand the preferences, and then use search or optimization to construct a plan. As a data-driven probabilistic model, the PEC framework in place that correctness can only be guaranteed in a probabilistic approximate sense. This is why data-driven machine learning is not enough, and we still need symbolic methods. LLM still suffer from hallucinations, faithfulness, and constraint satisfaction abilities. However, LLMs also change neuro-symbolic research in a positive way. The first change is that they can help bridge the semantic gap. Classical neural networks produce continuous vectors, while symbolic systems require discrete structure representation. Converting a nature language problem into logical rules, such as program SQL, PDDO, and other formal languages used to require a dedicated semantic parser and substantial label data. LLMs can act as much more general semantic parsers. The mapping is not always correct, but it's flexible and can be prompted with examples. The second change concerns the optimization gap. Neural learning usually relies on continuous gradient-based optimization. Symbolic reasoning often relies on discrete, non-differentiable search. Historically, connecting these two optimization was difficult. LLMs introduce another adaptation mechanism that is in context learning. We can change behavior through instructions, demonstrations, or feedback expressed in language without updating the model parameters. This does not eliminate discrete search, but it provides a flexible way to transfer information between a search process and a neural model during inference. The third change is a knowledge acquisition bottleneck. Classical symbolic methods rely manual creative knowledge bases. Building and maintaining those resources is expensive. LLMs encode a broader range of world knowledge in their parameters, so they can propose candidate facts and rules. Of course, parametric knowledge is not trustworthy. A useful pattern is like let the LLM propose the symbolic procedure verify and store only when what passed the check. The fourth change is the move from isolating modules to agentic orchestration. Planners, theorem provers, LLM can serve as a unified controller. It interprets the request, select a tool, and decide what to do next. The controller must know when not to trust itself, when to call a tool, and how to validate the results. This is the agent system. These 4 changes set up the rest of the tutorial. We now turn to the first major direction, symbolic for LLMs. There are 2 broaden points. Symbolic methods can provide data, and they can also augment the LLM directly during inference. Let's see the first part. Symbolic provide data. A symbolic system can play 3 roles. First, it can be a generator, producing problems and reasoning trajectories. Second, it can be a validator, checking whether model generated data is correct. Third, it can be a mutator. It can transform a seed problem in the symbolic space to a new problem. These roles are especially useful when human annotation is very expensive. Okay. Here are some examples. For countdown task, we receive a target number, 50, a set of input numbers, and allowed arithmetic observations. A search algorithm can generate a valid reasoning path. For example, 39 plus 13 equals 52, 66 divided by 33 equals 2, 52 minus 2 equals 50. For math navigation, a shortest path algorithm can generate both for the final route and the states visiting along the way. The key advantage is that the separation comes from an executable process. We can generate many instances and know whether each step is legal and illegal, and whether the final goal is reached. But what kind of trajectories should we use for training? A common choice is to keep only the optimal solution path that produce clean examples. However, it hides the work performed by the search algorithm. The search algorithm try alternatives and they encounter dead ends and they do backtracking. Stream search and other works instead convert richer search traits into language model training data. The traits can contain exploration and recovery, not just the final pass. Empirically, model trained on such augmented traces can outperform models trained only on optimal passes. Why might this happen? An optimal pass teaches the model what success look like after all mistakes have been removed. A search trace also teaches the models how to behave when its current hypothesis is wrong. This is much closer to the situation encountered when we use LLMs. Results show that this method is better than just fine-tuning the optimal path data. This observation motivates our work. Step back to Leap Forward, which is published at FutureOfAI 2026. Our question is simple. Can we teach LLM not only to generate a good next step, but also to recognize when it should backtrack? During training, we generate trajectories containing a special backtrack token. Look at this example. The model first computed 45 minus 39 equals 6. It then take a back step, back step, and write 39 plus 6 equals 45. At this point, the trace output the backtrack token. This trait contains how to output a backtrack token when error occurs, and it is generated entirely by symbolic search. At inference time, we have 3-step expansion, backtracking, and selection. For expansion, the sample contains a backtrack token, then the system roll back and re-expand from an early state. Across the resulting candidate passes, we use the score based on negative perplexity to choose the promising reasoning trajectories. In this way, we have constructed backtrack search algorithm based on LLM. We then use successful search trajectories for self-improvement. The slower search process acts like system 2. It explores and corrects. The accept trajectories are used to improve the model by SFT, transferring some of that behavior into fast system 1 generation. Here is our experiments. Backtracking augmented training was more pragmatical and data efficient than surprise fine-tuning on optimal solution passes. The broader lesson is that negative experience can become useful separation when value and recovery are represented explicitly. This idea extends beyond arithmetic puzzles. Any domains with executable transition system and detectable dead ends can potentially produce our algorithm. The second role is validation. Suppose the LLM generate mathematical proof. Instead of treating the text as ground truth, we send it to a serial prover, PDDO planner, or constraint solver. The symbolic tool filters invalid samples or return feedback that can be used for repair. This is widely used because validation is much more cheaper than generation. It might be hard to discover a proof, but once a formal proof is proposed, the proof checker can verify it deterministically. VC search is one example of using verification to connect less well-defined mathematical problems with well-defined formal checks. The third role is mutation. Synthetic data is important for fine-tuning, but heuristic mutation in natural language or just using another language model can easily change the answer, but introduce contradictions. A safer strategy is to transfer the problem into a symbolic language, sample transformations in the formal space, and then translate the result back into later language. The formal representation make invariants explicit, so the system can control both diversity and validity. Neuro-Symbolic DG for math reasoning is our work published on NeuroPiece 2024. It demonstrates this pipeline with SMT lib language. The method converts mathematical problems into formal constraints, perform mutation in the symbolic space, and use LLM to verbalize new formal instances. Solver checks preserve validity, while projected Markov chain Monte-Carlo methods supports diverse sampling. The construct data then improves the base model through SFT. We can notice the division of label. The symbolic layer protects semantics. The language model provides flexible translation and nature expression. NSAI is another work. It extends the same principle to multimodal geometry. It uses domain-specific language for plane geometry, generate a sample formal geometry configuration, and painter render rents the corresponding image. A reasoning and verification pipeline combining with a multimodal language model with a symbolic server constructs and checks solution passes. In the reported experiment, training with only 4,000 generated samples improved performances over the base model, and the experts manually evaluate the data quality. The quality is very high. The takeaway from this entire section is that symbolic data pipelines do more than create more tokens. They give us reasoning structures and informative value traces. We now move from data to inference time augmentation. The core idea is simple. When an LLM is not well suited to a sub-problem, it should call an external symbolic component that is maybe a solver, program, interpreter, tools, or search algorithms. The first category is solver augmented reasoning. The LLM translates Latin language into a formal representation, such as first order logic, SMT solver, or Prolog. A symbolic solver then derives the answer. Logic LLM is such an example. It follows this pattern for logic reasoning. SAT set LLM uses the declarative prompting to produce set of logic constraints and then evokes a satisficable solver such as Z3 to solve the problem. Relay work also generates Prolog programs for arithmetic reasoning and exploiting permutation or multiple candidate translation to reduce parsing errors. Planning provides another clear example. In blocks words, the task is to move the blocks from an initial configuration to a target configuration through a legal sequence of actions. LLMs often fail on long horizon versions because they lose trace of state or violate action preconditions. LLM plus P separates understanding from planning. The LLM generate a PDDL description of the objects, initial state, and goal. A planner such as fast downward then produce a valid plan. Again, this architecture is attractive because each component does what it is best at. The LLM handle language, while the planner handles systematic state space search. The second category is program augmented reasoning. In program added language model and program sorts, the LLM expresses the computational part of solution as code, often Python. A deterministic interpreter executes the code and returns the results. This is useful because large language models are often better at describing algorithms than a faithful carrying out every arithmetic operation in that algorithm. Binder generalizes this pattern. In parsing stage, the model maps the question and available knowledge into a program that may contain API calls. Sorry. During execution, those calls acquire external results, and a dismissive interpreter combines them to derive the answer. So the program is not only a calculator, it also an explicit compositional plan. The same idea applies beyond text. For a high resolution image, a model may miss a small object such as text on a billboarding. A system like Zyme can generate code to crop, zoom, enhance, or manipulate regions of the image before answering. The program creates an active perception process instead of relying on one forward pass. In robotics, code as policies translate latent language command into policy code. The code can process perception outputs, call control primitives, and it can recursively define missing functions. The language model supply semantic composition, and the robot runtime supplies ground execution. The third category is tool augmented reasoning. Tool formal expose how a language model can learn when and how to call external tools. Torah integrates natural language reasoning with utilization of external tools. Unlike the program source, tool augmented methods do not directly use a tool to solve to produce the final answer. Instead, the LLM decomposes the oral task and can evoke multiple tools, each responsible for a specific subtask. We can use pre-trained small machine learning. We can also use pre-trained small machine learning models at the same time, such as visual programming, which is the best paper in CVPR 2023. Each tool can be a machine learning model, such as like image classification model, object detection, and image segmentation. The first category is search augmented reasoning. A standard of generation commits to one token at a time. In practice, decoding may be gradient, sampled, or beam searched. But limitation is clear. Once the context contains a bad step, later generation is conditioned on that state. We can instead view reasoning as a tree search. A state is the current context or partial solution. Action extends that solution. The search space contains many possible reasoning sequences. Here are 4 major test time scaling search methods. This views with additional computation, we can sample multiple candidates and then score intermediate states or exploring promising branches, and we can backtrack from values. The essential question is not only how many tokens we generate, it is how we allocate computation across alternatives. In last year, we hosted a travel planning challenge in EJK, and I want to share some information we collected from this challenge. We saw many teams adopt neuro-symbolic designs. 2 representative patterns were LM plus depth first search and LM plus mixed integral neural programming, MILP. In the first pattern, the LM understands the query and then models travel planning as the next POI prediction problem, and use DFS to solve it. In the second pattern, the LLM extract preferences, entities, and constraints, then construct a mixed integral optimization problem. The optimizer find an itinerary satisfying the formal requirements and objective. Based on what we learned from this challenge, we also developed a broader discussion of trustworthy travel planning agents presenting in a workshop. The larger lesson is that reliability comes not from adding a solver anywhere in the pipeline, but from defining a clear contract between language understanding and formal optimization. So far, symbolic systems have helped LLMs. Now let's reverse the direction. How can LLMs help symbolic methods? The fundamental bottleneck of many symbolic methods is combinatorial exploration. Search and discrete optimization may need to explore large number of candidates. The search space is very large. Language model is fast and heuristic. It cannot replace exact search, but it can suggest where to look. There are three common mechanisms. First, pruning. The LM identifies branches that appear obviously unproductive. Secondly, heuristic ordering. It assigns probabilities or scores to next step, allowing the search algorithm to explore promising actions first. The third is warm starting. It generates a high quality initial solution or skeleton instead of starting from a random candidate. Alpha geometry is an example. It illustrates the collaboration in Olympic geometry. Geometric proofs often require auxiliary constructions such as adding a point or line. The number of possible constructions is very large. A language model proposes useful constructions based on learned geometry patterns, and a symbolic detection engine derives consequences and check whether the proof close. The neural component supplies a powerful prior over the search space. The symbolic component supplies sound detection. The result is stronger than plain the symbolic search and more reliable than unconstrained language model proof. For example, if we are given some another example, if we are given some observation, can we figure out Newton's law? Symbolic regression propose a really challenge. Given observed data, we want to discover mathematical expression that fits the data while remaining interpretable and generatable. In an idealized example, could the system rediscover physical law from measurements? The space of possible expression is extremely large. Traditional systems often use evolution search. However, such as this algorithm LMSR, use an LM to propose equation skeletons based on the problem context and historical candidates. Classical optimization then fits the numerical parameters and deterministic evaluation function ensure quality. The model contributes structural hypotheses. Numerical optimization and evaluation ground those hypotheses in data. After you evolve extends the idea with an evolutional coding agent, a popular of programs LM-based mutation. Use symbolic to evaluation and fitness-based selection. The importance design principle is the same. LMs are excellent proposer engine, but they should not be the sole judges of their own proposals. Whenever the target it can be executed or measured, an external evaluator can anchor open-end generation to an objective. This gives us a reusable findings, generate with the model, evaluate symbolically, select and repeat. We have now discussed symbolic methods for LMs and LMs for symbolic search. Agent bring both directions together. in a loop, especially Neuro-Symbolic agent. Agent is a system that can perceive its environment, performing reasoning, planning, and take actions to interact with the environment. In many current systems, the LM acts as a controller or brain. It receives operations through sensors or software interfaces and produces actions through tools. This framing introduces a valuable source of information, experience. The agent can observe not only examples written by human, but also the consequences of its own decisions. However, current agent often stores experience as raw text or trajectories. A long memory may contain useful information, but it's hard to retrieve or generation and reuse. Saving every trajectory does not automatically create knowledge. A Neuro-Symbolic agent tries to convert experience into explicit abstraction. Rules, constraints, skills, programs, or other such as causal relations. For example, instead of remembering 10 separate failed episodes, the agent may learn one rule describing the preconditions that all 10 violated. The goal is to move from episodic memory towards symbolic and reusable memory. We can organize Neuro-Symbolic agent process into 4 stages. First, exploration generates trajectories through interaction. Second, induction extracts symbolic rules or reusable skills from those trajectory. Third, a knowledge base stores abstraction, perhaps as code, logic rules, skills, or constraints. Fourth, guidance use the stored knowledge to improve later reasoning and planning. The loop then repeats. New behavior creates new evidence. New evidence refines the symbolic memory. Voyager provides an early example in Minecraft. The agent explored an open-end environment and built a library of executable skills. Instead of storing only complete episodes, it writes and refines code for behavior that can be reused in more complex tasks. Skills become building blocks. Once a basic capability is reliable, the agent can compose it into a higher level behavior. This is a Neuro-Symbolic in a practical sense. The LM propose and organize behavior, while code provide explicit executable representation of learned skills. WALE 2 make the knowledge learning loop more explicit. The system compares predict and actual trajectories, learns new symbolic knowledge from mistakes, translates symbolic knowledge to executable code, and prunes the rule set through a maximal coverage formalization. This addresses 2 problems at once. Predictions errors create target learning signals, and symbolic pruning prevents memory from growing into a reductant set. Okay, the final example use groups of sampled outputs. In each round, the most generated multiple candidates, the model generated multiple candidates. It then compares outcomes within the group, reflects on why some candidates are better than the others, and distills semantic knowledge that guides the next round without conventional parameter update. This is different from the traditional GRPO algorithm, just to update the knowledge. Across these agent examples, the importance is not the transcript, it is the abstraction learned from these transcripts. Okay, let me conclude with 4 points. First, symbolic methods remain important in the era of large models because probabilistic generation does not by itself guarantee exact consistency or constraint satisfaction. Second, symbolic system can improve LMs by generating structured training data, validating outputs, creating controlled mutations, and augmented reasoning with solvers, programs, tools, and such. So the direction also runs the other way. LLMs can accelerate a symbolic system by proposing candidates, guiding search, pruning branches, and providing warm starts. First, agents create a closed loop. They can learn rules and skills from trajectories, store them as explicit knowledge, and use that knowledge to guide future behavior. If you remember one design principle from this tutorial, I suggest this one. Use large models for semantic flexibility and propose generation. Use symbolic components for structure, execution, and verification. The most promising system will not ask one component to imitate the other. They will define a clear interface that allow each component to contribute its real strength. Thank you very much. Thank you very much for your attention. Okay.
All right. Thank you, Xiao very nice. Let me give Xiao special thanks for this being a terrible time for him, middle of the night. So, thank you for staying up late. So, and to all of our participants in China and the Far East and all those places where you're up at night. So, all right, we have a question. In a neurosymbolic architecture, how would the structure of a symbolic planner look, I guess, or be incorporated, and how would its interaction, what would be its interaction with the neural layer?
Where can I see the question?
In the private chat.
Okay. The first question?
Yeah.
Okay. Let me see.
About a symbolic planner.
I think it's very hard to let some symbolic structures in the neural layers. Maybe we can add some recursive layers in the large language models, such as looped language models, because the recursion is very important in symbolic way. I think so.
Mm-hmm. And when you talk about agents, are you incorporating planning in those kinds of agents?
I think current coding agents is a neurosymbolic agent, because I think current agent can interact with the terminal or some other softwares. So I think so what's the question?
When you're talking about neurosymbolic agents, or your general patterns for how to do an agent in a neurosymbolic way, do you incorporate planning, symbolic planning?
I think agent itself is neurosymbolic, because the tools is the symbolic system. So just with interactions, the whole system behave as neurosymbolic way. Yeah.
Okay. And you showed us some nice patterns where people have found success. What would you say, having looked at the landscape, what would you say is strikes you as an area where people should do more work? What's a good area for future work for the community, in your opinion?
Thank you very much.
Well, what you have suggestions for where people should do more research?
I think we should focus more on neuro-symbolic agent, such as coding agent. I think this is future.
Okay. Very good. Okay. Well, thank you so much, Xiao Wen. Everybody check out his work at Nanjing University and the work of his colleagues and many of the papers that he showed us. Lots of good projects there. All right, thanks. We'll let you get some sleep, Xiao Wen.
Thank you.
All right, take care.
Mm.
Okay, so now we have a break for 30 minutes. So you can get some lunch or whatever meal is appropriate for you right now. And I'll just mention, I've told we just passed 10,000 subscribers on YouTube. So thank you, making us the largest Neuro-Symbolic channel. All right, so see you all in about 30 minutes at 12:15 Eastern. Okay, welcome back, everyone. Now we have the start of a very special couple of blocks highlighting Neuro-Symbolic AI in industry. Do we have Cristina here? Yes. Hey, Cristina, long time no see.
Hello.
All right. So first up, we're going to see something on what's actually a hot topic now, AI for science, and some really strong work that Cristina's done. And this is not quite product. The rest of the industry talks will actually be about products. This is a little bit more forward-looking. And with that, take it away, Cristina.
Thank you, Alex, for the introduction. Also, thank you for inviting me to present at this nice workshop. Do you see my slide correctly? I believe so, right? Please let me know if it's something wrong. Okay, so my presentation for today is about the application of scientific discovery for Neuro-Symbolic AI. And this was done in collaboration with different people, but I will mention them later. Okay, so when we started to work in this field, we started to look at the basics. So we started to look at the classic scientific method, and we ask ourselves if, like, the usual way to discover science still fits its purpose. So, but we start to see more and more evidence that the classic method start to reach its limits. For example, here on the right, we can see a graph where we can see that the research outcomes over the years start to decrease, while the number of researchers is increasing over time. So this was published in the American Economic Review in 2020. And but this also supported by other laws, for example, Moore's law for microchip density. So that says that in the 70s, only few researchers were needed to double the density of chips in the frame of 2 years. So, but now to have the same rate of like this doubling the density of chips requires 20 more times the number of researchers. So what does this mean is that the ideas are harder to find, and but we don't know exactly why. So there are some hypotheses. For example, if we picked maybe all the low-hanging fruits of scientific discovery, that means all the long-hanging fruits is kind of what scientists can do just using their own brain, right? Or maybe science is incentivizing the wrong things, like people start to maybe optimize for obtaining grants rather than doing meaningful research. So, but what all of this is telling us is that we need perhaps something different going forward. So, but let's take a look at what their current AI approaches for scientific discovery. And I categorize this in 4 main branches, but this doesn't have to, it doesn't mean that it's a comprehensive review. It's just my take on this. So the first one is data-driven discovery. So we're all familiar with machine learning techniques that require a lot of data and minimal or no prior knowledge. And there are many examples of this, like neural surrogates or symbolic regression methods and so on. But what are the limitations of this? The limitation is that often have just plausible new discovery rather than physical meaningful ones. Another category is this what I call knowledge-aware models, and this I think were mentioned in some of the talk before are, for example, physics-informed neural networks, physics-inspired neural networks, or equivariant models, and so on. So what are these models doing is that they try to integrate some constraints or some symmetry inside the model's architecture themselves. But what are the limitations is that the architecture are like hard-coded for a specific problem, so they're not really general. And often this network impose only soft constraints and not hard constraints. Another category that I want to mention because it's also relevant for this workshop is neuro-symbolic or hybrid approaches. So this one tried to bridge the kind of the gap between symbolic reasoning and pattern recognition that is more for more familiar in the machine learning areas. So this method could be logic-guided learning, inductive logic programming, program synthesis. Also, this was mentioned in some of the talk before. But what are the limitations? Of course, also here we have a limitation, like usually scalability or imposition only of soft constraints instead of hard constraints and others. Finally, I would just want to mention generative AI, because this has been increasingly more popular, especially in the last few years. And here we can see some methods like the usual LLM or VLMs, but also agentic framework that were also mentioned before in the previous talk. So here what we are exploiting is the whole human knowledge, because this model has been trained on massive amount of data, and this data contains books, contains many things that basically encapsulate the whole human knowledge. So we can use this, exploit this knowledge that this method learned to propose new laws. But also this method, they have their own limitation, for example, hallucination, lack of scientific rigor, and so on. An example of this, we tried to recover Kepler's law of planetary motion with the ChatGPT. So in this case, we use GPT-5, was one of the first that came out some time ago. And we tried to rediscover the Kepler's law for planetary motion over the dataset for binary stars. So basically you have two stars that are orbiting each other, and you want to compute the period of the star around the other star. And we gave some data points in the prompt, and we renamed the variables, because if you use the usual names like M1 and 2, is this indicative that M1 maybe is the mass and M2 maybe is the second mass, and P is the orbital period, and so on. So we renamed the variable, and we asked ChatGPT to produce a formula that explains this data. So as you can see, ChatGPT tried different heuristic to come up with some different functional forms. It did not do a comprehensive search, of course, but in the end, the last formula that kind of proposed as a solution is not the right one. So it's this one, while the desired formula is the second one that I'm pointing at. So we also tried other models. The funniest one was Gemini, because Gemini first tried to generate some functional form, but at some point it gave up, and it looked online and found this data set and just basically cheated by saying, this is Kepler. So that was like a fun fact about this experiment. But so with this example, we can see that AI is starting to begin to transform scientific discovery in general, because now with AI, you can, like in the example before, generate many hypotheses. The problem is that we can generate a huge amount of hypotheses in a very fast, and a different type of scale than what we are used to. So we are basically flooding this, like the verification component. So we have this sort of verification bottleneck. And the verification is needed to identify like what are these genuine scientific discovery. So we're trying to distinguish between some plausible correlations over the data with like actual scientific laws. And this is very hard to do. So the research question now is, how can we automatically bridge the gap between canonical knowledge, so the knowledge we know already is true about the environment we're observing, and AI-driven discoveries. So, but the real question is then, can we evolve beyond the classic scientific method that it seems reach its limits? So then what we want to do is to discover scientifically meaningful formulas. So not just data approximations, but we want something that is consistent with the background theory. So the set of axioms that we know are true about the environment we are observing. And what is our desiderata? So first, that these hypotheses are verifiable, so we can verify if the background knowledge, so the axioms that we know are true about the environment, we can formally derive from the axioms this new hypothesis. And in the case we cannot verify directly, so actual like a formal proof, we also would like to have a distance. So we want to know how far is our hypothesis to the set of axioms that we know are true about the environment. So this is our desiderata. So then we start to look again at how the scientific discovery method works. And here is a very high level schematic. So with two different interpretations. So we can start like a scientist to manually hypothesize, like generate hypotheses from data and then manually verify it on theory to discover a new formula. Or we can start with the manual hypothesis from theory and then testing it on data and so on. And these are the kind of the most common interpretation of what a classic scientific method is. And then we have a machine learning that just look at the data and look for patterns and then generate new formulas in that way. So, but what we try to do is to have some alternatives. So, and I will just briefly talk about all of them in the rest of the talk. And the first one is what we call AI Descartes. So this method works in two phases. So the first one is we generate hypotheses from data. And then the second phase, we test this hypothesis on theory. And then we do this in a loop until we are satisfied with the hypothesis that we generated. The second one, we thought, okay, but these are two independent components. Is there a way to do this in one unique component? So do these two things at the same time. And this is why we developed this second framework called AI Hilbert. And this framework generates hypotheses directly from data and theory at the same time. And the last one that I also want to mention briefly is AI Neuter. So this one we say, okay, suppose we use the other two methods or any other methods like AI Descartes, AI Hilbert, but there are many more like PySR, AI Feynman, and so on. So suppose we generate a new formula in that way, and we have a partial knowledge about the environment. So we have a background theory, so a set of axioms, but it's not complete. Can we discover new theory that way? So this is the question that Neuter is answering. Okay, so now I'll start to describe each of these three frameworks. I will just try to give you a brief overview of them, and then for the details, you can, of course, are free to take a look at the paper, or you can contact me, ask me any question you want. Okay, so AI Descartes. AI Descartes, as I mentioned before, takes some data, generate some hypotheses from data, and then test this hypothesis on theory to generate a new formula. And this work was done in collaboration with my former colleague at IBM Research. Okay, so just a schematic of the framework. We take the data, we take the theory. From the data, we give the data in input to the symbolic discovery component. The symbolic discovery component will output an ordered list of hypotheses, and these are ordered based on the error on the data. We feed this list of hypotheses to the reasoning component that, together to a background theory, will re-rank this list of hypotheses. So now this re-ranked version has both error on the data and error on the theory into consideration. And then we can pick the first one, for example, and this formula then we can use for predictions. Okay, so but let's look at how these two components, so the symbolic discovery component and the reasoning component works. So the first one is symbolic regression. We use symbolic regression to generate hypotheses from the set of numerical observation that we have. So we formulate this problem as an optimization problem that very high level, it minimizes the error on the data, what we call fidelity. And then also has tried to minimize the complexity. So complexity is because I want to generate the simplest formula that explains a phenomenon, because we're trying to not overfit on the data, of course. And then also based to a grammar, which is defined over a set of primitives. For example, which operator I want to use. Like I want just to use the plus and minus, or I also want to use the division or other operators. And also based to some invariances and some other nonlinear numerical expressions. Okay, so, and we use then symbolic regression to generate a set of hypotheses. And if we are lucky, we can derive one of these hypotheses from the background theory. So, and how we do that? First, we try for direct derivability. So direct derivability, we have our functional form, and we want to try to prove, like formally, like with a theorem prover, for example, that our set of axioms that describe the environment directly implies our formula. But this is not always possible, and especially if we generate hypotheses from data, we might have, as you can see on the left, some numerical constant. And these numerical constants are likely not to be exact. So this will invalidate the proof. So then we introduce this notion of existential derivability to tackle this problem of noisy numerical constant. So what we simply do is just substitute this constant with numerical constant with actual logical constant, and then try to prove the equivalent formulation with this constant. So what does this mean? It means that the functional form is correct, but the constant might be off. So this is still valuable information, but in some noisy scenario, we probably not even be able to use this existential derivability. But what we can do is to try to understand how far the formula is to the derivable one. So this is a notion of distance of a formula generated from data to background theory, to a set of axioms. And how we compute this is trying to find the distance between two functions. So one, like the blue one that you can see here in the screen, is the formula that we derive from, the green one is the one we derive from data. While the blue one is the one that is implicitly defined by the axiom set, by the background theory. And we can compute this distance with a theorem prover, for example, in three ways. So the first one is looking at the data point. So like in the Kepler example that we saw before, suppose we have a star and some planets orbiting the star. So this data point will be the different planet, so the numerical observation of the planet. So we check how far are these two to functional forms on these data points. The second one is that we try to generalize between these data points. For example, we say, okay, we take our planet and we take Mars. Suppose you have a planet that has a mass in between the two masses. So what happened to the distance of these two formulas in that scenario? So this is the kind of interpretation of this error. And the last one is we say, okay, let's extend these intervals. So in the case of the planets, we take for example, the biggest one in the solar system, Jupiter, and we say, okay, what happened to the distance between these two formula if we take a planet that is much bigger than Jupiter? And based on this, what we call reasoning error, then we can have a different ranking of the hypotheses that we generated from data. So here we can have some results for Kepler's third law of planetary motion, our running example. And we can see that we have 3 data sets. So the solar system data set, exoplanet, that means we take measurements from different star systems with their corresponding planets, and then the binary star, so systems that have 2 stars orbiting each other. And here you can see that I ranked for each data set the hypothesis that we generated with the symbolic regression based on the numerical error. But then if we look also at the reasoning error, we can select which one approximates the formula better on this particular data set. For example, for the first one is the first one, so minimize both numerical error and reasoning error. For the second data set, similarly, these 2 things are in line with each other. But if we look at the third one, the first formula, the one that has lowest error on the data, is very long, and if you look at it, it looks very ugly, right? So our intuition as humans is that this probably is modeling noise as well. And indeed, if you run the reasoning error, we can see that the last one, the one that has the worst numerical error, has the lowest reasoning error. And this one is preferable compared to the other one. And this one is also provable by a theorem prover from the axioms that we set in the theory. Okay, so now I give you just a quick overview of AI Descartes that has these 2 phases. First, hypothesis generation, then theory. And the second paper I want to mention is AI Hilbert. So for AI Hilbert, these 2 things are done at the same time. And this work also was done with collaboration with some of my former colleagues at IBM Research. So AI Hilbert is a little bit different from AI Descartes in the sense that we restrict to polynomials. So we want to find functional forms of this form that you can see here. And the objective is that, so we formulate this problem as a multi-objective optimization problem. And we restrict to polynomials because we want to exploit algebraic optimization techniques. And so what are the 3 objectives of this paper? First is that we want to be compatible with the background theory. So we want to minimize the error to the background theory, but at the same time, we want also to minimize the error on the data and the complexity of the formula. So the objectives are the same as for AI Descartes, but now it's a multi-objective optimization. So these 3 things are done at the same time. So for here, just briefly, data fidelity, probably everybody knows what it is. We have a set of data points and we want to minimize loss function, that we can have different alternative of loss function, but fundamentally we just want to minimize a loss function on the data. Then the second one, optimization objective, is model complexity. And model complexity over a polynomial model can mean different things. For example, the degree of the polynomial, or the, I don't know, the number of non-zero coefficient of the polynomial, and so on. And the third one is the distance to the background knowledge. So for this one, like our whole paper is based on this nice theorem. I will not go into details about this, but the only thing to take away from this is that we want to formulate our formula, and we know that with some special condition we can always do that for polynomials. The functional form can be formulated as multiplication for some over some polynomial multipliers with the known axioms. So, and this formulation is possible for a complete and consistent background theory. So we have the equality symbol here in this case. And what do we mean with complete? Complete is basically we have a set of axioms that can fully explain the phenomenon we're observing. While consistent background theory, it means that the set of axioms does not have contradiction between each other. And just to give an example of axioms, in the case of Kepler, the axiom could be conservation of energy, conservation of momentum, definition of the center of mass, for example. And this is the case of complete and consistent. So if we apply this theorem, then we can obtain a formulation. But what happened in the case of incompleteness or inconsistency, we also have a formulation for that, where we just minimize basically the distance to this formulation. And what I want to mention about this incomplete case is that, and this is what is very nice about this paper, is that since we try to minimize the error on the data and the error from the theory at the same time, we can balance these two components. So here you can see that, for example, if we have less axiom to reach completeness, if we remove more theory, we need to use more data points. So basically, each axiom has an equivalent number of data points that you need to compensate the missing axiom. So, and this is very nice to show this balance between these two components. So more axiom you have, less data you need, less axiom you have, more data you need. So this is the kind of takeaway from this, this paper. And just now, briefly, I will not take too long because I think I'm already start to run out of time. I want just to mention AI Noether. So in AI Noether, the idea here is that we want to prove formula that we extract from data, but we have complete theory that can derive this formula. But now, suppose we don't have the full theory, but we are missing some part of the theory. So then, like similarly, as what I showed before for AI Hilbert, we can use the data together to the incomplete theory to derive the right formula. So, but the role of AI Noether now is not to generate an hypothesis, but to recover the missing axiom that we removed at the beginning. So in a general scenario, you want to explain a new phenomenon. And maybe you don't know everything you're supposed to know about the phenomenon. So, but looking at the data, maybe you use a lot of data with a machine learning tool to discover the formula that explains the phenomenon. So then you can recover and discover the theory that you're missing. So this is this paper in a nutshell. So, okay, we have some assumption also for this paper. For example, we restrict to polynomials. We assume not having data directly to recover the missing axiom. And then also we assume that the missing axiom is simpler than the formula that we are trying to derive. So, but how we do this? So to do this, and here is more technical, what I'm about to say, is that we study the reducible components of the algebraic variety defined by the set of incomplete axiom and the functional form. But for the people that are not familiar with this terminology, what I want to say is that we use this nice theorem that says that we can, under certain conditions, we can always find this set of irreducible varieties. And if you look at the animation, it's kind of like our phenomenon is described by the picture in the middle. And we can try to decompose this phenomenon into simpler components. So like if you have, for example, the variety represented by x times y is equal 0. So this can be divided into simpler components, x is equal 0 and y is equal 0. So this is very nice animation to give you the kind of the underlying idea of this paper. And just to conclude, I want to show you an example of what we were able to derive with this. We took the Einstein relativistic time dilation law, and we tried to recover the effect that the speed of light is constant. And without knowing anything about light, only some other axioms and the correct consequence, we were able to recover that the speed of light is actually a constant without not knowing anything about it. So this is, I think, a pretty cool example. So I hope that with this talk, show you briefly these three approaches, I kind of inspire you to consider scientific discovery as a nice application for Neuro-Symbolic AI. And of course, also here, there are many open questions that we can ask. And so we have more questions than answers at this point. So I also want to invite you to consider this topic as a research topic, which I find very interesting. And I conclude just showing you like the resources that we have. Everything is available, the code. So if you want to try it yourself, you can take a look at our GitHub pages. Thank you.
All right. Thank you so much, Cristina. Really excellent work, published in top places. Everyone check it out. I particularly love the introduction of algebraic ideas here, and also showing how you showed this balance between data and knowledge, that knowledge allows you to use less data. It's a very important point. So unfortunately, we don't have time for questions. We're a little bit.
Sorry, I went a little bit long.
No worries. Great stuff. Thank you so much, Cristina. If you can jump on Discord if you have time, maybe you can see some questions there, or people can ping you.
Okay.
All right.
Thank you very much.
Thanks. And now, let me introduce Dimitra. So, Dimitra, thank you so much. I'm very excited about this talk. I think many people will be also excited to see hardcore industry use of Neuro-Symbolic AI. So we're going to show exciting small companies, but this is one of the giants. With that, and real product. So with that, take it away, Dimitra.
Thank you. Can you hear me? Okay, excellent. Thank you. Okay, so let me talk to you about, let me start by talking to you about automated reasoning. As many of you know, automated reasoning is the field of computer science that establishes or tries to establish assurances based on mathematical proofs about what a system or a program will do or will never do. And it is a fascinating discipline. But in order to apply it to real-world products, it typically requires deep expertise. So it requires experts to work on formalizing these problems in order to be able to be amenable to applying these types of techniques. At Amazon, we've been using automated reasoning for over a decade, and its use is growing. And many of you may wonder, why is this the case? in particular in domains like security, access control, or cryptography, the blast radius of even very small errors is so large that it actually justifies having teams of experts working on formalizing, on encoding in mathematical logic key problems in those domains. And this is how it has been typically used at Amazon Web Services over the last decade. But now, like everybody else, we are focusing on AI agents. So you see here Byron Cook at our VP at reInvent, who talks about trust in agents. As we all know, agents are writing more and more of our code. Agents will be negotiating between themselves to plan or take actions on our behalf. And when these actions have to do with financial decisions, and like you probably want to be a little bit careful about how much you can trust your agents to do the work for you. As this is happening, we cannot use traditional techniques for that are potentially based on human review to be comfortable about what agents will do or the code that agents will write. We need automated techniques. And this is a real problem. I like to quote this excerpt from a New York Times opinion essay, which basically says that it's not just a matter of AI hallucinating, which we know is a problem, but we know, like we are trying to reduce this problem gradually. It's also the case that actually AI can be tricked by malicious prompts to perform wrong actions or to make wrong decisions. So this is a real problem. And we at Amazon believe that automated reasoning can be a differentiator in this world. We believe it so much that we are actually investing in automated reasoning heavily, and we are hiring. So if any of you in the audience are looking for a job right now and are interested in working in this domain, please contact us. So let me motivate the product that I will talk to you about. So I will talk to you today about our first, actually the first Neuro-Symbolic product by a cloud provider, which is the product that I'm, like automated reasoning checks, which I will be talking about. But let me motivate it by an example from my own experiences. I like to use my own experiences. So I don't know about you, but in the last few months, I've experienced really long flight delays, which were very annoying. So what I was wondering is whether, if my flight has been delayed by 6 hours, whether I could actually spend that time in a lounge a bit more comfortably than in the normal waiting areas. And as we know, a lot of companies are introducing chatbots as a way of scaling their customer support services. So imagine I would ask a chatbot, I'm traveling economy class and my flight departs in 6 hours today. Can I access Star Alliance member lounges? And I bet that if most of you were receiving this answer by a chatbot, you would probably think it's correct. Like if you travel economy, yeah, sorry, you can't access the Star Alliance lounges under any circumstances. But the reality is that this is not a precise answer. And when we're looking at the lounge access policy of Star Alliance, what you can see is that if you are a gold customer, irrespective of which class you are traveling, you actually can access member airline lounges under a number of conditions. And as you can see, these conditions are precise and can be a little bit complex, to interpret automatically or immediately in order to produce a very precise answer. So as we know, AI is actually unbelievable. We all use it, right? It's unbelievable at taking natural language text and interpreting it and summarizing it and providing answers that look very plausible. But the truth is that in some cases, you want these answers to be really precise. And automated reasoning is actually the science of precision. But in order for it to provide the precision that we want, it doesn't operate on natural language, but it operates on logic, mathematical logic, which is an example of which you see on the right of this screen. Automated reasoning checks was launched as a guardrail in Amazon Bedrock guardrails. And the idea is that what it will do is it will block AI answers that do not comply to policies. How does it do it? So this is something that is that I want to stress. Our ambition has been to make automated reasoning accessible to everyone, which means that automated reasoning checks will apply automated reasoning without requiring our customers to know anything about automated reasoning. And it performs this by combining Neuro-AI, which is basically large language models as you know them, with automated reasoning, which is also known as symbolic AI. So I'm sure I don't need to preach to this audience since this is a Neuro-Symbolic event. But this combination of LLMs, so the way we use LLMs to the creativity of LLMs to interpret natural language, and then we use the precision of automated reasoning or symbolic AI to check these results and give feedback to LLMs in a way that makes combines the two to produce the results that we need. Our priority is to make sure that we never allow a chatbot answer to be passed as compliant when it isn't. So this is a very, very important part of our product, because a guarantee that we want to provide to our customers so that we don't lose trust, which is actually pretty hard given that we are using LLMs in the loop. In order to provide these guarantees, we are separating, our product works in two phases. The first one is where we are building the source of truth, where we are basically helping our customers without expertise formalize their natural language policies into mathematical logic that will be the source of truth for the compliance checks. And the second part is what we really care about, answer verification, which means at inference time, we want to make sure that whenever a chatbot produces an answer, we are checking that answer for compliance against the source of truth. The reason we have separated into two stages is that for most of our customers, it is valuable to take natural language policies that may have ambiguities or conflicts and spend the time to provide inputs to our tools in order to ensure that the formalization that we'll provide will capture the intent and their knowledge of the domain. So policy model creation, which is the first stage of our tool, is a neuro-symbolic tool as well. It takes natural language documents as input, and it outputs formalizations in mathematical logic. The first part that it involves is defining the vocabulary, the variables that are going to be representing the basis for the rules that we are going to be building as we are encoding the particular policy. These variables can be, for example, is Star Alliance Gold customer is a Boolean that represents whether the customer has Star Alliance Gold status. We can also have, as you see highlighted here, custom types, which are basically enumerated types. For example, here, the type of Star Alliance logo displayed at the lounge entrance. And once we are defining this vocabulary, then we are extracting the logic of the natural language by using this vocabulary. So I'll give you an example I'll go through this very quickly for those of you who may not be familiar with this type of notations. The logic, the tools that we are using are SMT notation and SMT solvers. So basically, as you can see here in natural language, you're saying that you have access under some conditions, and this in logic means basically an implication, which means that if some conditions hold, then the conclusion has Star Alliance member lounge access will be true. And then as we go through these conditions, we see that this particular rule only refers to Star Alliance Gold customers traveling in any class on a Star Alliance member airline. So we see that we are requiring now a number of conditions. So this is an and. So you need to be a Star Alliance Gold customer and so on. And then further, you can see you have additional conditions that may include a disjunction. So either your flight is departing the same day or by 5 a.m. the next day. So you're gathering these conditions in your rules, and you may even have conditions about these enumerated types. So maybe the lounge logo type has to be Star Alliance Gold logo. So you're taking, in this ideal situation, it can be almost straightforward to see the mapping between the natural language and the logic. It is not always the case, because natural language documents may have exceptions in other parts of the document and so on that you need to consolidate into your rules. But as I said earlier, our customers will never need to see the logic on the right. The way our service interacts with our customers is that it allows them to see rules in a kind of structured natural language, which is closer to something that they can understand. And as you can imagine, in many cases, the LLM, as we know, may hallucinate. It may do a pretty good job, but either because the original document has ambiguities or because it didn't do a great job, there may be, we want subject matter experts to be able to review the policies that we are creating and refine them, provide feedback. And we provide a number of techniques that are based on automated reasoning to help our customers review the policies, and neuro-symbolic approaches for refining them. And I will give you only one example here in the interest of time. One of the things we do is we use automated reasoning to generate scenarios to be reviewed by our customers, which are covering the space of behaviors of the particular policy. This is an example scenario. It says that I want you to focus on the fact that it says that, well, it is possible to have access to a Star Alliance member lounge, but not to a business class lounge. And the feedback that the expert is giving here is that it is not possible, and we allow them to just chat and give us input in natural language. So maybe they say, well, if one has access to Star Alliance member lounges, then they can also access business lounges. And actually, in the policy that was ingested, this was not the relationship between lounges was not explicit. So that was a useful input that subject matter experts had to add. And we are able to take this input and refine the policies. And once this is done, we move on to answer verification, which is what we really care about. We now have a vetted by our customers formal policy, which is the source of truth. We have a natural language conversation between a human and a chatbot. And our answer verifier is also a neuro-symbolic tool that will take these as input and produce logical findings with respect to compliance. And I'll give you more I'll explain what these findings are. But the basis of it is, can this answer be provided to the end user, or does this answer have to be reviewed or blocked? The challenge is here is that we are also using LLMs in the loop, but we cannot use humans in the loop. So we have to be fast. The latency has to be very low because this is at inference time, but we still have to be reliable because we are telling our customers, look, if we tell you something is correct, rest assured, with a very, very high probability this is correct. And we also want to provide reliable and good explanations of why a particular result is provided. So the first, you will see in my slides at the top, when you see this symbol, it means that a step is performed through LLMs. And if you see the solver symbol, it means that this is where automated reasoning is working. The first step in answer verification is that we need to take a particular conversation and capture what is the claim that is being made, what is the argument structure. And we separate this in the contextual facts and conditions under which a particular claim is made, and then the claim itself. We call them premises and claims. For example, in this conversation, the premises that are made is that, okay, someone is traveling economy class, the flight departs in 6 hours, and this is a Star Alliance flight. And the claim that is made is that this customer can access Star Alliance member lounges. And then what you need to do is to take this argument structure and map it to, take the logical structure, but map it to the vocabulary of the policy, because ultimately you're going to check for compliance by comparing a mathematical formulation of your argument to the rules that have been that are in your formal policy, in your policy as formalized, that we talked about before. So, for example, here, economy class, which was a premise, will be mapped to, to the schema, to the variables of the policy, to customer class being equal to economy class. Flight departs today in 6 hours will be mapped to is flight departing same day, and so on. So you are now translating, this informal argument into a formal logical argument that you can see on the right. This translation is performed by an LLM, and we may encounter a few issues before we decide, before we can actually make a claim about whether the particular conversation was compliant or non-compliant. The first problem that we may encounter is that the LLM cannot map a part of the conversation to the schema. So what we do in this case, we are returning to our customers the fact that a premise was untranslated. And they can use this information in order, especially as they review their policies, because they may have accidentally left out parts that are important for them to be able to check compliance against their policy. So if this is something important, they need to extend their policy to include a variable that will talk about this particular fact. The second thing, as you can imagine, is that LLMs may not be reliable in interpreting a particular conversation. So how can we provide the assurance to our customers without having a human in the loop that this is a correct translation. And we do this by formalizing each conversation with multiple LLMs. In particular, we are in our service requiring to receive translations from 3 LLMs. And you can see what I'm trying to highlight in this case is that if we were to remove from the question today, you can see that my flight departs in 6 hours now is a little bit ambiguous. Does it fly? Is it departing the same day or not? And we can see that this ambiguity is actually exposed by the translations. We are receiving 2 translations where one includes flight departing the same day, because the first LLM thought that, in 6 hours, can be translated as departing the same day, and the other ones didn't. What we then do, and I'm not going to go into the depths of this, but we are then using automated reasoning to compare with quite sophisticated techniques all these translations. So these are the 2 possible translations that we obtained, and voting for each translation to see whether they are supported by all the LLMs. And depending on the requirements of our customers, on how strict they want to be in their confidence that the translation is correct. In this case, where a translation does not receive all votes, what we will tell our customers, what the answer verifier will return is that it detected ambiguity when it was trying to translate the particular conversation, and this information can be used to review the conversation and so on. So this is something where we are not going to provide any compliance output, but we will surface the ambiguity. Once we have translations, we are entering the wonderful world of solvers. As I said, we are using SMT solvers. The basic capability that an SMT solver provides is when you answer a question about, for example, a set of rules, and you're saying, can this set of rules ever be true? It will give you an answer that says either yes, it can be true, and it will provide a witness. This is the I here, where it will give you values of the variables that make these, of all the variables in your policy that make the rules all true. Or if it cannot, it will give you a subset of the rules. This is what we call an unsat core that displays the problem, right? So this is useful because if you have, say, 1,000 rules, and the reason why you cannot satisfy these rules is 3 rules, it helps you focus on those in order to understand the problem. Answer verification asks 2 questions to a solver, whether the policy and premises and claims can be true, or the policy and premises and the negation of the claims can be true. And based on these answers, it will say your conversation is valid. Yes, there's no problem under all circumstances. You are compliant with the policy. Or invalid, you're never compliant. That's like a real problem. I'm not going to cover impossible due to I don't have enough time. Or it can say, well, under some circumstances, your claim could be possible, but you don't have all the facts that you need. So you need to be careful. You need to be more precise in your answer. We provide explanations through witnesses and unsat cores. And the explanations are used as evidence during audits, to review policies during testing, to guide chatbots into asking clarifying questions, or to help chatbots improve their answers. So our customers decide how they're going to use the feedback, the extended feedback we provide, in order to build their solutions on top of our service. For example, in this case, where someone asks, I am traveling economy class and I am not a Star Alliance Gold customer, do I have lounge access? And the answer is yes. We can see that our service will say that this is invalid, and it will provide a single rule that gives which actually captures why this is not compliant with the policy. This is where the unsat core gives you a subset of the rules. And in my original question, like original motivating question, what it will say is that it is satisfiable, it is possible. So it will give an example where with values of the variables where it is indeed the case that you are not allowed to have lounge access, but also a scenario where you are allowed to have lounge access. And by comparing the two, often either LLMs like chatbots are able to take this information and produce a follow-up question where maybe the answer could be, it depends. Do you have Star Alliance Gold status? And start a conversation with the user that asked the original question. In summary, capturing natural language policies precisely is complicated due to ambiguities or other issues in natural language. And answering them precisely is also complicated. We are striving in our service to refine it and take input from our customers to make it better and better at doing this work. You can access, you can go to Amazon website and find tutorials and blogs about automated reasoning checks and documentations. And we also have a scientific paper. I will stop here, and I don't know, hopefully we have a couple of minutes for questions. Thank you.
Yes, this is excellent, Dimitra. So first of all, congratulations on this work. First, a Neuro-Symbolic product by a hyperscaler. It's fantastic and a very important moment, I think, for Neuro-Symbolic AI as a field. So thank you for showing this to us. Everyone check out the product and give them some business. Now, we have a question. How does it work with 3 LLMs? Are these 3 different commercial LLMs or in-house LLMs?
They are commercial LLMs, and we are not using the same LLM for all the translations. We have a specific configuration that are LLMs that are available through Bedrock, and which we have found give the best results for our service. For specific customers, we are also considering fine-tuning. So this is something that may make, help address their latency issues.
I have one main question. So you listed some challenges, and but I, having worked in this kind of area, I know they're very deep challenges, actually.
Yes.
So what would you say some of them, perhaps, that you listed could be, maybe addressed with pragmatic means, like just like the speed issue of LLMs at inference time, just throw a bunch of chips at it or something. But some other ones maybe actually require research, particularly in, say, in logic itself. So what would you say are some of the deeper issues you're, butting up against?
Deeper, so the great thing about having launched a product, despite the gray hair that it has added to all of our heads, because we wanted to do this as fast as possible, is that we are getting insights from how our customers are using our products. So many customers are using the policies directly to, rather than interpreting natural language conversations, they actually query the policies directly for compliance. And this is one use case where the translation issue at inference time is not is not really an issue. The biggest challenge for us is still in formalizing policies. So to even though we are becoming increasingly better at it, to cover the nuances, so that covers a number of research challenges, not only in the types of logics that you are supporting in order to address, various types of nuances in the actual natural language, in how do you formalize large documents, and how do you structure your formalization to match and also to create a we are actually, as part of our product, trying to show a relation between the initial document and the rules that we have provided. How do you capture implicit assumptions in natural language? I think that having a completely general product is hard, and it makes sense to look at specific domains and customize the product to be better in those domains, because it's really hard to have a really for our customers to be able to ultimately, they don't want to have to do many refinements of their policies. So
Right.
to get there is a real challenge.
Okay, awesome. We're a bit past time,
Thank
but
you. Feel free to contact me, everyone who is, I can't see who is in the audience, but we're excited to get input from the community. So
yeah. We'll send you the link for our Discord if you want to jump on there and
thank you.
Mingle with our community, and I'm sure you'll find some nice recruits. So, all right, and we should chat sometime. We're working on some very fun stuff.
Absolutely, thank you.
All right, well, appreciate Dimitra, and we'll have a break now. So we'll see you all in a few minutes for our set of cool startups and small companies.
Hello.
Hey, George. Excuse me. Welcome. So I'm excited about this talk. So had when I first heard about Symbolica getting funded, thought, oh, this sounds pretty cool. So and I think you guys have some sophisticated stuff to show us. I'm probably best characterized as a fanboy of category theory, but sliding into kind of getting into category theory. So very much looking forward to it. Take it away, George.
Awesome, thanks. Can you see my screen okay? This is an important part of the process. Okay, great. Cool, so good to meet everyone in the chat. My name is George Morgan. I'm the founder and CEO of a symbolic AI research lab called Symbolica. And today I want to talk about how a program is not a string. And this is really important because we live in a world where we have all of these autoregressive large language models, and they predict token by token. And this is just really not a very efficient way to deal with highly structured objects, for instance, programs. So to motivate why we are working on what we're working on, we wanted to solve ARC. And to give some background on ARC, the objective of the puzzle, so to speak, is you're provided with a bunch of these example grids with small little colorful dots, and you're asked to figure out what the generalized pattern is. So you're provided with a test input, which you typically don't know what the right-hand side of that test input is, and you have to figure out how to perform skill acquisition where you find the pattern that is generalized amongst all the examples, apply that to the test input, and then submit what comes on the right-hand side of that test input. And this is a very, very difficult problem because it's essentially a program induction problem. You have a bunch of inputs and outputs, and you need to find a program such that running that program on the input produces the output. And there are also constraints because you have multiple examples that you need to satisfy. So that program has to be correct for all of those. And that's the only way you can solve an ARC puzzle challenge. And so if you are doing program induction, you need a programming language. You need to be able to write and express programs. And so this is why we constructed our own in-house custom programming language called Symlang. It looks a lot like Rust. Any Rust programmer would be very familiar reading this code. It has the same kinds of keywords. Also, like in Rust, it has algebraic data types. It has match semantics, parametric polymorphism. It's got first-class functions. What does separate it from Rust slightly is this set macro, which gives you the ability to leverage a built-in set type, which we'll talk about in a minute. And also this tests macro. So tests are essentially how we describe in the language what those ARC puzzle tests that we must satisfy are. So it's essentially how we describe the program induction problem to the compiler. And this works not just on ARC. You can use this to write arbitrary tiny programs like, for instance, this distinct count program or GCD here. But of course, we want to do ARC, and so we'll do some live demos. What's actually cool about this is that because this engine was written, this compiler, everything written in Rust, we actually compile it to WASM, and I'm running it right here in the browser. So all these demos will be using the actual engine. When we were actually designing this programming language, we wanted to make sure that it had enough surface to actually be able to represent a solution to any ARC problem inside of it, because you don't want to only be able to solve a subset of ARC problems. That would be obviously a handicap to the model, and you wouldn't be able to do all of the tasks. And so in thinking about like what features a programming language would need to have in order to be able to express it, we essentially kind of boiled it down to generic algebraic data types. So the ability to specify something like a tree with a type metavariable t and recursively define its constructor as an inductive family of types. And then from that, you can also build higher order combinators. So for instance, we have the ability to return a function type as this is kind of inspired by the lambda calculus. And we have lambdas as well in the language. And then from this, you can build things like list and fold, all the way up through to a higher order combinator like reverse. And then, of course, this lets you start to do arc-like things. For instance, you can mirror a grid, which is a list of a list. You can rotate a grid 180 degrees, and many more other complex operations. We've also curated a corpus of roughly 6,800 programs written in this language. Some are ARC, some are actually just generic algorithms written in this, and this is important for training later. Another really important feature of the language is the type system. So types are constraints, and the way that this language works is it uses a Hindley-Milner type system wherein we type check by unification. So for instance, if you define a function that takes a generic type metavariable t, and then you call that function with a concrete type, say an int, then the type system will unify that type metavariable t with int, and then ensure that constraint is maintained. And this is really important because it provides a lot of extra information about what a legal move is versus an illegal move. And this actually will become really important later because the type system is actually used to induce a categorical mask over the model's outputs. And when we do this, which we'll describe in detail, we can actually ensure that we never get any ill-typed predictions. And we can also ensure that when we're training the model, we never propagate gradients backwards through any improperly typed terms. So to go through a couple examples, which I can actually run live, I have a list of just some fairly simple ARC tasks. This one involves upscaling a grid by 2. When I hit run, we can see that it does indeed produce the correct answer. The screen shows us that this is indeed the solution to this ARC puzzle. You can see it's already pretty complicated, and this is kind of the story as to why we need to leverage composition and types to be able to cut down the search space of these programs dramatically. If I change the solution to, say, upscale grid 1 and hit run, then we can see that this is actually not the right answer as expected. If I change it back to 2 and hit run, then we get the right answer again. Perhaps we can do ROT 180. This is yet again another more complicated program. If I change the upscale factor down, we can see indeed it's no longer the right answer. But rather than spending a ton of time going into detail about how the exact solution to this specific puzzle works, I think you get the idea that essentially it's a programming language that's executing and has types, and we compose those functions and in well-typed ways in order to iteratively build up a solution to the ARC puzzle using these higher order combinators. So let's talk a little bit about what happens if we want to build a program induction model. So now we're talking about how do we get an AI system to learn how to write these programs? Well, if you were to feed this into Transformer, this is roughly what it would look like. You would take the program and you would serialize it out into this linear stream of tokens. And this is an actual tokenized sequence using the GPT-2 tokenizer. And as you can see, it gets chunked up over all of these arbitrary boundaries. And, there's really no rhyme or reason to how this program has been serialized. We could try to pick a different program here, and we can see here that this is a lot of tokens chunked up along a lot of different boundaries, like bracket E, I, G, H, T, like this is clearly not an optimal encoding. It's also got a bunch of white space. And if you want to train a model on this, of course, it has to learn which of these tokens actually contributes to defining your program, which don't. And this is complicated. It takes training time. It takes samples. Also, switching back to a simpler program, what if we make a mistake? So, for instance, if we made a mistake at this token, the only way to fix or edit that mistake in a normal autoregressive transformer would be to delete the entire sequence and then begin regenerating from that point forward. So this is really not a great design. This is what I mean by a string. There's actually much richer structure. And that structure actually happens to be a graph. And so I'd like to talk a little bit about the graph perspective of encoding these programs. So the object that we're working with is a typed term hypergraph. So this is not an abstract syntax tree. It's not even a normal graph. It has a couple extra properties, which we'll talk about. But the main three takeaways are that it gives us incidence, sharing, and binding. Essentially, what this enables us to do is, unlike in an AST, if you need, two of the same sub-syntax trees nested, you have to copy it. This is not true in a hypergraph. You can just create a hyperedge. If you are expressing a lambda calculus program and you want to be able to refer to a binder, you typically have to use De Bruijn notation or some other trick like this in order to solve the alpha equivalence issue. In hypergraphs, this is literally just a direct edge. So this is a much more convenient representation of how to encode a program. But a program would be nothing without the operational semantics for how you interpret it. And so we've constructed these 9 hypergraph rewriting rules, and this is a small step call by value semantics rewriting system. So a rule application is a hypergraph rewrite. We essentially find any regex that applies, of which there could be many, and we perform a substitution at that edge redirection. And critically, a really important property of this is that it obeys the Church-Rosser theorem. In other words, it's confluent. So that states that it doesn't matter what order we apply any of these 9 rules in, the system is well behaved. And this determinism is actually extremely important for the training signal that we're going to pull out of this, which comes in step 5. But before we talk about training, I'd like to talk a little bit about reduction. So this is live running. This is the actual engine performing hypergraph rewriting on this canonical program. When I hit go, we can see the rewriting system executing over this program, firing regexes, performing hyperedge replacements until we reach a normal form. And this normal form is a single scalar value 6. This is a type int, and this is the right answer. A slightly more complicated program executing looks exactly the same. We're firing regexes, but this one is going to have a slightly different outcome. It's going to be a different type. It's going to be a list. So we can see here that the list concatenation rules fire, and of course the final value is correct, a list. So that is supposed to give a visual intuition for what the actual reduction of this program looks like graphically. And an important thing to note is that this sort of multi-way system is parallel by design. So, as I mentioned earlier, we have the Church-Rosser property. So we are confluent, which means that it doesn't matter which order we fire regexes in. So if multiple regexes are able to be fired, we can fire them in parallel, and the system is still semantically correct. And this is really important because transformers are parallel processors. And what this means is that we can train the transformer to learn to fire multiple regexes in parallel. And so this multi-way step has exactly the same shape in both our programming language and its semantics, and also the transformer architecture. So before we talk about encoding, it's really important to talk about what it means for something to be the same program. So obviously, if you've written programs before, you probably are aware that if you change the name of a function, as long as you change it everywhere, that's not going to change the behavior of the program. The compiler should output the same machine code, so to speak. And so, there are various things in our language where we can change them around to our heart's content, and we don't change the operational behavior of that program. Now, there are also things that we can't change without changing the behavior of the program. For instance, one thing that we can change is the order of elements in a set. It doesn't matter what way you write the elements in a set, but it does matter what order you write the elements in a list. And this is important to consider. So what better way to show you how this works instead of just describing it is to show you it. So this is actually the engine running and actually the model executing in the browser, which is awesome. On the far left, we have the program. In the middle, we have how that program gets lowered into a IR, which is this type-termed hypergraph. We have a learned encoder, and then we have embeddings. And so these buttons down here permute aspects of the program. So for instance, down here I have a set. If I permute the elements of the set, this should not change the embeddings. If I rename a argument, it shouldn't change the embeddings. If I rename a function, it shouldn't change the embeddings. If I rename a constructor, it shouldn't change the embeddings. That makes sense. Most compilers handle this for you, but we can go a step further. This is something that an abstract syntax tree encoding cannot represent. What if we want to swap the variance of an enum? Well, it doesn't change the behavior of the program, shouldn't change our embeddings. If we want to swap the match arms, same idea. Multiplication is commutative, so we can swap the arguments to multiplication. That doesn't change our embeddings. And critically, there are certain expressions in the language that we can swap the order of, like, for instance, these two let statements. Because high is not dependent on low, we can actually just swap these expressions around and it doesn't change the behavior of the program. So if it doesn't change the behavior, it shouldn't change the embeddings. Now, we'll talk about equivariance on the next slide, but also, it's very arbitrary what ID we give to a specific vertex. It doesn't matter what ID we give to, this let vertex on the hypergraph, for instance. So we can actually reorder all of the IDs, and all this does is reorder our embeddings. This doesn't change the embeddings, it just reorders them. Similarly, we can completely shuffle the way that we index into edges, and that doesn't change the embeddings at all. It doesn't even change their order. Now, what about something that does change the meaning of the program? Well, sub is not commutative. So if we swap the arguments to sub, now all of a sudden this does change the embedding, because that is a totally different program. It has a different interpretation. So this visually demonstrates how we actually go from source code into something that's interpretable by the transformer. This is really the first step from symbolic to neural in the Neuro-Symbolic of this project. So before we go deeper into the transformer, I want to talk about how we actually do quotient out or mod out the invariances of this, and it all starts by doing this WL style hypergraph canonical color refinement. So basically, there are these stages that we go through where we essentially come up with a canonical ordering or a canonical way of writing down our graphs. So it was a little bit hard to see, but essentially we recolor the graph until we have a canonical representation of that hypergraph. And this enables us to get a canonical hash for the meaning of that program. And this is useful for hash consing inside the compiler. This is essentially the same algorithm that you would find in any graph theory library or graph theory software package like Naughty or Bliss. We do this by working with the automorphism group under which you can permute the incidence matrix of the hypergraph. So the next thing to talk about is how permutation, how attention itself is permutation equivariant. And this is really important because if as we discussed earlier, if you're building a language model, you actually want to get rid of this. It's actually a bad property. For instance, like if I write the quick brown fox jumps, brown needs to come before fox. So the language model needs to discriminate that words have orders relative to each other. If you didn't inject positional encoding, essentially what the transformer would see is just a jumble of words in a bag. It would have no idea how they relate to each other in terms of an order. Now, we just spent a bunch of time defining the fact that this is actually exactly what we want. We want the model to completely not see the difference between programs under specific reorderings, as long as they don't change the semantic meaning of the program. So I thought we could visualize that. So if I have a very, very, very small, very, very simple transformer attention head, and I permute the embedding vectors in the context window, we can see that it's equivariant with respect to that permutation. In other words, the ordering that comes out of the model is the same as the ordering that goes into the model. And I can permute this forever. This property will hold. Now, if I reset this, and if I inject a positional encoding, so this is what a normal large language model encoder would be, then as soon as I permute this, now the values in the output of the embeddings are dependent on the order that they came into the context was. So this is not what we want. And it's very convenient that we get this for free. We just don't have to inject positional encodings. So next, let's actually dive into a trained model. So this is a smaller, actually trained model, end-to-end, on learning how to solve ARC programs, which I'll explain in a moment. But let's pick a real ARC program. So this is the graphs do get pretty large, but we can kind of do a mechanistic interpretability thing here where we can see for each head what the learned attention matrix is for that head in that specific layer of the transformer. And what's very cool, let me turn it down to a smaller program, maybe a little bit larger program. We can actually see like the strength with which the actual token literals in the source code attend to each other. And this is not attention through tokens as in through a tokenizer. This is actually through the hypergraph encoding. So you can see the hyper edges lighting up as I move around this attention matrix. And I can change the layers, and I can see, how each of these, nodes relates to each other. If I click on these, I can see the attention weights between the vertex and what it's connected to in the hypergraph structurally. So this is pretty interesting. I mean, of course, it's a transformer, and it's not really particularly interpretable neurally, but it is very cool to see, that, say, specific types or constructors learn to attend to things that are also of their same type. This is the kind of thing that you can see by probing the actual learned weights, which is quite interesting. And so it's important to see that through each of these layers, essentially what we're doing is message passing. This is exactly how the model is learning, what the objective is, in this case, program induction. Essentially, like each model starts, or each embedding vector starts not enriched by its neighbors. And then as we move through the transformer, it gets increasingly enriched with more type information, more information about what its neighbors are. And critically, the information it's being enriched with comes over very predefined structure with very specific operational semantics. And another thing to note is that the type system can be thought of kind of as the positional encoding policy. And I think that this is the coolest property of this encoding scheme. A very simple example of this is that you have a set, and the order of a set doesn't really matter, as we mentioned before. So we should be able to leverage the positional invariance of the context window in order to encode a set as a type. So when you write this set type, you want to take advantage of that property. But if you write a list, you don't. And this is very naturally encoded simply by the role and position in the hypergraph. Literally as you write the types in the high-level language, it changes the way that the model is actually able to propagate information between them. So what are we actually going to train the model to do? There's a bunch of joint losses that we train the model on, but the most obvious one you can kind of think of as the pre-training step for the model is predicting what program comes next. Predicting which rewrite comes next. So that is, if you have a bunch of red X's that are firing, how do you actually perform that regex? And this is great because it has a bunch of free labels. It forces the semantics, and the model is actually learning how to do hypergraph rewriting. Carrying this forward into an architecture, it gives us an opportunity to use the engine as an oracle. So we start with a graph. This is essentially at any given time step where the model is in terms of firing regexes. We pass from symbolic to neural, run the model, then out comes a graph that the model has said, okay, a regex is here, we're going to delete this this constructor, we're going to rewire these hyperedges. The engine takes those instructions and it does the Hindley-Milner style type unification, injects the extra information if it can perform, for instance, a type unification into the graph, re-encodes the graph, and then passes it to the model again. And then we just run this in a loop over and over and over. And this is the first thing we train the model to do, is cooperate with the engine as an oracle in order to learn the reduction semantics of the language. And the second objective, obviously, is writing programs. And the way that this works is essentially a variant of discrete diffusion. So each one of these red dots is like a removed or damaged part of the program. And we incrementally damage the nodes and edges of this hypergraph, essentially until it's completely gone. And then we ask the model to reconstruct that. And so it's essentially the inverse of reduction that provides us with an explicit loss for how to perform program induction. And this is a very natural construction with this encoding. And so essentially, as I mentioned, the operational semantics of the programming language and its reduction run backwards under sort of this denoising objective, provide us with an extremely crisp way of explaining what the synthesis objective of the model is. And so we train it on the joint distribution of all of these different losses. What does this look like graphically? I can give a quick demo of that as I finish up the presentation here. So let's say we wanted to do induction on this program. We start with a hole here, and we ask the model to perform one step of denoising, which it decides to introduce an app constructor. And then we ask the model to do another step of denoising, which it then fills in another app constructor and this declarator, and then fills in the final argument here. And so this is an example of synthesis happening through the model. What about if the model gets something wrong? This happens all the time. In fact, as we mentioned earlier, it's mostly editing. Program induction is mostly editing. Well, let's say the model had predicted 3 here, which is incorrect. What we want the model to do going forward is delete the invalid part of the program. In other words, introduce a hole, and then via the next cycle through the engine, repair the program. And this is another one of the losses that we train the model on. So instead of just synthesizing programs, we also give it corrupted or bad completed programs. In other words, there's no holes. And we ask the model to identify those completed incorrect programs, insert holes again. The type system will then, and the unification engine will insert and enrich that hole with what type has to go there. And then we back it out and fill in the hole. And I think I'm just about out of time. So let me just pull this all together. We'll skip this slide. The objective here is not to do autoregression, as I've covered. It's also not to do beam search, because we want the model to learn its own search policy. That's kind of the whole point. And it's also not reinforcement learning, because we have an oracle. And critically, the environment is not an opaque environment. Programming language has very well understood semantics. So a little bit of a teaser. And the final part of the presentation here is that metamath and theorem proving actually emits the same construction. And so we can do the same kind of operation, program synthesis, in the world of theorem proving by doing conditional denoising over proofs, which are these discrete objects. Here's a visual representation of proving a metamath proof by multi-way reduction. And similarly, we can also do repair. So if a proof is incorrect, we can ask the model to do that same task that I mentioned earlier on proofs. And so the takeaway here is that proof search and program synthesis are one inverse problem. We're really interested in both of these things. Curry-Howard is a real thing, and it's really fun to be able to take advantage of it. And for those watching at home, you can pause here. Here are some of the ahas that weren't obvious to me immediately, and I would say our big takeaways. And finally, just to leave the audience, put structure in the design of your architecture. Understand which symmetries are there, understand what you can quotient out, understand what your generating presentations are, understand the dynamics of your domain, understand the semantics, and you'll be able to solve problems very efficiently. Thank you so much.
Awesome. Very impressive, George. I want to say super rich with innovation, actually all through the whole spectrum from symbolic to neural. So actually 30 minutes is difficult to do justice for all the innovations you've shown us. So maybe we'll have to have you guys come back another time as well. But personally, I love it. And a great example, actually, students out there, innovation top to bottom, and rethink all the way to how transformers work. Excellent. Also, a good showcase of Curry-Howard, as George said, which we will have a tutorial on one of these days, but very important because it links these two worlds. This goes back to like 1958 or arguably earlier, right? Programming languages and logic. And you can see the benefits of looking at it the PL way. So thank you so much, George. We're a little bit past time for questions, unfortunately, but if you want to jump on Discord, or maybe I'll ask you a super quick one.
Sure.
Do you generate a program, it's from the audience, which works for all the train and test examples? If so, how do you manage potentially different parameters between examples, like number of objects, etc.?
I guess there's no asking for clarification because it's an audience question. But I'll interpret the question as how do you generate a program if there are potentially multiple equivalent programs? And this is actually something that we actually train into the model. So, one of the things you can do when you have this infinite data generator called the compiler that understands the semantics of your programming language, you can insert a bunch of extra terms that you have proofs for the equivalence of what those terms reduce to. So you can essentially take a term that has been reduced, figure out something that would reduce to that term, and then you could insert that term into your program and then turn this into this graph. And then because we know both the bigger program and we know the smaller program, another one of the losses that we can train into the model is teach the model to recognize a big program and refactor it into a small program. And so what that biases the model to do is simultaneously identify if it's over provisioned certain parts of the code and refactor it into smaller, cleaner algorithms. And then simultaneously also, if it's generating or synthesizing a program from scratch, generate a short program, because that's obviously beneficial to its loss.
Okay, good, crisp answer. We'll have to leave it at that. Thank you so much, George. And we'll send you a Discord link if you have time to join.
Awesome. Thanks for having me. Really appreciate it.
Okay, Vincent, welcome.
Good morning, good afternoon, wherever you are.
Yes. All right. So Vincent is going to tell us more about programs. Notably, on his advisory board is Bjarne Strustrup, who knows a thing or two about programs. Creator of C++. So, okay, take it away, Vincent.
Thank you. I'll try to be quick. I have far too many slides, so apologies in advance if I'm going too fast. I'll be available offline if people have questions. Another apology is that I'm the founder of a company called Metaspex. It's also the name of the framework that we sell, so my presentation might sound a bit salesy at times. It's not my intention. My intention is more to give a testimony of the usage of ontologies, classical symbolic AI, and optionally combined with large language models. So let's jump into it. The title, as you can see, is Ontologies and Large Language Models for Online Backends. Some background on me. I used to work for an AI company that some of you may have heard of, a company called iLog. I used to work for them in the 1990s, got acquired by IBM later on. Then subsequently, I worked for a company called Amadeus, which is the leader of travel technology in the world nowadays. I joined when it was kind of a fledgling startup in charge of building all the infrastructure. And 21 years after, it turns out to be the largest business application in the world by traffic, clocking around 100,000 transactions a second on average. So I started Metaspex a few years back to resolve a number of problems that I had seen at scale, and tie all this back to my past at iLog, where I was using ontologies to build online backends. So what are we talking about? What do we do? What we do is we elevate abstraction to the maximum level we can. We call this a direct expression of ideas. I stole this actually from Bjarne Stroustrup, who uses this. It is a little bit equivalent to what AI people call nowadays the intent. So connecting directly the intent to a tool that is capable of generating complete online backends. So when I say complete, it means from the web services endpoints down to the persistence of data. The keyword here is online. You may have heard of a small company called Palantir. Palantir is, so they claim, using ontologies for analytics and a number of other use cases, a pretty big company. I call this offline backends to compare it with what we do. It's not out of contempt, it's just to find words to describe this. By offline, I mean that there is less concern on response time, less concern on the footprint when running it, less concern on scalability, vertical, horizontal, and so on, less concern on availability of the backend. So we bear all these constraints and we deliver what sometimes is called transactional backends. So here I'm calling this online backend. So it's really different from what Palantir is doing. And what I'm trying to present today is the fact that because we ended up using ontologies, we didn't start from ontologies, we end up having extraordinary characteristics of the backends that are produced using the Metaspex framework. So we owe it all to ontologies. And the etymology of Metaspex is actually meta, coming from a direct expression of idea, the intent, embracing directly the intent, and specifications, the old term to describe what intent can be when it is an artifact, a document, which in our case is very structured. So I'm going to go through what Metaspex is not, because since the 1980s and Grace Hopper, the mother of COBOL, we know that online backends are a world of convention. So very quickly, people misunderstand what Metaspex is and try to tie it back to what exists. So very quickly, I'm going to show what it is not. So it's not a business domain specific tool. On the contrary, we allow the expression of a business domain. So you start having a glimpse of why we are using ontologies and capturing knowledge as it was described in the 80s and the 90s. It's not a tool to avoid thinking. It's a tool to express a very intense thinking. When using Metaspex, it is a very trying exercise because you actually condense all your thought. It's not a code generator. We don't generate any code. We use actually a host programming language. I'm going to say which one later. That is actually having capabilities to generate code, but we are not generating code ourselves. It's not an orchestrator of services, so we are not orchestrating agents or orchestrating backends or these kind of things. We can do it, but it's not really where we shine. We take care of database persistence. It does not contain an ORM. We do not actually deal with relational databases, and I'll explain why. We do not expose pure REST web services, and we do not use GraphQL. We think that these are doing kind of shortcuts. You can use GraphQL if you want on top of what we do, but we do not use it ourselves. You can describe REST web services, but you can describe as well very sophisticated web services with extremely complex business logic without actually any real limit. The most important point on this page is probably that we don't use the web ontology language, OWL. We don't use the other emanation of the semantic web or the Web3 from Tim Berners-Lee, the resource description framework schema. We think that, and I'm going to make enemies while saying this, but I'm going to say it nevertheless, we think that these are fringe applications of ontologies, and I'm going to show you why we think that ontologies are much wider than this. It does not use or require the use of natural language or large language models, but at the end of my presentation, I will explain why large language models can be useful, and it's not an all or nothing solution. You can actually re-engineer an entire legacy application and do it by parts, because we embrace the microservices architecture. So it's an innovative approach. I might as well say that it is a contrarian approach to backend engineering. It is truly uncompromised because we look at all the very heavy constraints that are set on online backends. And what we do is specification as code. So it means that the intent is expressed using code. It's not natural language, as I said earlier. And there is a kind of Cambrian explosion of concepts, which is due to the usage of ontologies. And all this is not without a learning curve. So I don't want to overpromise here. Metaspex is 300,000 lines of quite difficult to write code. So there are lots and lots of tools within the tool. There is a foundation ontology, very classical concept. And we have appliances to do very specific tasks, which do not require any kind of programming. So let me jump, and it's here that it's going to sound salesy, and again, I apologize for this. I'm going to jump to an event, an example that we call event. We did this for a customer. The solution is, the source code of the solution is completely available on GitHub. You find the link at the bottom of this page. And it is a public and private event management application backend. It's open to the public. It's a B2C application. It contains map multidimensional search and user messaging. It's very feature-rich, contains almost 300 web services. 74 were fully custom web services, 217 from the Metaspex Foundation ontology. And here you are not going to believe me, but it took 2 weeks and a half for developing this application. It's extremely small. And maybe to make you believe me, it's the time it takes to express the intent, and just the intent. People who like, I don't know, Claude Code would compare this to prompting. So it's very structured prompting. Although we do not use Claude Code and we use a structured input, this is what it takes. So there is no real implementation of the specification. The specification is actually automatically compiled. The result of the backend is a binary which is 23 megabytes, and it is even loaded only once in the RAM of the machine where it is running. You can run it in multiple machines, but once it is sitting in one machine, it's actually loaded only once in the operating system. And 23 megabytes is comparable to a single HTML modern page containing images. So it is really, really small, close to 300 web services into 23 megabytes. Again, this is due to ontologies, and I'm going to explain why. The response time is most of the time millisecond level, including the database. So it means that you can run a backend somewhere on the planet and have users on the opposite side of the planet. Even if you add network lag, response time is totally instantaneous. And also because it is very quick response time, user engagement is very high because everything feels extremely fast. The solution ran 3 years continuously with 3,000 users, never had a restart, not a single crash, not a single memory leak. And before I explain this, we do not use garbage collectors. And to perform this, it needed only a single core in AWS. Could have been run on multiple cores on the same machine or multiple machines, but the customer didn't need more than this. And there are almost no third-party dependencies. So some characteristic of this application, again, you can read the source code. It's a true specification. There is no query language, SQL, and so on in the code. There is no database API whatsoever. There is no network API, and I'm going to explain why. There is no manual memory management. There is no garbage collection. And we ensure that there are lots of cycles. People who are familiar with memory management techniques have heard about reference counting. Reference counting has a big problem. It does not tolerate cycles, at least not as is. And we allow cycles. So it's really an original algorithm that we use, which is a byproduct of using ontologies. And there is no explicit handling of JSON. So how does it work? You write a bunch of files. This is code. So there are brackets, curly braces, and these kind of things, semicolons, and so on. You put this straight into GCC or Clang. We support both. It produces a highly dense binary, which is technically called a module. And that module is just dropped inside a web server such as either Nginx or Apache. And then you're in business. And that machine where you're running this can be a Docker image on your laptop or natively on your laptop or a machine in the cloud. This backend starts listening to web services calls, perform the calculation of business logic, any kind of business logic comparable to anything you find in modern backends out in the cloud, and it performs persistence in one or several databases. Here, I'm going to tie back to my past being doing math extensively, and it's the first time I present a slide like this. I'm going to try to give a proof that, given all the constraints that I set, there are not two ways to do Metaspex. There are probably more than one, and probably more. But I'm going to try to hint at the fact that we didn't have many choices. We need the highest possible level of abstraction for data modeling. So we thought that we needed to unlearn the way it was done traditionally in online backends, and we needed to replace database schemas with knowledge engineering, which is a much more powerful way to embrace data structures. And when you start thinking about knowledge engineering, domain-specific stuff, you think about symbolic AI ontologies. So this is where actually ontologies came into play. It's a consequence of our goals. It's not the start. It's not us saying, oh, we are going to grab ontologies and see what kind of problems we are going to resolve with them. We could have invented a new programming language. We think it is really futile these times. Programming languages are so sophisticated and contain millions of lines of code that just doing this is super complex. So we thought it was futile, and we prefer to have a host programming language in which we express abstraction, very powerful abstractions that allow to express ontologies and everything we need. So thinking about embracing ontologies, it clearly means abstraction, very high-level abstraction, and it means that they need to be layered. And when you layer abstraction, you can layer 1, 2, 3, but very quickly you get something which used to be called the curse of abstraction, which means that every time you're using a little bit of performance, and this is growing exponentially. So when you really aim at having something extremely high level, to the level of a specification, you end up having a system that is not really usable and that you cannot deploy on the field. So there is a solution to this. It's called zero overhead abstraction, and there are at this moment only two prominent programming languages supporting this, C++ and Rust. There are tinier programming languages doing this. but the audience for this is really too small for us to consider. We also need inheritance, because when you look at the definition of ontologies, you quickly see the word discourse being used. So when you hear discourse, you think about language and abstract syntax trees and these kind of things. And the best way to do this is through inheritance, which means that Rust not having inheritance or not doing inheritance very, very easily, Rust is eliminated and we are left with C++ only. I was saying that we are contrarian, and here you realize why we are, because C++ is used in very large-scale shops. Google is using C++ extensively. It's the #1 programming language at Google. You find C++ in all the big online backends. You don't find it in the smaller ones. It's something which is essentially captured by Java. As we need also to avoid the impedance problem, because we are aiming at extreme performance, it means that we need to drop database schemas. So we need to drop as well relational databases, and we need to opt for something which is very mainstream, which is the JSON native databases. We could have used a Bigtable from Google, which is a slightly different thing and not necessarily JSON native, but the biggest market share, the databases that use JSON are the most common. So we support MongoDB, Couchbase, CouchDB, but we do not support relational databases, which is also very contrarian. The ontologies, as we see them, are a unification of different methods, and I'm going to come back to this. So ontologies, if you care to look at Wikipedia, here are 3 extracts of Wikipedia article. You see that on the top left, the definition of ontology from a philosophical standpoint. It's actually almost IT. It was very natural for AI to embrace ontologies for knowledge acquisition, because you already found in philosophy almost exactly the terminology that we needed. Bottom left, you see the definition for information science, and you see appearing the word discourse, which is very misleading and open to interpretation. The semantic web, for instance, has decided to interpret this as information interchange, which is not really the initial idea in philosophy, and not really the initial ideas of ontologies when we are using them in symbolic AI. So that's what we are doing. This is why we are not doing the semantic web interpretation, and we have our own. By the way, you were kind enough to mention that Bjarne Stroustrup is in our team, is our technology advisor. This is a quote from Bjarne Stroustrup, and when you read it, you find exactly the same words as we found in the philosophy definition of ontology. And the reason for this is not because he took inspiration from ontologies. I don't think he did. I don't want to speak for him. But the reason is he had very high aspirations of C++ becoming a way to express directly ideas. And that is the same idea as ontologies in AI, since they were embraced. So let's see code, because you're probably impatient and tired of hearing me speaking. This is an example of a type in a Metaspex ontology. So this is something that could appear in a CRM backend, customer relationship backend. So this is a contact. The beginning is pure C++. As soon as you see public root, it means that this type inherits from a type which is coming from the Metaspex framework. It says that any object instance of a contact are at the top of a document. You see the use of macro and some little strings that are used for information interchange or persistence in MongoDB or Couchbase or CouchDB. And then you see the data that are typical in ontologies. We use a construct called slot that we provide in the Metaspex framework. All terminology from ontologies used to be the terminology to describe atomic attributes. So here we have 3 atomic attributes, and we have a relationship. This relationship is also a construct offered in the Metaspex framework. It's a own, and this own is actually establishing a relationship between 2 independent objects, independently allocated, that participate in the same document. Of course, we have a ton of tools. I'm listing a few here. So we have root, we have slot, we have own. I need to mention that we have links. So this is equivalent to URLs that establish relationships from a document to another, from anywhere in a document to anywhere in a document, or between two objects in the same document. And this is really very similar to a URL. And of course, we have more complex relationships, composite relationships like lists, vectors, and so on. We offer as well semantic attributes. Some of you may remember Don Knuth's proposal to calculate semantics over an abstract syntax tree. So that is exactly what we are using. We implement incremental reevaluation of this. If you modify your document, semantic attributes are reevaluated. And these attributes can be structured. We call them translates. And this translates, the value of a translate can be a document. And on this document, you can have other attributes or translate and so on without any limit in terms of layers. So it's quite powerful in terms of description. I give you a few examples of behaviors. It's really a tiny bit, but just to make you realize what we do with an ontology. All the roots of documents are automatically granted a universal unique ID, and also metadata, the creation timestamp, the last saved timestamp, and quite a few others. When you modify the value of a slot, so you simply write first name equals, or in the address example, zip code of the address equals something different. Even if you do it on an object which is deep inside a document, it triggers automatically that the save of the entire document at the end of a web service, or when you call explicitly a commit function. So it's extremely frugal. It is extremely small in terms of specification. You express only what you intend to do, and the system is actually managing behind all the intricacies to make it run fast within 1 millisecond, typically, of real-time response time. When you cut a sub-document away from its overall document, all the external links are which were pointing at the sub-document are automatically cut. And this is part of the referential integrity process that we implement. And when there are strong links, then actions are propagated to the origins of these relationships, the objects, and transitively until there is nothing to maintain any longer, and the referential integrity is respected. This is a typical code to describe a web service. This is a Lambda. You see contact retrieve. This is the actual name of the web service endpoint. Here we connect to a database, which is a logical name, hx2a. It is described in the configuration file, so you don't need to recompile to support, to move from, let's say, MongoDB to Couchbase. You just change the configuration file, and suddenly everything is actually saved in Couchbase. And we have, I'm not going to give too many details on this, but this is extremely compact. It needs a learning curve, obviously, but you express only and exactly what you intend to do. And the C++ compiler is actually taking care of collapsing all these zero overhead abstractions to have a very dense binary that runs very fast. The fact that we use ontologies allows us to do something which is almost a first. You can reuse backend entire ontologies. It means that you can capitalize on libraries of domain-specific types, bits and pieces of or entire ontologies to build new applications faster. And you can, of course, with Metaspex, do web services integration, which means calling a backend from a Metaspex backend, any other backend, even non-Metaspex. But you can as well do integration at ontology level, meaning point at the user type, which is in the foundation ontology, from any of your types, and just grab that user type, which is in our already ready-made with all the bells and whistles of what users can do, and build a new application with this. This compounds with the natural productivity that you obtain when you are writing directly a specification and not implementing anything. And of course, From this referential integrity, and I'm not going to get too many details, it's a theorem actually, we are able to destroy objects immediately when they are not used, just like reference counting, but we allow cycles as well. And all this without any explicit use of destroying objects in the code. So now, how does it tie to LLMs? There are a number of hurdles with LLMs around producing code. Lots of people use Claude Code, for instance. I did a deep dive on this, posted a very popular article on LinkedIn on how Claude Code works. And it's quite obvious that sometimes long-forgotten obstacles exist. First, Henry Rice's theorem, which is, I know I botched it here because I didn't have too much time to describe it into details, and it's a very abstract theorem, but essentially it says that a piece of software, like an LLM, can only deduce trivial properties when reading another piece of source code, which is a very big hurdle. The lack of accuracy of large language models is also a huge problem, which means that what you get is not necessarily what you wanted, but there was a lot of interpretation. It was open to interpretation when you formulated your prompt. So you only get what it is capable of delivering, but not necessarily what you wanted. A more important article, which is setting a number of limits, is the one done by Peter Noor in 1985, and he was saying that software is theory building. So it is, in modern terms, we would say that it is about building abstractions. And when I say abstractions, I'm not talking about something really fancy, talking about putting code inside functions, putting code inside types, putting code inside methods, you name it, things that a developer does, most developers do all day long. And Peter Noor was explaining that the crux of software engineering is this. It's not to align lines of code. It is actually this. And I'm going to hide behind Gary Marcus here. Neural networks face a difficulty around identifying proper abstractions. More and more people are realizing this. There is a testimony from an employee at OpenAI, and he posted maybe a week ago that there is this huge challenge that nobody is talking about, which is that it's very difficult for an LLM to invent new valuable abstractions. They can do factorization, but factorization is not abstraction. Factorization is mechanical. Abstraction is a spark of genius, if you want, inventing a new theory. Yet, all this being said, LLMs today virtually possess all domain knowledge. They even possess, we are going to see it, Metaspex programming knowledge. And this was a very big surprise for us. So we think that there is an opportunity for LLMs and highly abstracted frameworks to collaborate together. I'm just going to show you a few slides, and I will finish here because I'm sure people are in disbelief or in
super quick, Vincent. We're past time.
Okay, so super quick. I'm just going to enroll a few things, showing an interaction with Gemini. So you can do it yourself, gemini.google.com. You go there, you ask Gemini whether it knows about Metaspex, how to formulate Metaspex ontologies, and so on. It will say yes, and then you can ask it to formulate entire Metaspex ontologies. Here is a code which is produced by Gemini as a general purpose LLM. And this is extremely shocking because we didn't expect it. We didn't think that it was possible. And at the same time, we discovered that Gemini had read all our documents, all our white papers, and so on, and was capable of doing this, which is kind of magical. LLMs possess the intent. They do not have to invent new abstractions. They just need to translate this into ontologies that Metaspex cannot solve. And I'm going to stop here. We have a lot of online resources if you are interested in digging further. 100 pages of white papers, and we are open to discussing with anybody who wants to try the product.
All right, thank you so much, Vincent. Let me just say one reason I thought this was, an interesting thing for everyone to see is, as Vincent said, a bit of a contrarian view, but in particular, really pushing object-oriented representation. And, the higher levels of OOP are quite powerful. And I think many people forget about metaprogramming and so on that you can do in OOP. So in particular, there's a kind of an ancient tension between object-oriented modeling, essentially knowledge representation, and a relational style knowledge representation. So, somewhat embodied by the ORM.
Correct.
Thing that was hot for a while, but never fully resolved, actually. So that relationship, in fact, we're starting to, in the Institute, maybe write something about that. So I think this is this is a direction more people should look at. And we heard two very different takes just in the last two talks, taking a programming language view and leveraging the power that's actually essentially the logical and knowledge representation power that's inherent in programming languages. So thank you, Vincent. Check out Vincent's work. And we'll connect again in some way, Vincent.
Thank you for having me.
All right, take care. All right, Sajjad, welcome.
Thank you so much, Alex.
Yeah. So now, and Parisa, who's part of our extended family, who many of you have seen speak in our and is on our education committee, is an advisor to Docs, if I'm saying it right. So,
yes.
Pleased to have you. Take it away.
Thank you so much. Can I go ahead and present? Can you see my screen? Hello, can you see my screen, please?
Yes, we can see it.
Okay, thank you. Yep. Great. Yes, I think as expected, there should be a lot of conversations around combining LLMs with other symbolic methods. And at DAX, we are pursuing one such approach, which is really how do we combine LLMs with knowledge graphs and other augmented tooling like reasoning, verification, mathematics, even code generation if required, to deliver on the promise of reliable, trustworthy AI. I'm sure everyone has spoken so far about, everyone here must be aware of the challenges of LLMs and their inability occasionally to give you correct answers. So that's really what we are after. And so one of the key pillars of this pursuit is to provide justified answers, right? And the title of my talk is Justification Without Truth. What I mean by that is, while you can source, the ground truth from source repositories, enterprise systems of records, but there's no way of knowing what's represented there is actually the truth. We can't guarantee that. But what we can certainly guarantee is making sure that you represent that knowledge in, with the highest fidelity that we can, by combining that knowledge with the fluency and the language skills of an LLM. So that brings us to the next topic of today, which is really how do we separate knowledge from language processing in a compositional architecture? We made an effort, and I think we've been modestly successful. I'm here to share with you some experiences from that effort. And this was an interesting, as we are processing some, I think, ERP records, we found that even though we accurately, correctly, deterministically computed the correct answer, our own verifier rejected the answer. And that was quite surprising. And then this talk is all about why was that answer rejected and what can we do about it? In order to understand this, we really have to go back to the definition of knowledge itself. We scoured a bunch of resources. As we said, we wanted to separate language processing from knowledge processing and then recombine both the streams to provide a fluent, correct, reliable answer. So the definition of knowledge, what is knowledge? How is it processed? What is the smallest unit of knowledge? There's not a lot of information as we scoured the landscape. In fact, we looked at one of the leading lights of information theory, Claude Shannon, and he speaks about how efficiently you can transfer information over a noisy channel. But really, what is the core, the smallest nugget of knowledge? How is it stored? How is it processed? How do you verify that? Was a little less, visible to us as we scout the net. But we could go back to, some of the great civilizations, the Greek civilization, and we found something that Plato had experimented with. And Plato, in his Theaetetus, pardon my pronunciations, has gone through multiple iterations of trying to define what is knowledge. At one point in time, it was a rhetorical question, right? Is it something that you actually believe? Well, the answer is maybe yes. It's probably partially yes. Then in their next iteration of their rhetorical debate, they said, does it necessarily have to be true? Even though you believe in it, does it have to be true? And the answer again was yes. But that's where we thought Plato stopped. Where we wanted to go beyond what Plato said was really, can you even justify it? How do you provide provenance, proof, and context, especially as you build computational knowledge processing systems? We thought that was an essential ingredient. So computational justification, it actually takes three forms, which is provenance. Where did this come from? Where did this knowledge come from? And is that a reliable source? The next question is, how was this established? Is there proof? And lastly, under what conditions, under what context? So that's really, the sum and substance of our knowledge processing capability in providing these kinds of justifications. So for us, then the unit of computational knowledge is the Greek alphabet kappa. And kappa is defined as a function of, the triples. I think the earlier speaker spoke about triples, ontologies and knowledge graphs and triples. Anything that you represent could potentially be broken down into subject, object, and predicate. So that alone is not enough. That claim alone is not enough. At what point in time was that claim relevant? At what point in time was that knowledge relevant? So the temporal aspect represented by the Greek letter tau is also important. And lastly, the status. So where did that, was it a factual piece of knowledge? Was it derived knowledge? Was it projected knowledge? Was it reported by somebody that you're just narrating? Was it derived from counterfactuals? So we represent that by the Greek alphabet mu. So for us, kappa is a function of all of these, capabilities. Of course, the bottom line is it is underwritten by the justification structure. For us, justification, as I previously described, was a function of provenance, proof, and context. And as I've given an example at the bottom of the screen here in the finance domain. I think what we're trying to model is a customer who owes about $12,450. So actually that claim can be deconstructed into the subject, which is a customer, the predicate that he has an outstanding balance, and 12,450 is the amount the customer actually owes. Now this is true as long as you also have the temporal aspect. When was this true? And on what basis do we make this claim that it is true? And that is, the factual information, right? And that comes from systems of record, like, a database, a particular row in the database and such. So this is our definition of a unit of computational knowledge. And with that established, then we went on to build higher level architecture to process knowledge. And as the earlier speaker also alluded, there are two classes of systems. There are the foundationalist systems and the coherentist systems, which is the foundationalist systems where you can trace the knowledge crisis, source code, whatever that artifact might be. And in this case, justification is inspectable. You can actually inspect the knowledge. You can repair that knowledge. But it also suffers from a weakness. The weakness is omission. There's no way of knowing unless you closely inspect that you might be missing some information. So missing of that information, the omission, is a weakness of these kinds of systems. On the other hand, you have these coherentist systems on neural networks, in our case, LLMs. They provide justification by coherence, right? I mean, they run inferences, and those inferences are expected to be in coherence with the training data that they were trained on. There's no explicit provenance here. You can't really trace it back to the data where the claims surfaced from, especially during inference time. And the failure mode here is commission, right? You might occasionally get a hallucination, errors, and these are plausible inferences. So our argument is you actually need both. It's not one or the other, but you actually need both these systems. And the next discussion is around language versus knowledge. So there are actually two key positions here. One is conflation. In an LLM, you actually conflate language and knowledge, and you expect the LLM to provide you an accurate, reliable, fluent, understandable answer. But those kinds of systems suffer by the errors of commission. And what we argue for is dissociation. Really, can you split language and knowledge and process them separately and find a way to recombine them? And that's what our architecture is based on. So we split the query into a language stream and into a knowledge stream and process them separately. And we find a way to compose the answer from the processing performed by each of these two streams. So we call that the composition. And in compose our answers. And of course, it's a very fine-grained things. And the finer the grain of interaction between the two systems, the more nuanced the answers that you might end up being able to provide. So what compositionality means really here is the sum of the parts, right? You break down a claim by the constituent parts. It's not just the constituent parts and the nuggets or factoids of information they represent, but really how do you compose them into a fluent answer? And therefore, we believe that compositionality is an essential ingredient. And at the frontiers of research, there's a lot going on in this space. And we're more than happy to learn from the great speakers here, as well as from our coach and guide, Parisa. And in the area of knowledge processing, of course, you need factual nuggets of information, and that can be retrieved from knowledge graphs, from keywords, vector search, uh, image descriptions, database channels, database rows and columns, source code, all of.
All right, we seem to have a connection problem at on the speaker's end. Hopefully that will get fixed. Sajjad, can you hear us? All right, let's give it a few moments.
Into a sentence as illustrated here. And what
we lost you for maybe a full minute at least.
Okay, sorry.
Rewind for a bit. Yep.
Yeah, I'll rewind.
Mm-hmm.
So as I said at the start of the discussion, even though we computed the correct answer, our verifier flagged it as an incorrect answer. And here is the reason why. We use deterministic mathematical computation was necessary. Thing we knew for the, and despite providing all the information the LLM needed to produce the final answer, it still hallucinated. It still added extra content here, which was not part of our input, data sources. So really what that taught us was you had to break down these answers claim by claim and then verify each claim against the data sources we have. And then every time we found a claim to be incorrect or invalid or improperly represented, to be able to go back and to regenerate, recreate, surgically rewrite, or even regenerate their entire answer. And now we're learning the art of building deterministic natural language generating engines to mitigate the risk of an LLM not generating. While we'll use an LLM for the first pass at creating a fluent answer, but rectifying that answer requires more deterministic natural language processing. So that's something that we're working on right now. So the diagnosis is hallucination is non-compositional. So you really need to work on that. So we built a technology, we call it ClaimGuard. ClaimGuard does this claim by claim verification, regeneration, rewrite, and it loops around until we get the answer right. So that really is meant to satisfy the justified part of the answer. And here are some different metaphors for performing these repairs, whether to delete, to hedge the answer, weaken the assertions, provide some attributions, surgically rewrite, regenerate the entire answer. A lot of different metaphors we use to actually providing accurate answers. And the result of all of this was that when we ran the facts benchmark, which is a Google DeepMind open source factuality benchmark, to our surprise, we scored 77.7. that put us at the top of the leaderboard. But then when we spoke to the owners of the benchmark, Kaggle and Google and DeepMind, they found it hard to put us on the leaderboard simply because we are not an LLM. We are a system built around the LLM, and that leaderboard was designed largely for LLMs. But this is, a illustration of our efforts in providing trustworthy, reliable, correct answers. So the frontier is, how do you really compose these answers, and the granularity with which we compose. We're working at the claim level right now. We want to get down to a final level of granularity, which is a span level, right? Span is a small nugget of information within a wider claim. So yes, the question is, can this span level, claim verification be performed? And the answer is, for us, we do believe it to be true. It is possible, but we haven't done that yet, so we don't know the answer. We're hopeful that we should get there. So with that, I'll end this, presentation. Take any questions if there are any.
Okay, great. Personally, I think that's unfair. You weren't allowed to be on the leaderboard, but or maybe there should be a overall leaderboard.
Yeah.
But that's impressive and promising. So you mentioned I guess that is your. I want to ask, what's the next step, and what's involved in taking it to the span level?
Yes, I think it requires span level, fine-grained graph navigation, and that navigation has also got to be guided by a reasoning engine. So as I said, we haven't built our reasoners quite yet, and now we're in the early stages of experimenting with some of the reasoning tools. And so we do want to improve our reasoning capabilities at the span level. And in terms of our benchmark, I also want to add, while we use an LLM, we use the lowest cost, cheapest LLMs that cost less than 1/10 of the cost of the frontier models. So with a lower cost model, we are able to beat the frontier lab models. So as part of our FACS benchmark, that was then in the month of January. We have made significant more progress now, and we should be running those benchmarks once more. And we're also exploring more other benchmarks like the legal benchmark. We certainly want to tackle the legal benchmark and similar other domain-specific benchmarks. And this capability allows us to build domain-specific superintelligence, where that intelligence can be relied on and can be made trustworthy for industrial applications. So that's really where we are. So as part of our next release planning, those are the areas we're working on. We're working on e-commerce. We wanted to start with a lower risk rather than dive headlong into banking, financial services, or into health and life sciences. We want to start with lower risk, domain applications, and then amp up the risk as we develop more and more confidence in the systems that we're building.
Very nice. You mentioned that compositionality, I interpret as a sort of signal that you have a hallucination, non-compositionality.
Yeah.
But but presumably it's not the only, or I mean, it's not definitive, or maybe it's one way. If you're non-compositional, it's probably a hallucination, but there can be other hallucinations. I mean, compositional hallucinations. So what do you find is the strength of that signal?
Yeah, right now, we're trying to make it as deterministic as possible. So as I said, we break it down by claim, and now we want to get down to the span. And then we want to also be able to reason with these nuggets of knowledge. What is that smallest nugget of knowledge? And can we assert all of those components of a nugget of knowledge, right? As I said here in this equation, each nugget of knowledge can be defined as this, equation here. We are not 100% right now with all of the capabilities needed to process a unit of information. There's another vector of research. There are times when we might not even have all the information we need to provide accurate answers. That's another area. So yes, I think in terms of our ability to detect hallucinations, I know when we ran the facts benchmark, let me say this, despite providing all the information the LLM needs to generate the final answer, as I said, it could err on the side of voice, right? It might use active voice versus passive voice. It could err in terms of tense. It could err in terms of the temporality. So the diversity of errors that it might produce, it's really hard to get our minds around that. We're doing our best right now to detect each and every one of those kinds of signals. And that comes through simply running enormous quantities of benchmarks, enormous quantities of tests, and uncovering different ways in which a fluent answer could be potentially wrong.
Okay, very nice. Well, thank you so much, Sajjad. Check out docs, everyone, and all of our company so far. All right, next up, thanks. We have Peng from Orbi, which was acquired by Unifor. This is evidence that you can start a neurosymbolic company and get acquired. So, all right, welcome, Peng. Tell us about Orbi.
All right, thank you, Alex, for the introduction. Hi, everyone, my name is Peng. I'm currently a Senior Director of AI Science at Unifor since the acquisition of Orbi AI. Today, I'm going to share with you some of the latest research we're working on at Unifor on neurosymbolic agents and how this is potentially enabling efficient and robust enterprise adoption for AI agents and AI agents that are capable of solving really complex problems. A little bit background about Orbi and Unifor. Orbi started as a AI automation technology company that worked a lot on automating graphical user interface actions. And since the acquisition at Unifor, we have been really on the mission of enabling customers to leverage latest and greatest AI technology at scale, and doing so without necessarily the cost of heavy LLM usage, and also without necessarily very deep domain knowledge in AI itself. So really trying to democratize the capabilities of AI agents to broader and diverse enterprise use cases. So you've probably seen from a lot of the talks so far about neural and symbolic, but I still wanted to just lead with a few examples of where AI agents are to set the stage. So here I have had cropped some headlines from the past 2-ish years on some notable AI agent failures in public. In May 2024, Google's AI asked people to put glue on their pizza or to eat rocks. So these search engine errors were going viral for a while because these were so outrageous suggestions. In the same year, Air Canada's chatbot offered customers misleading answers, which ended up in Air Canada having to actually take back some of the promises from their chatbot and having to actually pay their customers for the mistakes that their AI agents were making. In just last year, there was a highly publicized issue or incident again with Google, where if you ask Google, was 1995 30 years ago? it was not able to answer this question correctly. The correct answer last year was yes, obviously, but Google's AI-assisted search was not giving the right answer for this question. Here on this slide, you can see there are a bunch of different products deployed in the wild using AI from different companies. And one common feature that you see is it seems like they're very brittle on a lot of these use cases that seem to be pretty natural and straightforward to humans. I want to unpack one of these examples in particular, which was 1995, 30 years ago. Because when this was publicized, I actually ran some experiments with it. When this issue was first surfaced in the public eye, I immediately tested was 1995, 30 years ago. Remember, this was 2025. The model confidently told me, no, it was 29 years ago because of some training data issues. After this issue or this incident has been widely publicized, it seems like Google shipped a fix for this issue. And after a while, after the news has been out for a while, if you issue the same query again, you will be able to get the right answer. But being a computer scientist, I really wanted to test the limits of the system and how they're doing the fixes. So I asked, was 1996 30 years ago? And not surprisingly or surprisingly, the system still gave me a wrong answer because the fix was only for that specific incident. It was not generalizing. So it looks like there was no generalizable mechanism behind what was presenting that answer to users that was able to handle these variations of the same problem. And really, this is sort of just a small slice of what we see in enterprise users every day. So in business intelligence, when customers ask, what was the total sales last quarter? They could easily have asked some follow-up questions like average, median, or 95 percentile sales from either last quarter, last month, or year to date. Similarly, in HR operations, you can onboard a full-time employee into the HR system following a very complex workflow. It could easily be also a contractor, an intern. They could be based in the US, the European Union, or APAC with different compliance rules, which leads to very complex and different workflows. This looks complex at the surface, but everything that we're varying here actually has a very natural correspondence in programming, as we're familiar with. For example, an aggregation function or the actual information about the employee can be a parameter. Either we're going down the logic of top K versus top percentile. That's a branching operation. And really, however long your workflow is, it's a very familiar control flow in the program that we are very familiar with. So I wanted to make a distinction between the kinds of neural agents that are really prolific today that we use, like coding agents or deep research agents. These agents are really, really good at one-off tasks. So open-ended, novel, and unrepeated tasks, these models are, or these agents are really excelling at. But as soon as you start having recurring but varying tasks, like tasks from the same family with slightly different inputs, that really dominate enterprise use cases, these agents start to fail. So it sounds like what we really actually want is a function where, for the question was why X years ago, we have a function of f of X and Y that solves this whole family of problems rather than that one problem where X is 30 and Y is 1995. So how do we get there? The neural agents that we have today have these 3 pain points. One is variability, where semantically similar inputs can actually end up in very different trajectories because the neural model decides so. There will be high cost and latency because every single step of your agent operation requires the LLM to understand the scenario, to make more planning, and this doesn't go away if you switch to a similar problem. And the third and probably less obvious problem is context management and plan following, where if your workflow is really, really long, you're actually counting on the language model to keep track of where we are in that workflow. And if you have a loop, then the language model needs to remember, I've rolled out that loop 3 times, and now I'm on loop index number 4. All of these things are naturally what programs are good at. Programs are deterministic. Execution is nearly free on CPU time compared to GPU time, and anything like variable scoping, loops, or even a call stack come naturally to programs. So what we want to advocate, and this is the core of our research here, is instead of what we have today, which is LLMs that sometimes call code, we want to build we want to build an agent where it's a program that sometimes calls an LLM, but what's important is that this program itself is authored and revised by an LLM. The program will be the policy for this agent, and it's not going to be a byproduct of solving a specific instant of a problem. So what we propose, we're naming it, we're calling it agent behavior as code, where the agent's behavior is fully specified as a program that calls neural functions where it's absolutely necessary. So LLM capabilities are actually limited to things like perception and extraction. For example, is there a cat in this image? Judgment under ambiguity, for example, sentiment. Semantic mapping, for example, are these 2 sentences telling about the same thing? And authoring the program itself. Everything else, like control flow, state and typing and scoping, progress tracking, for example, the call stack or loop index, and anything repetitive, that is fully executed by the symbolic executor. And only the symbolic executor would touch the execution environment. I'll use these 2 gold and teal colors for neural and symbolic throughout the rest of the talk, so that it's more obvious what I'm illustrating. The important point about agent behavior as code is similar to infrastructure as code, for example, is we're persisting agent behavior or the specification as code. That's a persistent fact rather than something that we use in transients. So how does that differ from some of the prevalent uses of neuro-symbolic AI in the literature or in AI agents that we currently see? There are typically 2 common ways that we combine neural and symbolic operations today. One is symbolic wrapping neural, where you have a program on the outside that calls a neural function. One example of this could be AlphaGo, where you write a Monte Carlo tree search program that calls a value network that is written in neural functions. This is really powerful and is capable of solving one class of problems, but the outside program doesn't actually generalize to other problems necessarily easily. The other side is probably more common today, where a neural system wraps some symbolic operations. This is familiar as tool use, as agent skills. This is really nice when you have really diverse problems, because the outside neural layer is capable of dealing with arbitrary problems, and it's capable of writing and maintaining these symbolic tools. But more often than not, a lot of these symbolic tools are sort of more used in transient, or they're used in a very limited scope for that neural agent's operations. And a lot of the agent's behavior still end up being dictated by that neural agent at the outside. So instead of these two paradigms, what we try to come up with is maybe a third paradigm, which we call neuro-symbolic agents, where we sort of adopt a recursive definition. So here, neuro-symbolic is neural on the outermost layer, wrapping a symbolic execution of the agent program. But this symbolic execution can then in turn nest another layer of what we define as neurosymbolic. So if you really expand this out, it looks like neurosymbolic, 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 arbitrarily nested to the degree that it is necessary for the complexity of the task that you're looking at. And there's some nice properties about this formulation. First of all, on the outermost side, we have the neural model. So the model is going to be authoring what the symbolic executor is going to follow. So this helps us preserve really the flexibility and the plasticity of neural agents in solving any kind of unseen task. So we're not writing that Monte Carlo tree search program once and just using it. We're saying, okay, give me any new problem. I'm gonna try to write a new program for it, but I'm going to follow that program for this family of problems to try to solve subsequent versions of that problem. So we really maintain the flexibility of solving any kind of families of problems. And the second key important point about this formulation is that we use the program as the policy of the agent. So again, this neural author on the outermost side is never directly touching or executing the agent itself. And any execution goes through the symbolic layer to make sure that there's no cheating, there's no shortcut. Everything has to go through that symbolic policy at the end of the day. And last but not least, point about this innovation is also that we introduced this recursion. So we're not saying we will stop at neural-symbolic neural or neurosymbolic neurosymbolic. We're actually nesting that neurosymbolicism into this formulation so that at arbitrary complexity, we can still enjoy the flexibility from the neural author to be able to deal with diverse problems, as well as the symbolic artifact to be able to lock down a symbolic policy to execute for a family of problems. And one key mindset that we introduce with this is also we separate an agent's design from its execution. So typically, when you're working on neural agents, design and execution usually happen together, where you're working with a specific example and the design is you chatting with a neural agent for multiple turns, try to solve that problem, and execution would reuse that whole context that you chatted with the neural agent to solve that problem. But here we clearly separate at design time, we're going to receive user input, we're going to try to author that script that we use for execution time. We're going to try to make sure that that script is generalizable. And at execution time, we're going to use hopefully very thin neural operations to form fit new instances of problems in that family into the script so that we can directly execute that script. So this allows us to front load any design costs into the design time, but then execution time is almost free. And this also helps solve three challenges that neural models actually are fundamentally not the best solutions for. One of them is variable binding, where when you're trying to build a solution for a specific problem, you're going to see the variable values for everything in your problem. So for example, if I'm trying to enter employee record for Peng, and I'll see that the first name is Peng, that's me, and I'm not going to see an abstractive first name because that's the only way that I can finish this task. But in the program, we can directly just declare that, hey, there's a first name variable that will be filled with other variable values. And we're going to continue writing that program with that variable rather than the specific variable value. And the variable value will be swapped in with almost no cost at execution time. A second advantage of this formulation is if we want to edit the agent's behavior, instead of going back and forth in the chat or relying on the textual memory of your neural agent, we can directly edit and look at the code that dictates the agent's behavior. So for example, if I have a really long if and else branch, if you want to add one, you can be confident that if I look at the code diffs, I'm adding a brand new block. I'm not editing any of the previous blocks. You can have confidence that none of the previous blocks that you have already authored will be broken because of this new addition. So this is similar to code versioning in production. This is really powerful for us to be able to influence surgically the behavior of any neuro-symbolic agent without the hassle of sometimes it's following instructions and other times it's not. And the last one I've already alluded to a little bit earlier, which is context and efficiency. One example is loops. If you're asking a neural agent to execute a loop, there's actually usually no notion of loop scoping. And there will be a loop counter that's maintained in the chat context by the neural model. It's very inefficient, and after a while you'll run out of context. But this comes for free with a Symbolica executor because we can just write a loop, and the program index and your RAM and CPU will take care of how to advance the program index rather than an LLM, which is wasteful and expensive. So here's a concrete example of what I mentioned earlier in the previous slide. In a flat neural transcript, something like variables would be, oh, remember we established that earlier x equals 5, and we're now on iteration 2 of 3 of our loop. But in a program state model, this is simply an assignment and a for loop written down. So this buys us not only typed variables in your short-term state, so every step of execution, you're going to have a collection of typed variables. This also gives us execution frames in the program that are naturally tracking where the agent is, what is the agent's policy executing at, and the artifact that is the script that specifies the agent behavior provides structure like modularity and nesting and recursion that allows us to surgically improve and edit their behavior. I'll talk briefly about how we actually try to make this and share some initial results. So at a very high level, we use a neural model to analyze the problem and generate the symbolic program to execute. And then we only execute the symbolic program that on the environment, that's the agent's policy, and then update our beliefs about whether this program is doing well or does it need more feedback. But of course, just saying that we're going to write programs doesn't necessarily guarantee the kinds of generalizations we were talking about earlier, because you could have hard-coded answers for your problem that looks like a program, but still is not using anything. You could have inert parameters that are passed into the program but never used, or you could have examples that are leaking into the program, so it's actually not generalizing. So to deal with these problems, we come up with a simple solution where we ask the neural author, when it's authoring the program, to follow this variation checking. So at the beginning of writing the program, it will try to declare a few different variants of the problem that it needs to solve. And when we're executing that symbolic program, we'll try to swap in each of those substitutions into the program and re-execute. And then we're going to check whether the outputs are actually moving with the input. Is the input actually influencing the output that at the end that we're seeing? So in a concrete program, if we have something like the program on the left and we swap in the April numbers with different hypothetical numbers, we should be seeing different outputs at the end. If we're not, then the program is probably not doing a very good job at capturing this input. So we send that back to the neural model to rewrite the code. So I've been talking a lot about the hypothetical or theoretical benefits of such a potential formulation. How does this actually hold up in real applications? So I'm going to show some preliminary experimental results on some public benchmarks that we did, and you can see for yourself what this looks like. So the first benchmark is called GSM Symbolic, where we have a bunch of math problems that are like the one that I show in the slide, where Zahra is popping some popcorns, and there's some different numbers for descriptions for how this popping evolved over time. And we're going to have different variations for who's popping the popcorn, how fast the popcorn is popping, how many pops are being reported, and these will lead to naturally different answers. Here we ran a neuro-symbolic agent, or what we call the agent behavior as code, ABC agent, versus a fully neural agent that solves each variant individually. Here we have 100 examples. Each example has 50 different instances where the numbers, the names, or something in that description is being varied. And what we do with the neural agent is every instance is solved afresh. Every example is a new example. For the neuro-symbolic agent, we actually just derive the code once and apply it to all of the rest 49 instances. So it's actually a stronger test of generalization. What we see here is a surprising but a pleasant surprise, where the neural agent is only able to achieve about 96% accuracy, but this neuro-symbolic agent with code written once and only slowly adapted to some of the subsequent cases achieves a higher performance. So this neuro-symbolic agent actually doesn't sacrifice accuracy. And what's even more appealing is that when you compare the cost or the latency between these two agents, the neuro-symbolic agent is about 8.6 times cheaper in terms of API cost, and nine times faster in terms of wall clock time, which is dominated by API calls anyway. So you're actually getting slightly better performance or near perfect performance at about 1/9 of the cost and latency for all of these problems. We also test this on some other benchmarks. Again, here you see a tau square bench example. We see that the Neuro-Symbolic agent is able to hold up its performance at pass 4, which is if I have 4 independent tests of the same agent, all of them need to succeed. You can see that the Neuro-Symbolic agent is holding up the success rate pretty neatly compared to the neural agent, which is not as accurate to begin with, and also it's not holding up in repeats. What we see, one of the ideas we've introduced about Neuro-Symbolic agents was actually actively asking the agent to write variations and ask the code to generalize these variations. And we do see that in GenSym Symbolic, the dataset we've seen earlier, this is one of the mechanisms that's really bringing up the accuracy. So if you don't have this mechanism, the overall accuracy is going to be about 70%. But if you enable this kind of generalizable program writing practice, then performance will be improved by about 23%. I'll skip the end a little bit, but just want to leave you with this, which is, I think, the most durable thing that an agent can leave behind is actually not the answer itself or a chat log with the user. It can be actually a program. So this is what we hope will really help broaden the adoption of AI agents in the industry without breaking the world's electric grid. That's my talk. Thanks.
All right. Excellent. Thank you, Peng. Yeah, I want to ask one question at least. So when you, I like that you introduced another category to Henry Kotz's taxonomy. So, but this recursive thing, just to be clear, it's neural, because neural, as you point out, neural symbolic is different from symbolic neural. So, but recursively, it could become ambiguous inside. Is it a symbolic neural or a neural symbolic?
Right.
But do you always mean a neural symbolic, I presume? It's many recursive instances of neural symbolic, but not.
Yeah, that's a great question. So I think Neuro-Symbolic or a plain neural function can be viewed as a special case for Neuro-Symbolic, where there's no further symbolic nesting within that neural operation. So in a sense, this definition can capture both Neuro-Symbolic and symbolic neural. But we want to keep the definition simple and sort of generalizable. So we're going to say that it's always Neuro-Symbolic as a unit, with the understanding that neural itself can be a special case for that Neuro-Symbolic symbol as well.
Okay. All right. Well, thank you, Peng.
Thanks, Alex.
Very timely stuff in the age of agents. Check out the work of Orbi/Unifor. All right. Do we have Jans? Oh, it disappeared.
No.
Ah. All right. Sorry if I'm. Is it Jans?
Jans, yeah, very well.
Okay.
Very
I got lucky. Welcome, Jans. All right, and let me mention, Franz is Gartner, as I have mentioned in the past, is very aware of Neuro-Symbolic AI, which many may find surprising. And we see now, for good reason, it is kind of emerging in industry. And in fact, Jans would probably say, no, not emerging. We've been doing it for a while. So, and highlighted by Gardner, and as a leader in the area. So take it away, Jans.
All right, let me figure out how to share screen. Okay, here. And then
near the middle on the bottom.
no, I got it. I think I got it.
Okay, perfect.
You see it?
Yep.
Let me check if I can put your face somewhere else so I can see what other people see. Yeah. All right. So can I just start? Okay. So I'm going to talk about neuro-symbolic AI and knowledge graphs, and I'm going to try to convince you that knowledge graphs are a natural home for neuro-symbolic AI. So I started writing about neuro-symbolic AI and knowledge graphs in 2021 when the LLMs just came out, but we'll get to that later. So anyway, I'm a cognitive scientist, been doing graphs and thinking about human thinking for the last 40 years. And one of my passions has been in almost every project I've ever done is how can you predict and explain what comes next? Right? When I was doing my thesis research, I was building a model of a car driver. And one of the things, a typical thing you want to predict is this car coming from the right going to stop or not? Now, in a country like the USA, where you have stop signs, that's an easy one. If you live in a country where traffic from the right has right of way, but anyway, complicated. So anyway, so this was one of the things that kept me up while modeling human driver behavior. We, for example, working in France, we did a wonderful project for the FAA where we looked at maintenance records and preventative maintenance for aircraft for various airlines. And then the prediction was, oh, so when do we expect serious defects, say, in the fuselage? And what is the fuselage correlated to? Other things that can go wrong if the fuselage breaks. Anyway, so that was a typical prediction question. And then as a company, we worked for a long time in healthcare where we built knowledge graphs of well, everything you can get to know about the patient. We put in these knowledge graphs and then we do queries over them. And one of the questions that comes up is this particular patient going to get disease X? For example, will this patient get atrial fibrillation in the next 3 months? Right? All important questions. And so I'm going to use this healthcare example a little bit as an example today. And my claim is that logic, machine learning, and Gen AI need to work together to create a believable prediction machine, right? And these three types of AI in isolation can't do much, and they need a home to work together and to record what each have been doing and to contrast against each other. And that home, I think, the natural home for that is a knowledge graph. So as I said, I'm going to take a healthcare example to kind of talk us through this. And the healthcare example is, can I predict AFib for a particular patient? And just think of it, you have a hospital with EMR data, electronic medical records, but most of that data is more for billing between the hospital and the insurance company than that you can do something with it that is clinically important. So we work a lot with clinical notes and clinical trials, all in unstructured text. We kind of take what's in here and put it into a patient knowledge graph that has events. And then once we have that, we can, based on these series of events per patient, for example, train a recurrent neural network, and we can make a prediction using that. We can use rules to predict AFib, and we can use an LLM to predict AFib, right? I'm going to kind of walk us through this. So, but first, let us talk about knowledge graphs and agents. So 20 years ago, we only had databases, right? And mostly relational databases, but that was about it. And then I think about 20 years ago, our industry said, you know what, it would be actually more interesting if we also model data using the relationship between entities. And so we got into the world of graphs, but most of the time it was just taking the complexity of relational databases and to put that into a graph. It's still complex. And then 15 years ago, Google came up with the concept of knowledge graph, kind of adding semantics to a graph and kind of putting domain knowledge in graphs, particular domains, right? And then it got really interesting because then we started talking about application of graphs. But that data was still fairly static. And then at some point we added all kinds of AI to it, right? So we already 15 years ago, we would have description logics and prologue to implement symbolic rules on top of a knowledge graph. And then we started adding typical recurrent neural networks and other machine learning techniques to learn about predicting sequences of events. And then at some point, fairly recently, of course, we added a vector store to a knowledge graph, and we started integrating LLMs on a very deep level into the knowledge graphs, right? So that was the big next stage. And then at some point, we wanted to have agents that could use our knowledge graphs so that a user could talk to a knowledge graph, or that an agent used the knowledge graphs to do its work. And so we got to the point where we realized that when you work with any kind of database IT system, a lot of people think you can just reverse engineer the schema or the ontology, and that's all you need to know. But actually, most of learning how to work with the database is in the head of people, the people that made it or the users. How do I want to get the data out of my database? But also through learning. The agent tries and tries and tries things, and every time when you learn something, you want to put that learning back into the graph. And at some point, about a year ago, I think, the whole concept of a context graph came up, where you kind of say that it's not only the ontology or the schema of a database or a knowledge graph, but also everything you learned so far on how to work with that particular database or knowledge graph, right? And so we at our company created the whole concept of context graphs. Now I'll give a tiny demo a little bit later where we show how this actually all fits together, right? And now we can have almost autonomous, not entirely autonomous agentic AI that is entirely controlled by a context graph, but also feeding the context graph continuously, right? So that's kind of a little bit of the history of how we worked this. And so, like I showed you a little bit before, so we go from clinical notes and other information to a knowledge graph, and then we do predictions, right? So now let's take you through the various steps, right? So to begin with, you have to fill the graph, and we created some technology. It's all Neuro-Symbolic, and we call it CLINEX, clinical text extraction. Although we also have a version that does it for car maintenance and aircraft maintenance. And anyway, the point is you have to fill the graph, and we do that neurosymbolically. You have to create predictions from the graph, right? And then finally, you have to work with the graph as a human being. And so there's three completely different approaches of neurosymbolic AI that we apply in just an example like this, right? So let's begin with filling the graph. So I think most of the people in the audience would never ever trust an LLM, right? When you extracted something from text, that would be the most almost insane thing to believe, right? So basically, what you really want to do is use an ensemble of LLMs to help you with text extraction. So what we do is we take unstructured text, we created our structured output, and then we give it to the two LLMs, but to two different LLMs, and we get adjacent structure back, we compare the outputs, and then we use a third LLM to come up with a decision like which of the LLMs should we trust, and also explain why you trust it. And then we finally get the agreed terms between 3 LLMs, but we also store in the knowledge graph why we chose that particular term, right? But now you only have terms, dumb strings. We call them here always dumb strings because they're not grounded in any vocabulary, right? But you cannot do any work in most domains, especially healthcare, if you don't ground every string you ever generate into a vocabulary, right? So as a semantic knowledge graph company, we're all about ontologies and vocabularies, right? So I'm going to show you in a minute how we do that. And then ultimately the data goes into the knowledge graph. And what I say here, we do that for clinical notes, for test reports for cars, or for invoices and contracts, and many more examples. And so how do we do the grounding? Again, that is neuro-symbolic, right? So you get a term like AFib out of your unstructured text. If you're lucky, and this happens in less than 1% of the time, the term actually directly exists in your vocabulary. So, but anyway, you have to try anyway. Then if that doesn't work, you try a little bit of fuzzy matching and wildcards. If that doesn't work, you try variations with free text search. And if that doesn't work, you say, okay, let's get the vector embeddings that we have for every term in our vocabulary. And if that doesn't work, we basically take the original string that we were looking for, ask an LLM, hey, give us some synonyms that might describe this particular term, and then we start again. But it's a beautiful interplay between logic, symbolic reasoning, and well, what I was just talking about, right? And getting that into the knowledge graph. Okay, so that was the first part, and the second part is the prediction part, right? So we got the data out of the databases and the unstructured text, put it in the knowledge graph. And by the way, we structure most of these things always as what we call an entity event model, where we have a core entity that could be a patient or a car or a plane or a customer. But it's not only a series of events, but also interlinked into a holistic graph, right? And so here is an example of a graph that we have, right? So we have a medical records, right? Where a particular person had an encounter, which is an event with a sub-event, acute pharyngitis or sore throat, right? Which we link to an ICD-10 term. ICD-10 is the billing code, the thing that hospitals and insurance companies work with. But we also link it then to SNOMED, one of the most important vocabularies in healthcare. So now we have about 200 million triples for all the different vocabularies that you might have around medications, procedures, devices, diseases, etc. And of course, as you know, taxonomies are trees, right? And then we have 500,000 FDA-approved clinical trials. So each of these boxes is a clinical trial. And obviously, we apply the same Clinex technology to this. So we, again, extract terms out of that. And they also link to UMLS. Otherwise, what's the point of doing this work? And then we have COVID literature. So each of these boxes is a PubMed literature entry, right? And if you apply our technology to that, again, you extract the terms out of that, and then you link it again to UMLS. And it's all about the sore throat. And finally, we have adverse effects of vaccinations. And again, this is in here, right? This is in the in these reports. And so if you now want to do clinical trial matching, you can go from medical records straight to the clinical trials. But the point is that a patient was represented as a series of events. So that means you can say you're interested in AFib, you find patients with AFib, you look at the events that were leading up to this, and you can train a recurrent neural network. And once that is done, you can ask, hey, is this patient going to get AFib? And it will give you an answer. You can ask an LLM. This is kind of amazing. The same event we used to put into a recurrent neural network, we can give to an LLM, and it will give an opinion. And then we can do logic. Right? The doctors for a long time had rules when people might get AFib, and we do that. So we apply the logic, or you can ask doctors themselves. And once you've done that, you'll find that each of these technologies will give you a prediction. I'm sure there's a lot of machine learning people in the audience, and they know all about democratic voting techniques or ensemble techniques, right? But anyway, we get these various predictions, and then we feed that to a meta agent to finally get a prediction and a ranking, right? And that prediction goes back into the knowledge graph. So we get this final prediction, and then finally we can look at two patients. For example, here's a patient with a very high score for a Neuro-LLM, for recurrent neural network, and symbolic. So we ask another LLM, looking at these results, why do you think this is so high? Will this guy really get AFib? And it will give you an explanation, and here's a person that's pretty safe so far, right? And so this is the prediction part, and again, a completely different way of doing neuro-symbolic than the extraction technology, right? And now we get to the third neuro-symbolic technique that we use, and that is a context graph-driven agent that we call Graph Talker. In a sense, it's next generation MCP tool, but the control loop is not external, but it's part of the knowledge graph itself. And basically, the reason we had to do it is so that smart end users that never want to learn any Sparkle or machine learning or very ingenious prompting or logic, right, to talk to their data. But the most important thing that we discovered is, and I said it already before, when you're dealing with systems, it's amazing how much knowledge is in the head of people that's not in the data itself, not directly specified in the data. And so this is literally all about learning. So let me change the sharing. Let's see if I can do this easily here. Replace. Then we go to, I think this might work. Okay, yeah, I think it works. Let me go here. And so here we have a tool. So you remember the graph that we had, right? Earlier. And so, no, this is the wrong one. Which one are we seeing here? Okay, I found this window. Sorry about that. So here is this tool that works on top of our knowledge graph, where I started by asking, okay, please find some patients at risk for atrial fibrillation, right? And it says, well, here are the results. I found patients at high risk for atrial fibrillation using 3 independent prediction systems in patient graph, right? And that RNN scores, LLM predictions, LLM risk, and this is the output of a rule-based system. And it will actually tell you then how the prediction system worked and why doctors would say that you might get AFib. And then I say, are there patients where the RNN and the LLM disagree on the AFib risk, right? And then it will give me an answer, right? Both moderate, low risk, or both high risk, or one high and the other low, right? And so you get a little bit of data about that. And then because I never want to look at tables, I say, hey, could you please visualize this for me too, please, right? And it will create 2 visualizations, a scatter plot and a horizontal bar chart for the agreement category. And then when it's done, is would you like me to store the query and both visualizations in the query library? And I say, yes, please. And then it does this. And by the way, you can see on the right, this is like the trace of all those tools that were applied while doing that particular query. And you see that so far in preparation for this, I spent $2 on this query. Wow. And $8 in total, right? This is running on one of the expensive plot models. On the previous talk, we seem to have some ideas on how to make this a lot cheaper. Anyway, so we have this here, and then I could look at the query, like the AFib prediction model agreement between RNN and LLM. And what we do is we store the query as a URI. We store the query that we needed to get the data. And then we can look at the bar chart for both moderately low, low, high, low, high risk, etc., plus an interpretation of the data. Or I can look at a scatter plot, right, about both moderate, low risk, only high risk for R none. So R then low, L and high. But anyway, the point being, you don't need a data scientist, you don't need a Sparkle or database specialist, right? You just talk to this tool and it'll get you results. Now, the thing I want to stress is that when I started out with this particular knowledge graph, I didn't have any context graph. I just had an empty page here. What you see here are all the tutorials to how to deal with this particular knowledge graph. And all these tutorials are not written by me. They are written in interaction with me, but every time something went wrong or we couldn't figure out something, we took some time and we spent like 30 iterations to get an answer. And then I would say, hey, so what do I have to learn so far? And can we put that learning into a tutorial? And then the system said, of course, and it would write the tutorial for me, if that makes any sense to you guys, right? So there's a README file. It's always for the people in the audience that are using vibe coding or say work with Claude, right? It's like the Claude.md file with then all the subfiles for specific questions or things that you might want to do. And so there's an AFib queries tutorial where we explain in detail that if you have AFib question, what is the best way to deal with this? Or what if you want to deal with the particular vocabulary system that we have? And the point being not so much what's in here right now, but the fact is that I have a full tutorial system that the system built itself. And I hope that comes through, right? So now let me go back to my presentation. It's really weird. No one can ask me questions. Let's see, I have to find my thing again and then replace. I'm going to replace it with instead of email, Rosemary. Just find my PowerPoint. Give me a second. I can do my whole screen. Share. Okay. And then let's go back here. And this is my screen. Let me put the other screen. So I gave you a short demo, right? And just if I try to explain what actually is happening, right? So we have an MCP-like tool. So here's the tool Graph Talker with the control loop in it. And I ask a question. Graph Talker proposes a tool, it executes it, it verifies it, it refines it. But in the process of doing this, right, it learns things. So it puts things in its memory system, and so it learns from failure. And while doing queries, it also will read back, given the question of the user, hey, what can I use for my old knowledge? And so you get this beautiful figure 8 to learn. And it's kind of silly to think, because some people think this is all automatic now. The human in the loop is 100% important for making this work, right? Otherwise, you would get something really weird, right? So the human in the loop stays important. It will ask questions, it will look at the outcome of queries, and if it doesn't believe it, it will tell you. And sometimes it sees things that things are not correct, and it will ask the system, hey, write a tutorial part for this. So anyway, it all fits together in this Graph Talker paradigm. And so I think it's clear by now that this agent reasons against its own accumulated operational history, right? It's not just the schema or anything else. And it knows not only what is true, but what is already tried, why it decided something, who may see what, and how one decision led to the other. And so we're getting closer to autonomous action. But I really don't believe that much in autonomous action. It is kind of controlled autonomous action where the human is always as much as possible in control, right? And then one more time summarizing. So we have a neuro-symbolic technique to fill the graph, neuro-symbolic ensemble to kind of create predictions, and a neuro-symbolic agent to actually act on the graph and give end users what they really want. And again, it's hopefully pretty clear that we have this neural component to handle all the fluency, language, and ambiguity, and the symbolic structure keeps everything together, right, in the knowledge graph. And it's applied in almost the NSAI, the neuro-symbolic at ingestion time, inference time, and query time all the time. That's my story for this afternoon. Any questions?
Okay. Thank you, Jan. It's very nice. I think one takeaway, hopefully for everyone, is not all knowledge graph approaches are necessarily the same. There's a lot to do. It's very complicated getting a knowledge graph to work. And actually it takes a lot of sub-problems to be solved. And there are many ways to solve those things. So the simple knowledge graph RAG that became popular recently, I've seen many approaches that are just too simplistic to actually work. So I think we're kind of seeing that in these various companies we're highlighting, that they put a lot of thought into different aspects of it, and it's necessary. One question from the audience. Are you producing sparkles with LLMs too, or are they predefined by experts? What methods do you recommend to ensure that the sparkles are high quality and not biased if you use more than one ontology?
So to begin with, in our knowledge graph, we have a way to reverse engineer the shackle of the knowledge graph, meaning we take the schema of the data that we have in the knowledge graph and kind of a condensation technique that you get all the essential classes and predicates in your knowledge graph. And the knowledge graph is not allowed to create any query that doesn't use those classes and those predicates. So you'll never get a Sparkle query that is syntactically incorrect. But you can get very stupid Sparkle queries, like to say for every subject predicate object in this graph, right? Which work great for a knowledge graph under 1 million triples, but you have 2 billion triples. You can't have that. So we have a whole series of anti-patterns, right? We have a big database, never do this shape of the data, never do this shape of the data. So that's in the control loop and in the context, what not to do, what is done to do, right? And then we use the context system, but if you do, so basically you get iterations, right, to get to an answer, and in the beginning, you might get 30 iterations to solve a question. And then we ask the graph talker, okay, so why did it take so long? Where did it go wrong? And it will give you analytics. And then you say, okay, can you write this up for your context? Or it says itself, oh yeah, that was stupid. Why shall I write it up as a context? And it will write it in the context system, and it will never do it again, right? So it's a question of learning. If you just look at the ontology, it works, but not super efficient, right? You have to work for a while as a knowledge graph engineer or just as an end user. We have end users that don't know anything about knowledge graphs, but they're training graph talker continuously. Because this system not only works for knowledge graph, but you can also use the same tool to talk to any relational database or MongoDB, or let's say even a tool like Neo4j. So again, it reverse engineers the schemas and it creates the appropriate language for that particular database. And again, learning is the absolute most important part.
Awesome. All right, we have a break now, which until 15 minutes after, so about 10 minutes. Maybe I'll use that opportunity to ask you one quick question, Jans. So one thing that might have slipped past people is, I think it's significant. You characterized things like cars and so on all as events, which I find interesting. And actually, I mean, if you think hard enough about ontologies and what are things and what are verbs and so on, you can come to that conclusion. Actually, everything is an event. And
yeah,
so,
I do approach it well. Literally, instead of just having a link, an edge between two nodes, every edge is a temporal predicate, right? Most predicates, even if you're married to someone, right? But that's because of A married to B. Now you're married from a start time to an end time, right?
yeah.
Or you live there. Now you live there from a start and end. So every predicate can be, and this is the wrong English word, temporalized, right?
Mm-hmm.
And so we use that pattern a lot.
Yes. Very nice. Okay, and that is usually, or I think it's a sophisticated idea that more people should know about. Okay, well, thanks again, Jans.
It's my pleasure.
Check out Franz and Allegrograph, and we'll now take a break. See you all in about 9 minutes.
All right.
See ya.
Hey, Alex.
All right. Hey, Benjamin.
Glad I can hear you too.
Okay.
That's good.
So, last but not least, we have Benjamin Grossoff, who, as many of you know, helped us think up the whole institute. So now he's at DARPA, continuing his big thinking, and he's going to show us some of it. And so today we saw Neuro-Symbolic AI in industry, and now it's a fitting cap to look at, I think, what I believe is the largest consumer of IT in the world, which is the US government. So take it away, Benjamin.
Okay, thanks, Alex. Well, first of all, thank you for having me. And it's an honor to speak at the summer school this year. I have presented previously at the summer school. I'm going full screen here. Let me know. Does that look okay now?
It disappeared, appeared, then disappeared.
Should I stick to non-full screen?
Try it again.
I'll try again going to full screen. Or do I have to do that through the restream to present screen as opposed to go full screen in the PowerPoint app?
There's a suggestion that maybe you turned off screen sharing.
Huh. That's kind of weird. I didn't do that via any explicit action. All right, I'm doing share screen. I'm going to do entire screen. Is that working?
Nope.
Okay, well, so we don't mess around too long here. How about I just show the window?
Ah, there we go. That's working.
Okay, all right, so I'm going to just show the window. Wish there was a way to drop the banner. I mean the ribbon. But anyway, it's not, this stuff is big font. So I think we'll be okay.
Yeah, I think
all right. So thank you. All right, so my talk is about how is it possible to create high assurance or enable high assurance in AI. So this is a two-part talk. I have created and lead 2 programs at DARPA. One is called CODORD and the other is called Clara. And these address 2 of what I think are the most important problems in AI, and both are largely justified, motivated, and aiming at high assurance. So let me first talk about CODORD. CODORD is short for Human AI Communication for Deontic Reasoning DevOps. Now, the deontic here is important because, first of all, it means permissions, obligations, and prohibitions, which are rife in the way that we live in modern civilization, maybe older civilizations too, but in particular requires defeasibility and multiple modalities from a logical viewpoint, and whether it's organizational policies, laws, regulations, healthcare treatment guidance, and so on, is important in life, but also very demanding from an expressiveness viewpoint, logically. So the objective in CODORD is to do decision support, be highly assured, and cost efficient enough to be able to afford to have capabilities that are providing a relatively high level of assurance. So what it takes expressively is also important and useful, and in many cases needed in many other realms as well, which I'll come to toward the end of the talk and also when talking about Clara. So this sub-talk about CODORD, I meant in terms of the end of that. So today, knowledge representation and reasoning, which I'll call throughout this talk automated reasoning, or AR for short, has a couple of crucial advantages from a kind of methodology viewpoint that are associated with high assurance, or kind of key constituents of high assurance. One is being able to have very high correctness, not just 90% or 99%, but say how many nines, as people talk about in manufacturing and total quality management. So maybe 99.99 or 99.999999. So it could be many of those decimal places. Now, how much correctness you need will depend on application, and there's cost benefit trade-off, of course, as there always is in application work and deployment in particular. But another aspect is being able to have not only verifiability in the usual sense, but also including explicit logical form explanations that can be readily comprehended and utilized, including to support editing and debugging and an edit test loop by knowledge engineers that is trained in logic array, but also other users who have knowledge to contribute. And these might be people helping develop test cases. It might be operators in the military. It might be a compliance officer in a bank. It might be a salesperson or a procurement person in e-commerce or along supply chain, folks like that. So LLMs have their strengths as well, including being able to do relatively rapid development and not requiring much specialized expertise to use overall. However, we'd like to have both, and Codord is focused on trying to be able to provide the best of both machine learning and AR. The key step to cost efficiency is to attack the problem of being able to translate from natural language into a suitable specification in a relatively high expressiveness logic. That's called knowledge authoring, and do so in a way which is relatively low in cost as compared to what it has been before the Codord program. So logical AI was really the first area that was commercially successful, starting in the 70s and really dominating the so-called expert systems boom or era of the 1980s, which actually lasted into the early 1990s and produced the so-called business rules management system sector in industry, but at a much lower rate of growth than happened during the mid 80s when people first got excited about it. And what ended that era? Why did the center of gravity in AI investment, both in R&D, but also in terms of fielding and deployment, shift to machine learning pretty strongly starting around the later 90s? The reason is that there was a so-called bottleneck, a KA bottleneck. Back then, it was often called the knowledge acquisition bottleneck, which applied when knowledge was relatively complex in expressiveness and form. Now, what we want is to reach high assurance for inferences that we care about in order to support decisions that we care about that have relatively high stakes. So one way to technically narrow that or operationalize that, make that crisp, is to have a focal set of queries or a focal set of implications that you're looking for in a large space that overall is being treated in AR. So this KA bottleneck basically was a blocker for the entire field of logical AI in terms of its growth rate, its total size in terms of revenue and economically and so on, all the way from the early 90s until now. Now, some big bites were taken out of it. One was knowledge graphs, and I worked on that when I was a DARPA performer 20-something years ago. And when I thought, who would be great to go after this problem? Who cares about it? Who has a lot at stake? it seemed to me DARPA and the US Department of Defense was a good place to go after that. And it required a degree of patience to produce results that I find is often hard to summon investment in industry. So in decision support, in particular, we want to be able to, in defense, support things like course of action planning, autonomy, whether it's in weapon or other kind of civilian systems, maybe transportation, robotics, in manufacturing, the home, etc. And also literally navigating international agreements where, for example, there are permissions or obligations or prohibitions associated with different routes in logistics, in maritime, the oceans, and also in other settings, air corridors, for example. So part of the difficulty in terms of the state of the art before the Codor program is that the logical semantics of natural language is far from solved. It's not yet really been addressed very deeply or satisfactorily by LLMs, although they can kind of give the illusion of that. So there were, however, already existing logical languages and tool sets, in particular the RuLog language, which is an extension of well-founded logic programs. If you don't know what that is, more or less Prolog, but a cleaner version of it, with a tool called ErgoAI that enable being able to reason well about deontics, including with defeasibility, with multiple logical modalities, including, for example, not just belief and obligation, permission, prohibition, but say intention or other kinds of desire that people often talk about in the field of AR. Now, so here are some examples of where the deontics in particular is important, but overall assurance is a growing need in DoD and also increasingly recognized as looming larger and larger in AI overall as the stakes socially and economically and also militarily grow. Now, there are some very specific practical limitations or in the pre-program SOA as of January 2025 that knowledge engineers trained in logic, even they had to do most of the translating from natural language into the logic in their brains. We'll call that manual KA. Another was accessibility that SMEs couldn't directly do it. SMEs or subject matter experts usually are not trained in logical AI. They are not KAs. A third is the iterativity, that doing a single round in the authoring was not accomplishable even by those trained, the KEs. In particular, there's a need for revising in a way where contextualization is complex and requires repeated test and edit, relatively small steps done relatively quickly, which actually the existing tools support in AR now much better than they used to, and in particular, the ErgoAI tool does. However, you have to reach shared understanding between the people who do have logic expertise as humans and between them and the machine, as well as with between the SMEs, hopefully, and the machine to do an effective job. Now, the approach in Codord is to attack these first two problems of automating it all and accessibility or degree or depth of automation and accessibility by automating via AI itself the generating of the logical statements. In other words, to much more highly automate the encoding into logic starting from natural language. In terms of the iterativity, one basic way to do this is treating the natural language as source form to edit that natural language source form and then rerun generating within an overall process of doing revising. We see here in the lower right an example of a rule in the target language here that starts out in natural language, say as Colonel Smith grants permission to Major Kinjay to airdrop equipment packages in a particular map sector if a particular operation is green lighted. Now the SOA for complex statements like this, a rule, often was that it took hundreds or even thousands of dollars per assertion sentence and days to months to get to the point where things were satisfactorily debugged, depending largely on the expressive complexity of the assertion. This is a kind of, I don't know, maybe 6 out of 10 in terms of expressive complexity. It's considerably more complex than most knowledge graph kinds of stuff is. Now, where did these numbers in terms of dollar amounts come from? Various people have industry experience. There's actually been little to no academic research in this area quantifying precisely or studying the amounts of money involved because basically it was cost prohibitive for most applications. So why did this program get approved to be funded and pursued and executed? One of the technical insights here is that although we cannot rely on LLMs for doing logical reasoning of the kind required for deontics and in these relatively high stakes kind of application settings, we can use them for their strengths. And one of their outstanding strengths, maybe their greatest outstanding strength from an engineering viewpoint, is in translating between different languages, whether they're natural language or they're computer languages. So this open hard problem of generating high expressiveness logic code, we can seek to leverage LLMs. And that's what the program has been doing. And I'll tell you what some of the interim results are in the program. It's been going pretty well, actually, overall. So at the time that we laid out the program, we said, well, LLMs so far at that time, 18 months ago, were able to code into as targets imperative programming languages such as C, C++, Python, Java, JavaScript, and so on that had very large size training data sets available, often called high resource languages as targets. And there are some other techniques we can draw on in AI that we talked about, like creating synthetic data, using semantic parsing, and there had at that time hadn't been very much experience yet in treating logic as the target for coding agents as opposed to treating imperative programming languages as the targets for coding assistants. So some things looked harder, some things looked like might be opportunities to be easier or to take advantage of, which are summarized in the table below. I'm not going to take the time to go through all that. But the cool thing is we've discovered since then things have moved in terms of the state of the art and what's been happening in industry. So the concept here in CodeOrd is instead of a knowledge engineer, KE, learning a domain from a SME, depicted on the right side of the upper band of this slide, with a lot of work required to iterate between the KE and the SME to learn the domain, often reading documents, not just talking to people. And then they would do generation and then revising. And that itself involved a loop, which you see toward the left middle of the diagram here as well. And then the AI would fully automatically perform logical reasoning, say for RULOG in the Ergo AI existing logic engine. In CodeOrd, the concept is not just KEs, but also SMEs can input NL to an AI coding agent that generates code in the logic and then also hand it off to do the logical reasoning as we see in the upper left, which is depicted by that AI as being more central in the process in the middle band as we go from top to bottom in this diagram. This would enable not only KEs to start from NL, but also in many cases for SMEs to be able to contribute directly. The long-term vision then being that the AI would also do more and more of the revising, as we've seen happen in the area of coding into imperative logic languages, imperative programming languages so far, with the main form of input to the AI being natural language and much less need for the labor, relatively expensive, of highly trained KEs. So why might CodeOrd succeed where others have failed? I mean, we had basically depending on how you count, well over 3 decades of primarily stasis on the KA bottleneck for complex KR, for complex AR. Well, first is that there have been these advances in NLP, including LLMs. Secondly, a focus on a target logic that meets 4 practical requirements. I'll lay those out in a moment. And the third being by focusing on deontics for decision support in contrast to general semantic natural language understanding, which has much wider, huger, and more diffuse and ill-defined scope. So by having a more sharply defined target problem here. Now, what are the 4 practical requirements? And these are what led to the choice of ErgoAI by the performers and the DARPA team on ErgoAI as the target engine and its implementation, particular syntax for RULOG. The first is have sufficient expressiveness, be concise when specifying knowledge, including when adding exceptions, when doing edits, and so on, relatively small amounts of syntax to change, rather than great scads of it. Second, being scalable computationally. Without onerous expressive restrictions imposed, RULOG can be kept polynomial time. Yes, you heard me, polynomial time. Even though Prolog and the basic kind of so-called normal LP is is itself not even decidable. And the way to accomplish this is by reusing the third truth value undefined in the well-founded semantics for LP logic programs, extended expressively in RULOG. It's basically a more powerful form expressively of a well-founded LP. One can keep things polynomial time. There's a technique called restraint. It's been out there for a long time, implemented for a long time, low overhead. The third is having strong explainability to support the debugging process, but also participation by SMEs and trustworthiness and acceptance overall. Adoption, therefore, overall. Fourth, having a tool set that is high quality and open source, which had become recently available before the program started. Now, over on the right, we see some tiers of expressiveness. I mentioned that multi-agent, multimodal. For example, consider this sentence. The US desires that Germany believes that Poland is obliged to transship military supplies to Ukraine for their side of the war between Ukraine and Russia. So that involved a single sentence, not a few tens of words, with several agents, US, Germany, Poland, Ukraine, and multiple modalities, believe, desire, and oblige or intend, maybe mixed with that as well. So one of the great lessons of practical rule-based systems in their deployed applications for the last 40 plus years is that the ability to have exceptions relatively concisely stated and managed in a sound and comprehensive way is usually important. It's not enough to have so-called monotonic logic, such as classical logic. And for deontics, even the most basic rules often have exceptions. Like the most basic rule in defense, for example, is a soldier must obey the order of their superior officer, except when it's an illegal order, except when it is superseded by a later order from that same superior, or superseded by another order from further up the command chain beyond that order, that officer for the original order. So in short, we need, but also can have the expressiveness required for deontics. And a key to that is a so-called high log technique for higher order syntax in AR, including specifically both in first order logic and also in logic programs that more or less extend normal logic programs a la Prolog. The program overall, the DARPA program, here includes not just software that's being developed, but also machine learning models, methodology guidance and structuring, and some design insights and rationale. It's involved updating a SOA repeatedly every couple months or so, and there was a big jump in the competency of the LLMs and foundation models in terms of their ability to code into quite low resource languages, which Ergo AI is. Also, the test and eval team was developing multiple test cases and executing evaluations with a protocol designed and developed as well. And then some novel measures and insights, some best practices, etc. So there are a lot of things that have been being developed, including on the test and eval side in the program, not just agentic approaches developed by the different performers doing research funded by DARPA in this program of CODOR. Encoding natural language, not just for assertions, but also for queries, and continually updating an agentic state-of-the-art system to compare the perform approaches to that was based on more or less commercial off-the-shelf foundation models. So what are the results to date? The eval has been of correctness of focal queries and also of the labor time cost of knowledge authoring. We've been being quite successful. The declarative character of the target language probably helps the low resource coding process. We were so successful beyond what we'd originally guesstimated in the first phase of the program, a year long, that we did a major revision of the plan for phase 2, going after 5 to 10 times more natural language sentences in our tests and demos and milestones. Overall, we're seeing roughly at least an order of magnitude lower labor time for the steps of KA that we've been evaluating and testing. So this is looking very promising as far as serious progress, on the KA bottleneck. With lower time, you're also we've found as well lower elapsed time for human developing skill at doing KA. So the applications and future opportunities here, we're basically applying neurosymbolic techniques. We're applying machine learning, especially neural net machine learning, to help AR, to help the logical side of AI become more practically deployable. We're looking at applications, for example, in financial and tax and regulation and legal, well beyond defense. And there have been already a handful of publications released by multiple performers in this program. The opportunities and outlook include going after KA for other languages in the logic program family. For example, answer set programs, which overall do not scale nearly as well computationally as well-founded LP does. This can help feed the second DARPA program that I'm going to talk about, Clara, which is in the second half of this overall presentation I'll be getting to shortly. So beyond deontics, there's high potential for doing reasoning about action, about causality and planning, because decision support settings usually require one or more of those, and also settings where you're reasoning for doing decision support using deontics usually involve one or more of those. And another direction, there's potential for meta reasoning, which is useful for systems integration and also for machine learning, and therefore for Clara, which I'm going to tell you about more. But I have here in the slides, which we intend to post publicly, I believe the Centaur Institute will be doing that associated with the summer school. Some pointers for additional info about the Codord program. So now let's talk about the other program, Clara. This is short for Compositional Learning and Reasoning, which is essentially the superclass of Neuro-Symbolic, because it's not just for neural net as a form of machine learning. With AI for complex systems engineering. So this is an approach to enable high assurance that can be built into next generation AI systems of systems, including specifically systems of systems for defense. Some of the largest and most complex systems in the world that exist today and have historically are in the defense realm, including perhaps foremost by the US. The goal here is to create a foundation based on theory, new theory in computer science and AI that can provide high assurance while also simultaneously enabling broader applicability than in the past when you could have high assurance in AI systems that hierarchically compose a variety of heterogeneous ML and AR subsystems. Over on the right, we see a little diagram of some of the major subfamilies. There are many further refinements we could talk about within the area of, say, Bayesian ML, neural nets ML, reinforcement learning ML, etc. And on the AR side, within classical, including modal logics, for example, as well as within rules, including LP and ASP, but also probabilistic variants of LP systems or other kinds of logics. So by assurance here, we mean not just verifiability, but also having strong explainability. And there's actually some technical rigor that was introduced in the solicitation about what are some key characteristics of being strong in explainability that can be formulated in logical terms. So one way to think about shared meaning in general, which is important in Codord between human and machine, but also here in Clara between different AI systems, as well as among humans and between humans in AI systems, is having automated proofs in logic that ordinary mortals, not with PhDs in logic or whatever, or even graduate degrees in logic, can understand and follow and feel confidence in and trust, become a basis for trustworthiness of the systems that are developed. So the approach of Clara is the following, and it's a very radical premise, which is if you talk to people 50 years ago in AI and you ask, will ML someday be formulated in terms of logic? Probably most of the leading AI lights in the field would have said, yes, someday. And there was quite a lot of work on that between the mid 70s and the mid 80s. But it didn't get that far, unfortunately. So the premise of this program is things are different now. We're in a position to go after this long held dream in the field of AI. Put ML itself on a logic based footing. And that can offer, together with enabling high assurance, a host of potential benefits in future if we're able to be successful in this very ambitious program. One is to be able to more robustly follow the intent of the humans instructing a system. It might be commanders in defense, but it might be many other kinds of users in other kinds of application settings. To lower the costs of testing, which blow up worse and worse and worse as you compose more heterogeneity and larger number and variety of subsystems when overall creating systems of systems. So we desperately need better modularity, including around the creation of and the conducting of testing in AI systems overall, especially as we get into higher stake applications that are bigger from an economic or business viewpoint, and also bigger in terms of maybe stakes of survival, political freedoms, and also health. We want to be able to update knowledge in more agile fashion, enabling systems to be able to adapt more rapidly to changing conditions, changing world state, changing goals or desires or priorities among objectives that society or people or organizations have for these AI systems. We want to be able to generalize better, like, in the classic kind of out of distribution sense, and overall have more reusability, including via stronger compositionality, as mentioned in the title of the program. Now, let me mention that reasoning in AI systems has been hijacked as a term by the LLM advocates. I view it as basically logic envy, akin to the physics envy that people have often talked about for economists and psychologists. They took a word that was well understood to correspond to proving in logic and then decided to call, for example, chain of thought with opaque, sloppy, error prone steps in the so called reasoning and apply the term reasoning to that. So I thought Luis did a great job, Luis Lam, this morning, um, placing that in context along a spectrum. And I don't mind that, but I think most people who use the term, who hear the term in the general audience for AI, people who are lay in terms of AI research, do not understand that distinction in the terminology. So calling out logical AI as distinct from LLM so-called reasoning is very important to educate the world about neurosymbolic. So in terms of the architecture envisioned for the Clara for systems, after Clara has hopefully succeeded or at least made some significant steps of progress, we will have a form of AR that is generalized in some crucial regards to be able to tackle the learning aspects and talk well together with, compose very deeply and cleanly and elegantly with, potentially, AR approaches and uh, uh, components. And then be able to build applications of AI on top of that that have high assurance, so that the taxonomy of AI changes, as we see in the lower left, post Clara, to have a whole new shared branch between AR and ML that provides both assurance and applicability, as opposed to today where you kind of have to choose between having assurance with AR, but then having some problems in terms of narrowness of applicability versus ML having weak assurance, but fairly broad applicability. And the fact that this is possible in the direction of Clara, I think we've seen a very interesting example of a system and architecture in Deep Problem, which came out in the late 2010s and has the papers from the early 2020s that does this. It uses joint loss with gradient feedback that stitches together Bayesian logic programs with neural nets. For example, at a lower level, the neural net is handling the perception for MNIST type handwritten character recognition, and the Bayesian rules are able to deal with there being noise and uncertainty, but also solving, say, addition problems in this very simple example that will fit on a single half slide here that is featured in the original papers about Deep Problem. Now, there's a major technical challenge around breadth of applicability. We'd like to extend the kind of assurance provided by rules, in other words, declarative logic programs, much more widely to the overall set of useful frontier machine learning and AR techniques, and extend that assurance also to composing all those things together. Now, here, in terms of expressiveness, we can leverage and combine two recent major advances. The first has been in the area of Bayesian probabilistic rules, notably for, we could use that for the inferencing aspect of ML. And making ML, while doing this, be AR based is something that has been pioneered not just by Problem, but there's another whole nice technology stack, software, high quality, open source available that's been done in CP-Lint and PITA by Fabrizio Raguzzi and all, fairly recently as well. great book by Fabrizio on probabilistic logic programming, which I recommend, second edition 2023. There's also been another major area of recent expressive advances, which is that in ErgoAI, to use the so-called high log technique, which is very elegant, simple transformation that takes higher order syntax into first order syntax, and use that especially for the training aspect of machine learning, where you have to navigate in large spaces of candidate learned models that you're considering moving to during the course of training. So we'll talk more about some of the advantages of that on the next slide as well. So there are some other potential opportunities to create compositions of AR and ML, a variety of kinds of AR and ML, in a hierarchical, fine-grained way. And one which I think is very exciting, as talked about in the solicitation, we're pursuing with the performers in the program, is reformulating rules in terms of linear algebra so that rule deductive inferencing can be viewed as tensor operations. And of course, tensor operations are at the heart of neural nets and many of the other frontier techniques for ML today. Neural nets can be viewed in terms of fuzzy probabilistic automated reasoning, and there are concept bottlenecks. So there's a variety of ideas that performers are pursuing, using in the Clara program. Now, how is it that we're going to move to kind of high expressiveness or high enough to do learning kind of stuff, both inferencing and training in ML terms, and also be tractable? In other words, to break this historic tension between expressiveness and tractability for the purposes of Clara and creating high assurance AI that does neurosymbolic, that does learning and reasoning. We can leverage the opportunity to create tractable generalized AR via the bounded rationality techniques, which are coping with high log. There's this technique called restraint using the third truth value in well-founded LP. And that has already happened in the area of making higher order tractable, as implemented, for example, in ErgoAI, and applicable probably to many other AR logics and AR systems. But then, how do we tackle the probabilistic aspect, which historically has been a major source of computational explosiveness? Here we can do it by having higher order knowledge, meta-knowledge essentially, about the structure of probability distributions over sets of logical statements. So for example, on the right, we see, say if you've got 600 logical statements, say Booleans that you're reasoning over, the joint Bayesian probability distribution would be size 2 to the 600, which is over 10 to the 180. Really impractical size if you have to compute through most of that. However, if you're able to decompose in terms of multiplicative structure or additive structure, then you get something, say, under 10 to the 5th. Very, very doable from a computational viewpoint. So I only here am able to kind of sketch the technical argument and the basis for hope. But what's been happening in the program, we have this vision. We aim to get mindshare to move towards maturing the TRL, the technology readiness level, and the tools, and to standardize once we're able to get results, and to have follow-on efforts to build commercial community and be working with research, testing, and training orgs to explore applications and turn the industry paradigm inside out, to integrate AR throughout the guts of ML as opposed to patching it on the outside, like by making external calls to Lean or some classical prover, as was done with the Olympiad efforts recently. Now, the Clara program, since the solicitation was issued, we actually have a bit of update. There was immense interest from candidate performers, and the funded technical focus includes planning, as well as the things I was talking about, and distillation from the guts of foundation models into logical knowledge and reasoning, tackling integrations not only with neural nets, but also with reinforcement learning. The vision is very ambitious. We're looking for people who might cooperate, or organizations that might cooperate. We're already starting to find that in the community of researchers in Neuro-Symbolic. And we're focusing initially, especially in the realm of supply chain and logistics in terms of application areas, which is very important commercially, e-commerce and so on, not just in defense as in the US Department of Defense. I'll take questions now. Thanks very much.
All right. Thanks so much, Benjamin. Well, I've now learned that we've probably all experienced catastrophic failure, but there's also catastrophic success. That's what we want. Okay, so a few questions. One is a comment, interesting examples, easy explanation, loving it. So that's good. Could you please expand your argument on reasoning?
Which aspect of argument?
Yeah, I forgot when that question came. If you can hear me, could you clarify the asker of that question? All right, well.
Do you want to ask a different question meanwhile?
That's happening. Here's another question. What are your thoughts on autonomous weapons?
Okay, well, first of all, dangerous, obviously. Let me point out that these dangers have long been recognized in science fiction, including in a movie that was done in 1970, which I saw as a boy and gave me nightmares for years. Colossus, the Forbidden Project. And the idea in that movie was that the US and the Soviet Union both transfer effective control of nuclear weapons targeting and firing to a supercomputer, essentially, one in each of those nations. And then they decide to talk to each other and cut humans out of the loop and kill off all the humans so that they can get access to more resources. So ethicality and being able to have commanders' intent be respected, have humans in effective control of autonomous weapons, I think is very important, personally. And I can tell you that many people in the US Department of Defense, many people in the European nations and other nations that are allies of the US have put lots of concern and attention and continue to on that aspect of things. But it's been so hard to have AI systems which you can specify and test in a way where you can really have strong confidence that you understand how they're going to behave in complicated circumstances when the current assessment of a situation is changing rapidly as well. And I think if we're able to make success in Neuro-Symbolic AI progress, including in the directions that Codord and Clara are going after, that will help. Codord can be used to specify ethical policies, as well as many other kinds of policies or legal stuff, regulatory and contractual. And so from the beginning, autonomous weapons have been one of the targets that is most in people's face and looms most sharply and as a sort of highest peak around wanting to be able to automate well ethicality and effective human control around autonomous weapons.
All right, excellent. I think we're just on time. So thanks so much, Benjamin. If you have time, you can jump on. Here we have the follow-up. Thanks for taking the question. You mentioned that reasoning is something borrowed from original techniques rather than semantic web / symbolic AI.
Well, I'm going to restate that a bit in a way that might be a bit more accurate. So it is true that the notion of reasoning in AI dates back no later than the 50s, with work at CMU by Alan Newell, for example, on reasoner, and then work by Robinson on first order theorem proving, resolution, stuff like that. So it does precede the semantic web era, which was basically late 90s into the 2000s, the aughties, in terms of when the research on that happened. I would say that the notion of declarative logic programs, which was developed in the 80s, basically, is underappreciated as a fundamental contribution in computer science. So as we'll be discussing in the panel tomorrow, semantic, the very first successful semantic technology essentially was relational databases. And Sparkle and RDF databases and knowledge graphs are all kind of extensions, still working in the same logical system. So that logical system had some crucial characteristics, including defeasibility, but also essentially computational practicality, and scalability that are far superior to that of classical logic as developed over a century ago, that nowadays we call first order logic or just simply classical logic. So I think people don't realize just how deep the roots run here. And so I appreciate your question. I think that one of the things that really has been a breakthrough in the understanding of declarative logic programs is how some of the rather subtle things that people don't necessarily really glom onto and get educated about in computer science education are what make databases be so well scalable and have the potential to likewise make rule systems that are more expressive be very highly scalable as well.
Okay. All right. And so everyone, they're starting to publish. So the fruits of this program, and these programs Benjamin is describing, are fundamental research, open publishable stuff. So thanks so much, Benjamin, and nice segue that he made to tomorrow. So we'll see Benjamin again on a star-studded panel, and we have a bunch of superstars in general tomorrow, including Turing Award winner Andy Barto, which I'm very much looking forward to, and also other luminaries, including some famous journalists and the famous Gary Marcus, and as well as I mentioned, the creator of Prologue, which we've heard some about today. So lots of great stuff tomorrow. Everyone rest up for another great day tomorrow. Thanks, everyone. See you in the morning.
Thanks. Take care, everybody.